Welcome to CCNA 200-301 course. Today, I'm going to cover Section 3, Part 4, IP addressing and routing. Today is all about IPv6. We're going to do a deep dive. Here are the topics I plan on covering today. Number 1, fundamentals of IPv6. Number 2, IPv6 address types and scopes. Number 3, IPv6 neighbor discovery. Number 4, IPv6 address assignment. Number 5, IPv4 to IPv6 migration strategies. Number 6, IPv6 routing and subnetting. And finally, I'll wrap it up with an IPv6 lab. Let's roll. Fundamentals of IPv6. So why IPv6? Well, first of all, we have actually ran out of IPv4 addresses. The only IPv4 addresses that exist today are the ones that somebody else had purchased, either an ISP or a customer, and they no longer have a need for those IPs, and they willingly want to give those IPs up. Then we basically get them repurposed and get them reallocated to a different customer who actually has a business need to have IPv4 addressing. So that's the scenario that we're dealing with today. Plus, the IPv4 addresses were very poorly allocated to begin with. Like in the beginning of the internet age, if you will, a lot of big universities here in the US, for example, ended up procuring like Class A and Class B style of public IPv4 address ranges, and that is absolutely ridiculous. Nobody should ever need a Class A or Class B style of IPv4 address space. And because of that, we had a really poor allocation of how the IPv4 addresses were assigned. Another element that is important to consider is things like network address translation, which I talked about in one of my videos, and RFC 1918 private IP addresses, which is basically a private IP address range you can use within your LAN, but you cannot route these IPs over your WAN. These two technologies, private IP addressing and NAT, are considered to hinder the innovation because everything in the networking stack has to be built around these two technologies. Instead of focusing on innovation, we're basically creating like a workaround, and that is an obstacle to coming up with creative ideas that can benefit us, that would allow us potentially to have end-to-end connectivity without having to NAT, for example. And if you think about it, we actually have a need for a larger address space. And why is that the case? Well, if you think about it, there's more people on planet Earth today than there were back in 1970s and 80s when the internet was being designed. And there are certainly a lot more devices online than there were back then. So, case in point, currently the world population is over 7.8 billion, and it's increasing by the day. So if you think about it, even if half of the world's population is using the internet, then IPv4, we know, if you watched any of my previous videos, you can only have roughly 4.3 billion IP addresses in IPv4. Well, if half the world's population is on the internet, right there, we're pretty much at capacity. But if you think about it, each human being actually has multiple devices. So if you accommodate for that, let's assume there's 3 billion people online, and all those 3 billion people have two devices that they use. They have a phone and they have a laptop or a desktop. So 2 times 3 is 6. That's 6 billion potential IP addresses that you may need for those devices to talk to each other. That's beyond the capacity of IPv4, hence the need for IPv6. And then think about devices. we have devices like IoT, Internet of Things, right? So we got IP cameras and we got smart devices and smart meters and smart city that has all these different sensors that are placed throughout the city and all that stuff. You need a lot of devices now with IP addresses assigned to them so you can remotely manage them, configure them, have visibility into them, and capture the data that you need to be able to make intelligent decisions, which is part of the digital transformation that the world is going through today. That's another important reason for needing an address space that allows us to do that. And we also need a global reachability and flexibility, end to end. So for example, from my phone to your phone, we want to talk to each other without using NAT. Now, I understand that some security people think that NAT is a good technology because it allows us to hide our private IPs. But the only reason we have this view of the world today is because that's the only lens we have that we view the world from. But if you were to look at the world from a different lens, aka IPv6 lens, then we'll realize that we have the ability to be able to connect devices end-to-end without compromising security, because IPv6 comes with some standard security features built in. And speaking of features, here are some of the key features of IPv6. It's designed to be plug and play by nature, meaning you don't have to configure your network much. As soon as you plug in the devices and you enable IPv6, the devices just automatically start talking IPv6 to each other. The network header of IPv6 has been streamlined compared to the IPv4 header. There are no more broadcasts in IPv6. Really interesting. We'll talk about that. There are extension headers. That's a field within the IPv6 header that's been added that allows a lot of flexibility to IPv6, which means new extensions can be written in the future without having to rewrite the entire protocol. And finally, we have better security with IPsec support. These are only a subset of features. There's a whole plethora of additional features, but I just wanted to highlight some of the strongest features of IPv6. Now let's look at IPv6 from the OSI model perspective, and there's a very important point that I want to hit on for you to understand the role of IPv6. What we have is an application, for example, an email that I want to send from my machine. And that email will use TCP at layer 4 or the transport layer, at layer 3 or the network layer. It's going to have to use IP. At layer 2, it may use Ethernet. There might be another technology, but let's just assume it's Ethernet because that's the dominant technology in use today. And then at the physical layer, we'll have bits and bytes and all that, and electrical signals and photons. But the key here is that what we do when we go from IPv4 to IPv6 is that we just simply stop using IPv4 and we switch over to IPv6 at the network layer of the OSI model. So all we're doing is just changing the stack at the network layer, and the layers below IP and the layers above IP remain the same. And that's the beauty of having a reference model like OSI in a Lego block style, is because we can go ahead and add different components to different layers of the OSI model without having to rewrite the entire thing. And that's why it's such a powerful reference model, and it has survived for so long, is because of its modular nature. Now let me give you a quick overview of IPv6. So the IPv6 address size is 128-bit. That is absolutely ridiculously gigantic, and we'll talk about it in a moment. It's defined in RFC 2460. As opposed to IPv4 address space of 32-bit. And what that means is we have 3.4 times 10 to the power of 38, or 340 undecillion addresses, or it could also be rewritten as 340 trillion, trillion, trillion. Now that is an absolutely insane amount of IP addresses. And to put things in perspective, let's quickly take a look at this chart right in front of you. So all the way up top, we got a million, then a billion, then a trillion, then a quadrillion, and we keep going down until we get to undecillion, okay? And we have how many of these undecillions? We have 340 of these bad boys, the undecillion. I mean, this is an absolute craziness. So the bottom line is, unless our scientists start assigning an IP address to every single human cell in our body, we shouldn't actually run out of IPv6 addresses for the foreseeable future, or at least for the next couple of generations. In IPv6, the address is divided into 8 groups of 4 hexadecimal characters each. So let me show you how an IPv6 address could be written. Now, as I mentioned earlier, IPv6 is one of those topics that absolutely instills a fear of God in people's heart because it's so different. Hang in there with me. Throughout this video, I will keep explaining different components and how the structure of the IPv6 address works. So by the time you're done, you'll be very confident. And I encourage you to actually watch this video a couple of times for this topic to sink in, especially if you're brand new. But if you are already familiar with IPv6, then this video will absolutely solidify your knowledge in the realm of IPv6. So back to the address here, as I mentioned, it's 8 groups of 4 hexadecimal characters each. So each character here is a hexadecimal. So 4 is a hex, 0 is a hex, 0 is a hex, 1 is a hex. Then after the colon, all of these values are hexadecimal, all of these values are hexadecimal, and so on and so forth, all the way to the end. Each hex character is 4-bit, hence each quartet is 16-bit. Another element I want to bring to your attention to is this one block of IPs is called a quartet, as opposed to, if you remember, in IPv4, we had octets. So IPv4 had octets. Here in the IPv6 world, we have quartets. And each quartet is 16-bit because each hexadecimal character is 4 bits in binary. And 2 hex characters make up a byte, or 8 bits. So if this is 4 bits, and if this is 4 bits, then if you were to combine them together, that's 8 bits. And 8 bits equal 1 byte. Now let's quickly look at the conversion chart. Here's a decimal, hexadecimal, and binary conversion chart. Now, technically, we don't need to worry about decimal when it comes to IPv6 addressing because everything is in hexadecimal. But as I mentioned, each hex value in IPv6 is composed of 4 binary values. Okay, so 0 would be 4 zeros. If you look at A, that's 1010. And Y is 41010. Well, if we map this back to handy-dandy binary conversion chart, so 1, 2, 4, 8, these are different bit positions. Well, if we were to enable this bit, because this is A equals 10 from a decimal perspective, right? So that means this bit position is on, 4 is off, 2 is on, 1 is off. Well, when 8 plus 2 is on, that would be 1010. And that's exactly what we're seeing here. That's A. And when it's F, that's all ones. With this context in mind, you'll be able to understand IPv6 addressing in a much better way. So there are 2 rules to shorten the IPv6 address. Rule number 1 is eliminate group of consecutive zeros via double colon. So what does that mean? So if we look at this full IPv6 address that we looked at just a moment ago, 4001:0070, so on and so forth, the simplified version of this IP address could be written as this. So what that means is, you see what we're doing here is we're taking a chunk of these zeros, these three quartets, quartet number 3, quartet number 4, and quartet number 5. We're taking them and we're collapsing that into colon. So that's one of the ways this can be re-represented and rewritten in a more simplified format. Because remember, as human beings, machines can understand binary. They don't even worry about hex and all that. At the end of the day, machines only understand bits. As human beings, our understanding of the world is more limited because of our limited capacity. So we have to make sense of things. And for us to make sense, we can only understand a very small string of numbers. So because IPv6's address is ridiculously large, powers that be who designed IPv6, they came up with the strategy of compressing the IPv6 addressing in such a way that we can kind of minimize the address space so it's easier for us to look at and make sense of. Now, to continue building on this, rule number 2 is we can also drop the leading zeros. What that means is the simplest form of this IPv6 address that we just looked at. So initially, this is how we write the full address. Then we simplified it further. And if you look at this one, this is the simplest form. And what did we do here? We dropped these 2 zeros and we dropped this 0 right here. You see they're missing. If you look below, right here, these 2 zeros in blue and this 0 in blue is missing. And the reason it's missing is because it's totally allowed according to the rules of IPv6. Couple of additional things I want you to keep in mind. Successive fields of 0 can be represented as colon, but that can only happen once. Here's an example of an IPv6 address right here. And this can be rewritten as, you see what we did was we took the second quartet and we collapsed it in a single 0. We don't do double colon here. But you see, we took the 4th and the 5th octets and we collapsed them into double colons. In other words, according to the IPv6 rules, wherever we have the longest set of zeros combined together, we'll collapse that into double colons. And where we have a smaller set of zeros, we can just collapse them into a single 0. That's totally legal, totally allowed. Here's another IPv6 address we can look at. So FF01:000 all the way down to 1. Look at what we did. We took all of these quartets and we collapsed them into colon. See, now it's a lot easier. This is even easier than IPv4, for God's sakes. FF01:1. So I'm starting to like IPv6 already. Now let's take a look at this. So we took an address that's represented as all zeros and a 1 at the end. We took all these zeros and collapsed them into colon 1. Now this smokes IPv4 in simplification. I mean, it can't get any simpler than this. I mean, this is absolutely beautiful. And I mean, check this out. If you thought this was beautiful, I mean, here you might actually get tears in your eyes, okay? Here we have all zeros collapsed into colon. How beautiful is that? And by the way, this is how we represent a default route in IPv6. This is way simpler than 0.0.0.0 in IPv4. Remember that, guys? When we configure default route in IPv4, tell me if this doesn't smoke this 0.0.0.0. So you see, IPv6 can be simpler if you can look at it a little bit differently and understand the rules and regulations of IPv6. However, there are a couple of things you need to keep in mind to make sure you're not stepping into the illegal realm, meaning you're not doing anything that's not allowed. So for example, you can't have double colon twice. So you can't have an address that has colon here and colon again. You cannot do that, because this confuses the system, okay? You may be able to do it when you're writing it on a piece of paper, but computers will never make that mistake. And this is against the rules of IPv6 addressing. So keep this in mind, because this could be a beautiful exam question to get you to see if you really understand the rules of IPv6 addressing. Now let's quickly look at the difference between IPv4 and IPv6 header. Now to the left is an IPv4 header. It's 20 byte in length and it's composed of 14 fields. Okay, so if you were to count all these fields in this header, there are 14, trust me. Go ahead and count them. And if you look at the IPv6 header to the right, in contrast, it's double in length, it's 40 byte, but it's a lot more simplified. It's only 8 fields as opposed to 14 fields. So it's been really, really optimized. You have different fields like version that actually says it's version 6, traffic class is used for QoS, flows is used for the sequence of packets and to avoid packet reordering. Payload length is all about payload. Next header is the extension header that we talked about, which allows a lot of flexibility to IPv6. Hop count, basically TTL in IPv4 has been renamed to hop limit in IPv6 header. And then we have a 128-bit source address, and then we have a 128-bit destination address. And to the left, the legend here shows all the fields that have actually been removed or pulled from IPv6 to make the header more streamlined. Now let's shift our focus to IPv6 address types and scopes. This is the key topic. If you guys understand this, you'll pretty much understand everything there is to know about IPv6. In RFC 2373 section 2.4, IP addressing architecture is defined. And what it says is that we take the IPv6 address and we break it into different portions. And the leading bits define the specific type of an IPv6 address. So if you look at the table at the bottom of the screen here, you'll see how the RFC has carved out the entire IPv6 addressing architecture. So in the first column, you're seeing the allocation. In the second column, we see the prefix in binary. And then finally, in the third column, we see the hexadecimal value associated with those prefixes. So if you look at our allocation number 1, called aggregatable global unicast addresses, the prefix start with 001 in binary. And it's represented in hexadecimal as 2000. Now you right now might be extremely confused. What does that even mean? So let me do some whiteboarding to explain. If we were to look at the address, let's say 1A2C. This is the first quartet in the IPv6 address space. Each of these values here is a hexadecimal. Each of these digits is a hexadecimal digit. So if we were to zoom in to the 1 here, it's actually 4 bits. So these 4 bits could be, for an argument's sake, say it's all zeros, and then the second would also be all zeros, and then so on and so forth. The RFC says that regardless, the bits will always start with 001. That has actually been reserved. What we'll do afterwards is we'll then have all zeros all the way through. And where this range would end is, once again, the first 3 bits are always going to be reserved according to the RFC standard. So what we can do is we can almost draw an imaginary line here, and everything to the left of this line is reserved according to the RFC. But to the right of it, we could have all the ones in the first quartet. And if we did that, let's say if this is the start of the range, where we have all zeros here, and then the bottom here, if this is the end of the range, what we'll get is the value 2000 all the way up to 3FFF. Well, you might be asking, where does the value 2000 come from? Well, if you look at the first hexadecimal digit, because the RFC says it must be 2, that means if you look at these 4 digits here, and if you look at our binary conversion chart, 1, 2, 4, 8, that means the bit in the third position, the third most significant bit is actually on, all the other bits are off. That means that our address will start with 2000. because the first digit is 2 and then the rest of the digits are all zeros. And the highest value that we can get is 3FFF. And what that means is, once again, look at the bottom here, 2 plus 1 equals 3. And then if the rest of them are all ones in hexadecimal is F. So that's the total range of global unicast IPv6 addresses. Now, second type of allocation you want to look at is link local unicast addresses. So the link local, the first 10 bits must always be in this sequence as we see. And when we convert them into hexadecimal, we get FE80. Well, next up is site local unicast addresses. And here's how the sequence is specified, and it should translate to FEC0. And finally, we have the multicast addresses. And what we see is the first 2 hex digits in the first quartet of the IPv6 address will always start with FF. Now, that said, it's very important that you understand that the site local unicast addresses, that has been deprecated. We now have what are called unique unicast addresses or unique local addresses. And we'll talk about that in a moment. A new RFC came along and it basically invalidated this site local unicast addresses. It changed to something different, and we'll talk about it momentarily. Now, here's what I plan on doing next, guys. I'm going to zoom into each of these allocations so you get to see how each of these components are specified according to the RFC standards. First, we'll look at IPv6 aggregatable global unicast address. Say that 3 more times. Number 1, it's the same as IPv4 public space. So if you want to look at it from an IPv4 perspective, you can think of the public range of IPv4 addresses, which means these addresses are internet routable. We talked about the prefix range. I did the binary math for you a little bit ago. So the entire range is in hex begins with 2000 and goes all the way up to 3FFF. It can also be represented as 2000:/3. And the way this gets carved out by the service providers is, once again, the first 3 bits will always be 001, right? So that's the first 3 bits. The next 45 bits is the global routing prefix that's assigned to the ISPs, and that's the provider space. And then what we get here is the 16 bits at the site level, and this is something that's assigned to the customers. If you need a internet routable IPv6 address, you'll go to your ISP and request a block. Your ISP will give you a subnet, and then you can take that subnet and assign it to the rest of your organization. And if you want, you can also further subnet it, meaning you can further subdivide it into multiple additional networks if you would like, so you can accommodate your entire company. If you have 100 offices or maybe even 10,000 offices, or regardless of the number of offices, you can just take the appropriate block from your ISP and allocate the chunks accordingly. And the cool thing is, we'll talk about subnetting in this video, so just hang in there with me as we continue moving forward. And then the final piece is the last 64 bits are the host ID, and typically the last 64 bits are the interface ID, which basically is a combination of MAC address and some additional data that's attached to the MAC address, and we'll address that momentarily. Here's another way of looking at it. The registry prefix is assigned by IANA, which is the Internet Assigned Numbering Authority, and it's assigned to the regional internet authority. So this could be for us, for example, ARIN, which stands for American Registry for Internet Numbers. And this could be the initial chunk. This is just an example. Then ARIN might assign a chunk, a /32 block. So the top block was /16. Then ARIN might assign, let's say, AT&T or Verizon or Comcast or whoever, a /32, And then the ISP will take that chunk and allocate a /48 block to the customer. And then the customer can take that /48 block and assign /64 for individual links, for example. And this gives the customer the ability to play with 16 bits. 64 minus 48 is 16 bits. So the customer can play with these 16 bits to further subdivide or create subnets within their network and allocate chunks to different sites accordingly. Now let's look at IPv6 link local address. It's assigned automatically. As soon as the IPv6 host comes online, it just automatically gets a link local address. You have to do nothing. It's very similar to, if you guys remember how Windows would allocate 169.254 addresses. If you ever remember seeing one, you typically get this address when your machine is unable to contact a DHCP server. It will self-assign itself a 169.254 address. That's also called a PIPA, which stands for Automatic Private IP Addressing in Windows. Every IPv6 interface must have this address. So the previous address that we just finished talking about, the global unicast address, that address is not a must. You don't have to have that address. You only need to have it if you're going to route traffic to the internet at an IPv6 level. But if you just need to communicate with other devices within your LAN or local area network, you can get away with just having link local addresses that are automatically assigned. And these addresses use Neighbor Discovery Protocol, or NTP, which replaces R in IPv6. And the link local addresses, according to the RFC standard, always begin with FE80::/10, which means the first bits are always in this sequence, as you see in front of your screen, followed by 54 zeros. And there's something interesting in IPv6 called Modified EUI 64. And EUI stands for Extended Unique Identifier. And what that means is we take the last 64 bits in the IPv6 header, and we also look at the MAC address of the machine, and MAC address is 48-bit, and we manipulate those bits. To explain this better, let me quickly jump on CLI so you see what I'm talking about. So let's quickly take a look at the MAC address of our machine here, of our fast Ethernet interface. Let's do show interface fast Ethernet 0/0. You see what happens with the link local address is we look at our burned in address, which is our MAC address. By the way, the difference between the MAC address in parentheses with BIA in front of it, which stands for burned in address, and the MAC address to the left of it, is that on a Cisco device, I'm on a Cisco router right now, I can go ahead and manually assign a MAC address, which is different than the manufacturer ID. But the ones that's assigned by the manufacturer is a unique address, and that's the one that's called burned in address. Now, I may change the one to the left, but I cannot change the burned in address. Okay, I just wanted to quickly specify that. Now, let me explain how Modify EUI 64 works. If we were to take this MAC address and do what it's suggesting us to do, which basically says we take the 48-bit MAC address and we insert FFFE in the middle of it, and then we change the 7th bit. Let me show you what that means. Let's do that together. First thing it says is we're gonna divide this into two different pieces. So there's CC01B2. That's one portion of it. That's the first 24 bits of this MAC address. And then we'll do 65.000. So once again, this is the first 24 bits. And this is the last 24 bits of our MAC address, right? Because MAC address is a 48-bit address. And see what it says? We have to insert FFFE in the middle. So we do FFFE in the middle. But then it also says one more other thing. It says we also have to flip or invert the 7th most significant bit. And this bit is called U/L. It stands for universal or local bit. When it's set to universal or U, that's the manufacturer ID. Okay, so that's the one set by manufacturer. If it's L, L means it was defined by the administrator. So what we want to do is, because we are modifying this bit, this tells the router that this bit has been manipulated by an administrator. The 7th bit here means, remember, this is the hexadecimal address, right? So each hex is 4 bits. So we'll take CC and zoom in. How is C represented in binary? Well, remember the handy dandy chart, 1248. We're going to look at that, and then 1248. We can do that. And then find out this C position. But before we do that, we need to even figure out what C means from a decimal perspective. C is 12 in decimal. Well, we're going to have to come up with number 12 here. So if 8 is on, and 4 is on, and 2 and 1 are off, that gives us a value of C. Now this says we have to flip the 7th bit, but let's go ahead and finish this out first. 1100. Now, if you look at the bits here, starting from left to right, this is bit number 1, bit number 2, bit number 3, bit number 4, 5, 6, 7. It says to flip it. That means if it's 0, we're going to set it to 1. Well, when we do that, what happens to this C? This C now becomes 8 plus 4 is 12. So that's C plus 2 makes it 14. 14 will make it E. So we'll have to now switch this to E. So it's going to become CE01. Now let's see what the router does when I go ahead and enable IPv6 on the interface. So I'll do configure terminal, and I'll go to interface fast Ethernet 0/0, and I'll say IPv6 enable. All I have to do is just type in this command to enable IPv6 on this interface. That's it. And you'll see what happens. When I do show IPv6 interface, you'll see that we only have one interface that's running IPv6. Now, currently it's administratively down because we haven't enabled it yet. But you see it says IPv6 is enabled. Link. This is a link local address, and it's set to FE80 and then CE01 B2FFFE65. So now let's compare this value, which was calculated by the modified EU64, and see if this matches the math that I did earlier. And let's take a look. And sure enough, you see CE01 B2FF FE65 0000. And that's it. So that is really cool. Here's another example of applying modified EUI64 to a MAC address. So it becomes this address right here based on all the steps that we went through. If you were to apply those steps here, you can pause the video and actually do this. I would suggest you do this, and you'll come up with this value that will reinforce some learning. Now you might be thinking at this point, why did we have to do this? Well, the reason we did it is because we want to make sure that our last 64 bits of our IPv6 address will always be unique, because we don't want to run into duplicate IP address situation, right? So when we take our MAC address, which is supposed to be universally unique, and then we add this modified EUI64 math to it, it's supposed to make it even more unique. And there should never be, at least theoretically, a case where you should find two IPv6 devices on your network with the same address. If you do, then there are additional mechanisms that actually protect against that, and we'll talk about that in a moment. But theoretically, you should never have that problem. Now let's talk about IPv6 unique local addresses. These are analogous to IPv4 private IP addresses. So you guys remember 10.0.0.0/8 and 172.16.0.0/12 and 192.168.0.0/16. That's exactly what the unique local addresses are for, which means they're not routable on the internet, and they're not registered with any numbering authority. They're only valid on your local LAN. And initially, IANA reserved a prefix that began with FC00::/7, but then another RFC came along a couple of years later, RFC 4193, that changed things a little bit, and it says that the 8th bit is set to 1. So in practice today, what you should see in real world is a unique local address that begins with FD00::8. But you should also know this address for exam purposes. And here's how it looks like. When we say FD, like these are the first two hex digits, that's the first 8 bits that, they're reserved. That's how it looks like. The rest of the 40 bits, that's global ID for our network. What we can do then is we can play with 16 bits to do subnetting. And finally, remember, we always want the last 64 bits in IPv6 to be associated with the interface ID. In other words, if I were to draw a line in the middle here, the bits to the left would actually be what you would call network bits. The bits to the right are host bits. Once again, very similar to IPv4 from an overall logic perspective. So if you guys go and watch my IPv4 addressing video, you guys will start to understand the fundamentals of subnetting. I highly recommend that you understand the IPv4 subnetting first before we get into the IPv6 subnetting, because it's going to be a lot easier. Now here's a quick recap of IPv6 address types and scopes. First, we have a link local address that's a must-have address. And the use case for this one is it's local to the link between two IPv6 endpoints. We have unique local address next. That's optional. It's organization-wide address space, and it's analogous to IPv4 addresses. We also talked about global unicast address. This is also optional. The use case for this one is internet routable address space, and this is analogous to the public IPv4 addresses. And this is how the scope looks like. So if you were to visualize the scope, the link local addresses have a very narrow scope. They're only good on a link. Then the unique local address scope is organization-wide. So this is your entire company. And then the global scope is the internet routable address space. Now let's quickly talk about IPv6 multicast address. This is the last type of addressing we'll discuss according to RFC 2373. It's analogous to IPv4 Class D range. So if you guys remember 224.0.0 through 239.255.255.255, that's what IPv6 multicast address space is analogous to. First bits, according to the RFC standard, are always set to FF and also represented as FF00::8. Now, if you were to look at it from the addressing space perspective, these two hex digits, FF, which in binary are all ones, they are reserved. And then the bits right next to it, you could have a flag here. Typically, you'll see that as a 0, which means permanent. Unless it has 1 in front of it, that means it's temporary. And then the last hex digit in that quartet would be the scope. And you'll see things like 02, for example. You'll see that a lot. As a matter of fact, you'll see FF02 a lot. That 2 means it's a link local scope. Okay, so something to keep in mind. Now, here is a multicast address table to show you how it all connects to help crystallize IPv6 multicast groups. All host address in IPv6 multicast is FF02::1. It's analogous to 224.0.0.1 or all host broadcast, which is all 255s. That means when you send anything to this destination, all hosts will get it. In contrast to if you send something to FF02::2, that's equivalent to 224.0.0.2. That's all routers, not all hosts. Only all the IPv6 routers will get packets in this multicast group. Another type of address that's important for you to understand is solicited node multicast. And that is FF02::1: FF00:00:000/104. This is what replaces ARP in IPv6. So remember ARP in IPv4? What's the purpose of ARP in IPv4? The whole idea is we already have an IP address. We need to determine the MAC of the other machine, the destination machine. In this case, in IPv6, solicited node address is used to find the MAC address of the destination host. And let's go back to the CLI so I can show you a couple of things that we just discussed. So remember we were looking at show IPv6 interface earlier. Look at the joined groups. These are the multicast groups. So FF02::1, what is that? Well, we just looked at it. FF02::1 is all hosts. So that's what it is. Okay. And then the one underneath it is FF02::1:FF65:0. And you see this solicited node address here at the bottom, FF02::1:FF. That's what's being represented here. Next up is 4 types of ICMPv6 messages, and they're divided into 2 broad categories. One is called solicitations. The other is called advertisements. Solicitation means when you request something from someone or ask for something. Advertisements mean when you reply to somebody. Okay? So first up is neighbor solicitation. And what we do in this type of messages, we request information from neighbors on the LAN. It's the equivalent of ARP request in IPv4, if you guys recall. Neighbor advertisement is you advertise yourself to neighbors on the LAN. It's analogous to ARP reply. We also have another category for routers, specific to routers. That's called router solicitation. So you request information from routers on the LAN. Typically a host would send this, or even a router could send this. One router could send this to another router. Analogous to ARP request. And the router advertisement is you advertise yourself as the LAN router in a response. This is equivalent to ARP reply. Now, router solicitation and router advertisement make IPv6 plug and play via the stateless auto configuration we talked about and duplicate address detection, and we'll discuss that next. Next thing I want to talk about is solicited node multicast. So in IPv6, a very important concept is to avoid duplicate IP addresses, right? Because we have to figure out IP addresses automatically, and we don't even need a DHCP server to figure that out. The hosts just automatically assign themselves IPv6 addresses. It's very important that we avoid duplication of IPv6 addresses. So what we do is a neighbor solicitation is sent to a solicited node multicast address of FF02::1:FF00:0000/104 plus the last 24 bits or last 6 hex digits of our IPv6 address. So if you were to look at an IPv6 address format, up at the top we got the network portion, 64 bits to the left, and then 64 bits to the right is the host portion, right? If you were to map that, what we see is in solicited node multicast address, we have 104 bits that are reserved or assigned to the solicited node multicast address. And the lower 24 bits come from our interface address. And let me show you what that means. So for example, if we have a unicast address of 2001.1AB:2003:1:CBAC:DF01, it has a corresponding solicited node multicast address of FF02::1:F. And you see what we did? We took the last 24 bits or the last 6 hex digits and we added them to the solicited node multicast address. Now, under this context, let's go back to CLI and see what we're seeing. So you see, this is our link local address, right? And here's our solicited node multicast address. Now pay attention. You see after the FF, you got 65:0. This comes directly from here, 65:0. So these are the last 24 bits or 6 hex digits. Well, you might say this is not 6 digits, Naj. All I'm seeing is only 3 hex digits. Well, remember, in IPv6, we can collapse 4 zeros and 1 0. Remember the IPv6 rules we discussed earlier? So in reality, you actually have 4 zeros here, but they're actually being collapsed by the router into 1 0. And that's what we're seeing here. Now, let me explain this further, okay? So let's go to interface fast Ethernet 0/0. Let's say if I were to assign ourselves IPv6 address 2001:0000:0001:/128. If I did that, watch what happens when we look at show IPv6 interface. So under the global unicast IP addresses, we now have this address show up. But look what happened. We took this address right here and we applied those rules that we learned about earlier to this address. Now that I'm here on the CLI, let me show you one more thing. So if I were to assign myself IPv6 address 2000:0000:0000:0000A/64, watch what's going to happen when I do show IPv6 interface. Under global unicast address, you see what happened? We have 2002:AA. What happened? You typed in this address. Well, if you guys remember the rules of IPv6 that we talked about at the top of this video, what ends up happening is the router will automatically grab all these zeros in the middle quartets and collapse them into : as you see here. Okay? So these are all collapsed into : and these 3 leading zeros in front of A can be dropped because they're leading zeros. So it's legal to drop the leading zeros. What is considered illegal is to drop the trailing zeros, okay? And let me explain what that means. So it's illegal. It's not allowed to drop trailing zeros. So for example, if you had a scenario where you had something like 0, 1, 0, 0, you could definitely drop the leading zero because that's allowed. But if you were to also drop these 2 zeros at the end, the trailing zeros, the router would get confused. It wouldn't know the exact bit position of this one because there are zeros in the front and zeros at the back. So that's why the router doesn't allow, that's why the trailing zeros are not allowed to be dropped. So here's another big picture view of why we need solicited node multicast address to begin with. In basic terms, the IPv6 host sends a request to the solicited node multicast address asking neighbors if anyone on this LAN segment has the same IPv6 address. Assuming no one else responds back with our IPv6 address, that means our IPv6 address is unique, and this process is called duplicate address detection or DAD. This process also helps us determine the MAC address of our neighbor, similar to ARP in IPv4, and if all goes well with duplicate address detection, meaning we did not find anybody else with our address, and our address is indeed unique, we then send a network advertisement to all host multicast of FF02::1. Now, to solidify this knowledge, let's jump back to the CLI with this understanding, and let me run a couple of debug commands so you can actually visually see how this works. So let me go to router 2 that we haven't touched. Let's do show IP interface brief. Yep, we haven't touched this router. Let's also do show run interface fast Ethernet 00. Nothing configured on it. It's shut down as well. So we'll go to global config mode. If you guys remember, we first have to turn on IPv6 unicast routing. So we're going to go ahead and do that. Next thing we're going to do is we're going to go to interface fast Ethernet 0/0. We're going to do no shut on it. But before I do, I forgot to actually enable debug. So I'll do debug IPv6 neighbor discovery, and I'll do debug IPv6 packets. And I'll do debug IPv6 packet, not packets. So let's go to the global config mode, go to interface fast Ethernet 0/0. And what we'll do this time around is go ahead and enable IPv6 on this interface and watch what happens. Look at all the debug output that it's generating for us. Let's go ahead and do UAll. This means go ahead and disable or turn off all the debugging. Basically, it stands for U stands for undebug. All means stop all debugging. Now let's see if we can make sense of this debug output. So what we have is ICMP version 6 neighbor discovery. We're sending neighbor solicitation for our link local address on our fast Ethernet 0/0. It's destined for solicited node multicast address of this, okay, which again, if you match the last 6 hex digits, they match this multicast address, which is the solicited node multicast address. And then we wait until we find out through the duplicate address detection that our address is indeed unique. And at that point, because we have confirmed that we have a unique address, we'll go ahead and send a neighbor advertisement for this address to the rest of the LAN, okay? And it's sent to the all hosts address of FF02::1. So all the hosts on our network now know that this is our IPv6 link local address and they can reach out to us. And at this point, what we should be able to do is, let's take a look. Let's do show IPv6 interface, and we're up. Let's also take a look at router 1 and look at to show IPv6 interface. We're also up here. If you were to grab this link local address, we should be able to ping it from router 2, for example. So let's go ahead and do that. Let's do ping. And this address that we grabbed from router 1, when we do that, notice it asks for output interface. We're going to type in fast Ethernet 0/0, and boom, we were able to ping it, and it was 100% successful. What that helps us do is it helps us build what's called an IPv6 neighbor table. It's similar to an ARP table in IPv4. Let's quickly go ahead and take a look at that. Do show IPv6 neighbor. Take a look at this. So the guy that we just pinged, we're able to extract their MAC address. What I want you guys to understand is, by just the act of pinging gave us the ability to figure out our neighbor's MAC address, because remember, the neighbor's MAC address is encoded in this value right here. If you were to correspond this to this hardware address or the MAC address of the neighboring router, remember we had to add FFFE in the middle. Remember that? So this is what we are seeing here. And then we had to flip the 7th bit and all that. So the CC here became CE. And then the rest of it is basically, it matches this hardware address. And we inserted FFFE in the middle. So I wanted to let you know, this is how neighbor discovery process helps us find the MAC address of our neighboring device. Now here's a quick recap of everything that we have talked about so far in the IPv6 neighbor discovery process. First, we go through the neighbor solicitation and neighbor advertisement. It helps us find a MAC address of our neighbor and a confirmation that our IPv6 address is unique. And I also showed you the debug output of that. And the next thing that happens is we have a router solicitation and router advertisement. Helps us find a MAC address of our neighboring router and a prefix or prefixes plus prefix length used on local link. So once you have the routers start communicating with each other, they start exchanging some additional pieces of information in addition to the MAC address, and that is the prefix length and the prefix that they have available. The neighbor discovery process, plug and play, makes DHCP optional. So you don't need to have DHCP, by the way, in IPv6. You can get away with just letting IPv6 do its magic that we just talked about. But in real world, of course, you would want to have a DHCP server because you want to configure IPv6 address management, right? So you want to use some sort of tool that allows you to do IP address management or IPAM, very similar to the IPAM tool that you might be using in your environment today for managing IPv4. Same thing, because the cool thing with DHCP is not only you get an automatic IP, but you also get a DHCP parameter along with your local default gateway, and you can get some additional options with that as well. Now let's quickly look at the IPv6 address assignment. So here, what I want you to pay attention to is in this decision process tree, there are two main components here. We got the link local address, okay? And we looked at it, and as soon as we type in the command IPv6 enable, our router automatically assigns ourselves a link local address using our MAC address using the dynamic EUI64 interface ID, right? So we saw that in action. We can also manually specify that too if you want. But most likely, there's no reason for you to define static IPs. Most likely, you're just going to let the router do its thing. Now, on the other side of the spectrum, to the right, we got the routable address assignment. This is where we have different options. We have static and we have dynamic. Now, with the static option, we can type in on the interface IPv6 unnumbered, for example. Now, this is a blast from the past. We don't use it anymore because this was used on serial links, primarily point-to-point serial links for conserving IP addressing space. In IPv6, we don't have that problem. So in real world, you should never see this used. Okay, so let's just eliminate one option there to simplify things for you. Typically, you would type in an IPv6 address yourself if you're doing a static assignment. We can also do stateless auto configuration. And once again, in IPv6, devices are automatically programmed to assign themselves an IPv6 address. We also saw that in action earlier, including your Mac, Windows machines. They have the ability to just automatically assign themselves an IPv6 address. And the final component is the DHCP version 6. Okay. Now, to show you that in action on CLI, let's go take a look. So we'll just look at the routable internet address assignment. Okay, so if I were to take you to this interface and type in IPv6 address, you see how many different options we have available to us. We can assign ourselves a link local address or an entire global prefix, or we can do what's called an auto config. So when we type in auto config, this would be the stateless configuration right here under dynamic. Okay. If we manually specified the IP, like we did earlier, and I showed you, remember on router 1, this 2002 address, ::A, this would be the example of assigning an IPv6 address under static category. IPv6 unnumbered, you'll never see that in real world, so I'm not even going to bother showing you this. And then the DHCP, what you can do is you can type in IPv6 DHCP, and you can specify if it's a client or if it's an IPv6 relay or if it's a server. You can specify that, and it will just automatically pick up an IPv6 address if you had an IPv6 address management solution. Now let's quickly talk through the IPv4 to IPv6 migration strategies. This might be a little bit beyond the scope of CCNA exam, but I think from a real-world practicality perspective, it's crucial that you have this information. The first strategy I would like to discuss is what's called dual stack. So what dual stack means is it allows both IPv4 and IPv6 to coexist. And as you can see in the diagram here, we've got this host up at the top that has an IPv4 address. We have host at the bottom with IPv6. And then we have routers that have both IPv4 and IPv6. And they have interfaces into the IPv4 internet or the IPv6 internet accordingly. And most of the new devices today, whether they're routers or switches or endpoints, they are dual stack capable and dual stack ready. And that's a great way to get started at IPv6, which means you don't have to rip and replace anything. You don't have to rip out IPv4 to implement IPv6. You can literally, on the same machine, turn on IPv6. And you can do the same thing on your switches and routers, so you can slowly make that migration. This is the most popular way of migrating in real world. And here's how you would configure dual stack on a router. First, you'll type in IPv6 unicast routing command in a global configuration mode as shown here. And then you'll go into the interface and you'll have both IPv4 address and you'll have an IPv6 address specified in the interface. And that makes it dual stack. The next strategy is called NAT-PT. Stands for NAT Protocol Translation. And what happens in this scenario is we've got this router in the middle that becomes the intermediary, and it's capable of translating IPv6 into IPv4 and vice versa. So this is as if I knew Spanish and English. I would listen to a speaker who's speaking English to me and then translate that into Spanish and vice versa. So this is exactly what the NAT-PT is doing for us. There are a couple of additional strategies beyond the two that I discussed, but these two are the most practical ones that I've seen implemented in real world. Now let's talk through IPv6 routing and subnetting. First, let's look at routing. IPv6 supports both static and dynamic routing. Here are the type of static routes supported by IPv6. A regular static route, a static default route, it's represented as ::/0. A static host route, represented as /128. A floating static route, and what you do here is specify higher admin distance. And an example of this you guys can see in my IPv4 video that I did, and you'll see what a floating static route is. Dynamic routing protocols that are supported by IPv6, RIP-NG. So the original RIP protocol or routing information protocol had to be rewritten for IPv6, and it's called RIP Next Generation. We have EIGRP version 6, this enhanced rewritten protocol. We have OSPF version 3, this is the enhanced version of OSPF supporting IPv6. We got ISIS and BGP. Both of these protocols natively support IPv6. And they didn't have to be rewritten. Now, a quick recap of global unicast address format. So if you guys recall, we got an IPv6 address that has two different pieces to it. We got the network portion and we got the host portion, both divided into 64 bits equally. Now, if you were to zoom in, if you guys recall, so we have this authority called IANA, Internet Assigned Numbering Authority, that assigns the prefix to a regional internet registry, which would be ARIN, American Registry for Internet Numbers. Then ARIN would actually take a block and assign it to a local internet registry, like an AT&T or Comcast or Verizon or whatever, and that would be a /32. And by the time it gets to the user, they're assigned a /48 block, and then it gives them the ability to manipulate between /48 and /64. This gives them about 16 bits to play with. And they can use these 16 bits to further subnet their environment or to create multiple chunks of that network assigned by the ISP. Under this context, let's continue moving forward. So you reach out to American Registry for Internet Numbers as a customer and you go, look, I need an IPv6 block that is unique globally. You have to go ahead and do that online. You can Google it. You'll see you have to fill out some forms and you have to provide justification for it. But it's easy to get IPv6 addresses. Let's assume they give you the following IPv6 prefix. They give you 2001:1111:AAAA:/48. Once you get that, your business requirements dictate that you need 7 subnets, meaning let's assume you have 7 locations. And each location you want to assign a unique subnet. Well, we already know that IPv6 address is a 128-bit address divided into 2 portions of 64 bits each. So what we'll do is we'll take the /48 assigned by our ISP and we'll go ahead and manipulate this portion, these 16 bits right in the middle of the 48 bits to the left assigned by the ISP and the 64 bits that are unique to the interface or the host. We'll manipulate these to come up with the subnets we need to come up with. Let's go ahead and do that. And all together, the leftmost become the subnet prefix and the rightmost would become the host prefix. Now let's continue building on that. So we're going to take that chunk that was allocated to us by our ISP, and this is what we came up with. We added these right here. So 1, 2, 3, 4, 5, 6, 7. Now I decided to do this, but you could pick whatever you want. This could be A001 if you wanted to, or whatever have you. But I picked these because it will further simplify our addresses, and I'll show you that in a moment. Can these addresses be shortened any further? If you guys remember the rules of IPv6, the leading zeros, which are these 3, can be dropped. And when we drop them, that means the router will just literally ignore all of these zeros if you type them in. And that will make it easier for us to identify our address. Now let's do a quick IPv6 lab. We're going to focus on static routing. Dynamic routing is outside the scope of CCNA. Here's how our topology looks. We got 2 routers. I wanted to keep it real simple. We got this prefix right here. That's a globally assigned prefix up at the top, and we'll replace X with either ::1 on router 1 or ::2 on router 2. And here are all the loopbacks that we'll create that belongs to that range that we just talked about that was allocated by our ISP. And once we do all that, router 1 should be able to get to the loopback addresses that are represented as a LAN on router 2 and vice versa. Router 2 should be able to get to all the loopbacks on router 1. And that's why I'm keeping this lab simple, because as it is, IPv6 is a complicated topic. I wanted to keep it very simple. So here I am on router 1. I'm going to go ahead and type in the command default interface fast ethernet 00. If you don't know this command, you should. What it does is it goes ahead and eliminates and removes all the previous configuration and brings the interface back to the default, the factory default configuration, which is the blank config. So I'm going to do that on both sides. And at this point, we shouldn't have anything else configured on this router. To get things started, we're going to start off with IPv6 unicast routing. That's important. I'm going to do the same thing on router 2, IPv6 unicast routing. So this way we can enable IPv6 routing on these routers. I'm going to go back to router 1 and I'm going to start configuring the IP address here. So I'll do interface fast ethernet 00 IPv6 address 2001:1111:AAAA:1:1 /64. That is our router 1. And I'm going to go ahead and mimic the same config on router 2. So interface fast00, IPv6 address 2001:1111:1:2/64 and do a no shut on this interface. And we should be able to ping router 2 from here. Now, before I do that, let's go ahead and look at the command do show IPv6 interface. And here you go, it's up. It automatically assigned itself the link local address. And here's our unicast address based on the diagram here. Looks good. We got all these multicast addresses that we talked about. And let's go ahead and take a look at do show IPv6 neighbor, see if our neighbor table has anything. No, it's blank right now. Let's go to router 2, do the same thing. Do show IPv6 interface, and sure enough, we're up and running. We have link local address and we have our unicast address. Now on router 1, let's go ahead and ping router 2. And the way we're going to do that is we're going to go ahead and copy and paste, and we're going to replace the last hex with 2. I have to type in the keyword do in front. And there you go. This was successful. Now let's go ahead and look at our neighbor table again. And sure enough, our neighbor table is built at this point. If you guys remember the neighbor solicitation and neighbor advertisement and router solicitation, router advertisement, that actually allowed us to go ahead and build our IPv6 neighbor table. So it's looking good. Let's go to router 2 and see if things look good as far as our neighbor table. And sure enough, we have both our link local address and our unicast address. The difference is link local is a must. We always have it. It's only significant on that local link. So the best way I can explain it is if you look at the link between R1 and R2 here on the diagram at the bottom, the link local address is only significant on this interface on each router that is pointing to the other router. That's it. Outside of this scope, that address has no existence. You cannot route it. There's nothing else you can do beyond the scope of these 2 links. You cannot advertise it to other routers. It only exists on this local link. Whereas the 2001 address, which is a global unicast address, that is internet routable. So our devices in the New York location can ping devices in the San Jose office using this global unicast address, assuming that it's a global unicast address assigned by our ISP and we have end-to-end connectivity. So with that, let's go back to router 1 and let's go ahead and start configuring our loopbacks. So I'm going to configure the first loopback, interface loopback 0, and I'm going to go IPv6 address 2001:1111:2:1/64. And then I'll go ahead and create the next loopback, loopback 1. So our loopback 1 address is, we need to go ahead and change 2 to 3. And then we'll do our loopback 2 address, and we'll change the 3 to 4 according to our diagram. Now let's go ahead and take a look at do show IPv6 interface brief to see if all of our addresses are configured. And sure enough, you see even the loopback addresses have a link local address on top of the global unicast address. Pretty interesting, huh? And now what we'll do is we'll go to router 2 and do the same thing. We'll do interface loopback 0, IPv6 address 2001:1111:5:1/64. I'll then create a loopback 1 address, change the 5 to 6. I'll create a loopback 2 and change the 6 to 7. And that should pretty much do it. So now let's go ahead and verify, make sure all of our loopbacks are configured the way we want it, everything to be configured. And sure enough, fast Ethernet is up, link local, global loopback is up. We have local, global address. It all looks beautiful. And we already verified connectivity by pinging our neighbor. Okay, so that's good. But we're not going to be able to ping the loopbacks because the loopbacks are one hop away. And for that, we need routing. And we have two different types of routing, static routing or dynamic routing. Well, we're going to go ahead and take advantage of static routing. On router 1, I'm going to go ahead and start configuring static routes to the loopback addresses of router 2 so I can reach them. The way you do that is in global config mode, you type in IPv6 route, and you go ahead and type in the route that you want to specify, and you also specify your next hop interface, plus what you need to do is we'll go to router 2 and grab its link local address, because this is a must. If you don't have that, then routing is not going to work. And that's it. So if the format is the same in IPv4, where you type in IP route, you type in the destination, and then you specify the next hop. Here in IPv6, the big difference is you also have to specify the interface. Okay? And we're going to do the same thing again for the other loopback with 6. And then we're going to do that one more time and do that for loopback 7. So at this point, we have all the routes set up. And if I were to do show IPv6 route, you'll get to see that all of these connected and local routes with the C flag and the L flag are automatically added by the router. And by the way, the one that ends in /128 is equivalent to a /32 in IPv4, which is what? A host route, right? So this /128 is how the IPv6 host route is specified. Now, that being said, here are all the static routes we just configured with the S flag in front of them. By the way, in these brackets, the value to the left of the slash is called admin distance or administrative distance. And the value to the right of the slash is the metric. Keep that in mind. It's the same logic, whether it's IPv4 or IPv6. And the reason it's 1 here is because I'm using static routing. If it was dynamic routing, then it's going to be the admin distance for that routing protocol. Okay, so we're done on router 1. Let's go ahead and be a little lazy, I suppose, and set up IPv6 route. And we'll set up a default route here. And we'll specify the next hop interface. And one more thing we need to do is go ahead and grab the show IPv6 interface and grab the link local address of router 1 and add that as the next hop. And that should be it. If I were to look at do show IPv6 route, boom, here it is. It's a static default route. It's the equivalent of a 0.0.0.0 route in IPv4. But you see, this is much simpler than IPv4. That's why I love IPv6 at times, because it's simpler than IPv4. And what we're going to do now is go to router 1 and ping. Let's go ahead and ping all these loopbacks and see if you're able to reach them. Sure enough, I can ping loopback 0. Let's try loopback 1. I can go to loopback 1, and I can also get to loopback 7. That is wonderful news. Now let's go to R2 and see if we can ping all the loopbacks on R1. Sure enough, I can do that. Let's try loopback 1. I can do that. Let's try loopback 4. I can do that. And that concludes our lab. Welcome to CCNA 200-301 course. Today, I'm going to cover section 4, part 1 of the CCNA exam, IP services. In particular, we're going to cover IP service galore. Here are the topics I plan on covering today. First, FHRP. Second, DHCP. Third, DNS. Finally, I'll wrap it up with device management protocols such as NTP, SNMP, Syslog, SSH, and TFTP/FTP. Let's go. Let's first discuss FHRP. Before we understand what that is, let's quickly take a look at the network architecture and design, because that will help us understand the value of having redundant default gateways. Now, as you can clearly see in our current design, whether we look at the branch site that is at the bottom of the screen or the data center top right of the screen, we have no network edge redundancy. And when I say network edge, it's basically the customer edge router located either at the branch site or the data center. That's what constitutes the edge of the network. Now, in this instance, what's happening is, let's look at the branch site. If that PC wants to talk to the data center server up at the top, there's only one default gateway that it can go through. And if that default gateway goes down, our entire network is hosed. Same thing with the IP phone. It's only got a single default gateway. Return traffic from the data center back to the branch, there's only a single default gateway. When it comes to network, a lack of redundancy is a cardinal sin. You cannot afford to build your network without redundancy. You must account for redundancy. Unless there is a financial reason for not being able to create a network that is fully redundant, that is understandable, but you must let your business owners know the risks involved if they're not letting you design your network correctly. Now, that said, let's talk about a couple of issues with this design. Here are all the single points of failure in this design. Core switch 1, if that goes down, everything goes down. Link between the core switch 1 and branch customer edge 1, that goes down, everything is down. If that router at the edge goes down, absolutely we're down. If that circuit that we have plugged into the customer edge goes down, we're hosed. Moving up the chain, at the data center, default gateway circuit goes down, we're done. Data center's customer edge 1 goes down, we're done. If the link between core switch 1 and CE1 goes down, we're done. And if the core switch 1 melts and blows up, our network goes down. The whole name of the game when it comes to redundancy in networking is eliminating these single points of failure in our network. And that's exactly what I'm going to talk about. So I'm going to keep building on this next. So before we had no network redundancy, now we're looking slightly better. Starting off at the branch, what you will see differently here is that we got redundant circuits plugged into our default gateway. We still have a single default gateway box, but we have redundant circuits coming in now. So if one circuit goes down, our traffic can still continue going through the secondary link. Now at the data center, things are looking much better. Not only we have redundant circuits coming in, we now actually have redundant customer edge routers. That is excellent. And they're also plugged in redundantly into the core switches. So for all intents and purposes, we no longer have any points of failure in the data center. But in the branch, we still have a few single points of failure, and let me point those out for you. Core switch 1 is still a single point of failure. Link between core switch 1 and CE1 is still a single point of failure. And finally, the edge router in the branch is still a single point of failure. But as you can see, by adding redundancy in the data center and also bringing in redundant circuits into the branch, we have essentially reduced our exposure and created a better environment. Let's see if we can still do better than this. Here we have a fully redundant network. As you can see, we don't have any single point of failure. We got in the branch, we have redundant circuits coming in. We got redundant routers plugged into redundant core switches. Same thing happening in the data center. Redundant circuits, redundant routers, redundant core switches. It all looks great at this point. But we still have a problem. We have a single default gateway. Why is that? Well, the host operating system, whether you have Mac or Windows, what you have is on that device, under the IP configuration, you can only specify a single default gateway. And that's what creates this unique challenge for us. Because we cannot program redundant gateways on our host operating system, we have to figure out a way to get creative and allow the network to provide that type of redundancy to our end hosts or to our endpoints. What we can do though is we can get around this problem by configuring all hosts to point to the primary default gateway. When the primary default gateway fails, we can manually configure all hosts to the secondary gateway. And when the primary default gateway comes back online, we can go ahead and manually change all the hosts and point to the primary default gateway. Well, I don't know about you, but to me, that is extremely painful, especially if you have dozens of users or hundreds of users in your environment. That is not practical. Unless you're getting paid per manual entry, I would never do that, ever. And what's the solution? Well, the best solution is automation. And that's where FHRP comes into the picture. So now let's talk through what FHRP is. Stands for First Hop Redundancy Protocol. Why is it called First Hop Redundancy Protocol? Well, think about it. In our network, we have these switches are in a layer 2 domain. Whether in the branch or the data center, these switches are in a layer 2 domain. The first layer 3 hop in our network starts at these routers. That's the first layer 3 hop. Hence the name First Hop Redundancy Protocol. The primary purpose of FHRP is to provide default gateway redundancy. As I alluded to on the previous slide, by default, we only have a single default gateway. When we run FHRP, it allows us to alleviate this problem and rectify this issue. And it essentially makes default gateway failover automatic for us. Now, let me logically explain to you step by step how First Hop Redundancy Protocol works. Now, this is a conceptual understanding. So bear with me here. I'm not going to show you the configuration piece. I'm just going to logically show you the steps so you understand how that works. And then after we're done with that, I'll then jump on a CLI and show you how to configure FHRP on a command line. Now, what we're doing here, in order to explain this step by step, we're going to zoom into a branch site that has redundant default gateways. So the first step is that FHRP assigns what's called a VIP, a virtual IP, and it also assigns a corresponding VMAC or virtual MAC to the default gateway routers. Now, what does that mean? So if you guys remember, the problem is on this device right here, I can only have one default gateway. That's all my operating system allows me to do. So how do I allow a single default gateway to point to redundant devices? That's where FHRP comes in. So we take these two devices and we kind of combine them, so to speak, and we create a single VIP, virtual IP, and a single VMAC, a virtual MAC address. And the binding of the two is what FHRP does for us. And this fools the operating system into believing, these endpoints believe that they actually have access to only a single default gateway, but in reality, they actually have access to more than one default gateway. You can actually have more than two if you wanted to, but in most of the networks, you only have two default gateways. Endpoints, which in our case is a PC and IP phone, get their IP and default gateway from the DHCP server. So another thing that's not in this picture here is at work, in real world, of course, we'll have a DHCP server that serves all the clients that are in our environment. Instead of manually assigning all the IPs, we have a DHCP server and that pushes the configuration down. Endpoints populate their ARP table with this virtual IP and virtual MAC address. When the primary default gateway fails, the secondary takes over. Nothing changes on the endpoints though, because their ARP entries remain the same because it's all virtual IP and virtual MAC. So even if the primary default gateway went away, that's okay, because remember, we did some virtual magic with the IP and default gateway, and that's what allows us to keep ARP entries intact. However, the switches must update their MAC table from the primary default gateway to the secondary default gateway. This is done via gratuitous ARP. So if you guys remember, ARP, what is ARP? ARP is where you have an IP address of the other machine, but you don't have the MAC, but the network in the middle automatically figures out the MAC address for you. Gratuitous ARP is where you proactively update the MAC address table of the devices. And it's essentially an ARP reply for which we haven't received an ARP request. It's a broadcast, not a unicast. And gratuitous ARP is sent, as I alluded to earlier, proactively by the secondary default gateway to assist switches in updating their MAC address table. And when the primary default gateway comes back online, it doesn't automatically assume its previous role by default. However, we can change that behavior by making a change in our configuration. So at this point, this was just a conceptual level understanding. If it doesn't make a whole lot of sense to you right now, don't worry about it. I promise it will when I show you on the CLI how it all works. Now, there are three flavors of first hop redundancy protocol. The first one I want to talk about is HSRP version 2. It's Cisco proprietary. It uses the redundancy type of active and standby. Load balancing is done per subnet. Default priority is 100. It uses a multicast address of 224.0.0.102. And the default hello timer is 3 seconds. And it uses communication port number. For IPv4, it uses UDP 1985. And for IPv6, it uses UDP 2029. Moving on to VRRP, Virtual Router Redundancy Protocol. It's defined in RFC 5798, so it's industry standard. So if you had a Cisco device and a Juniper device, you can set up a VRRP and they will be able to communicate with each other and form FHRP. It operates in active standby similar to HSRP. Load balancing is per subnet. Default priority is 100. Multicast address is 224.0.0.18. Hello timer is better. It's 1 second. And communication port, in this case, it doesn't use a TCP port or a UDP port. Instead, it uses IP protocol 112. And finally, we have GLBP or Gateway Load Balancing Protocol. This one is also Cisco proprietary, similar to HSRP. However, the biggest difference with this one is the redundancy type is active-active. Load balancing is done per host instead of per subnet. Default priority is the same as the rest, 100. Multicast here is 224.0.0.102, same as HSRP. And hello timer is 3 seconds, same as HSRP, it's default. By the way, these timers can be changed, and we'll discuss that. And the communication port that it uses is UDP port 3222. Now let's quickly zoom in to HSRP. Stands for Hot Standby Router Protocol. Cisco proprietary, as I alluded to earlier. It allows multiple routers to appear as one by assigning a virtual IP and a matching MAC address. HSRP elects one active router to support data traffic from the endpoints at any given point in time, while the standby routers wait for the active router to fail. So what that means is, let's say if you had 4 routers that are participating in HSRP, only one could be active at any given point in time. The rest will be in standby mode, waiting for the active to go away. There are 2 versions of HSRP, version 1 and version 2. Now, version 2 is better and enhanced compared to version 1. And one thing that I want to let you know is these versions are not backwards compatible. So if you're in version 2, then make sure all the devices that are participating in that HSRP group are part of the same version. Otherwise, you're going to have stability issues and your HSRP is not going to work. HSRP version 2 communicates via multicast address 224.0.0.102 over UDP port 1985. It uses hello packets to talk to other HSRP-enabled routers. Default hello timer is 3 seconds and the hold time is 10 seconds. Typically, the hold time is 3 times the default hello. And if you want to do HSRP load balancing, it can be achieved. You actually have to create multiple HSRP groups. Now, if this last point doesn't make a lot of sense to you right now, it will as I continue building on this. So we'll quickly jump on a CLI to do this configuration. And what I'll show you on the CLI is Bob's PC and Customer Edge 1 and Customer Edge 2 routers. And we'll go ahead and configure HSRP on our devices on CE1 and CE2 to show you how that impacts Bob. So the first thing we're going to do when we do our configuration is we're going to assign HSRP group and virtual IP and then mirror the config on both default gateway routers. We'll then assign CE1 higher priority so it becomes active and CE2 becomes standby, and we'll also zoom into the HSRP group assignment. Now, if you see the virtual IP address on the screen here, it's 10.1.1.254. And the virtual MAC address in our case is 0000.0C9F.F001. Now, where does that come from? This is the default virtual MAC address on all the devices that use HSRP version 2. And as you can see, I've kind of given you a breakdown of how it looks. So all the elements in red, that signifies the Cisco vendor ID. 9F.F is the HSRP ID. And then the last portion, 001 in green, is the standby group number. Now, the standby group number changes based on the group that you choose. In our example here, we're going to choose group number 1, so it's going to match exactly what you see here. But if you were using group 2, then the last digit of the MAC address will switch to 002 instead of 1, and so on and so forth. Now that said, let's jump on CLI. So here I am on the CLI. One thing I want to show you on Bob's PC, if I do ipconfig/all, you'll clearly see that on Bob's PC, the IPv4 address is 10.1.1.99. The subnet mask is /24, and here's the default gateway, 10.1.1.254. Now let's jump to CE1 and go ahead and configure our HSRP configuration. So if you recall, the first thing we're going to do is we're going to go to Fast Ethernet 00, and the HSRP configuration is done inside of the interface. So it's an interface level configuration. The first command we type in here is standby version 2. So that defines version 2 of HSRP for us. The next command we type in is standby 1, and this number 1 signifies the group number. And after that, we're going to type in our virtual IP that we want to specify. And what we want to do next is standby 1 priority 254. And finally, we want to type in standby 1 preempt. And what that does for us is preempt ensures that when this router goes down and comes back online, it will assume its role as the king of the hill, if you will. And the priority command, the higher the number, the better the priority. So priority is important because that's how you select or elect an active router versus a standby. So at this time on CE1, we're good to go. And let's go ahead and look at our configuration here. So we'll do show standby brief. And what you see here is that on a Fast Ethernet 00, we belong to group 1. Our priority is 254. We are currently the active router. State is active. Active is local, which means us. We're local. Standby is unknown because we don't have the standby, the secondary router configured yet. And our virtual IP is 10.1.1.254. So let's go ahead and write our configuration on CE1. Now let's jump on to CE2 and quickly get this bad boy configured. So we'll do standby version 2, and we'll do standby 1 IP 10.1.1.254. And just like that, I now have HSRP configured on CE2. And let's quickly look at show standby brief. And let's take a look at that. And as you can see right now, our router on interface Fast Ethernet 0/0, we belong to group 1, priority of 100, which is the default priority. We're in the state of speak. However, we went from speak to standby, which is good because we want CE2 to be standby, secondary, right? Active guy is 10.1.1.252. That is CE1, as you can see here in the diagram below. And standby is unknown right now because I typed in this command before the status change. So we'll redo this command and you'll see this is going to change. And the virtual IP is the IP defined in this diagram here. Now let's go ahead and type in this command again. And as you can see, standby is local, which means we're the standby device right now. And now let's go back to CE1 and see how that looks. And sure enough, now CE1 shows that router 2, CE2, is the standby. Now that said, let's go to Bob and do a continuous ping, and we'll do a ping to 109.10.1.99, which happens to be, as you can see on this diagram here, some public IP address that we're pinging. So this right here is a testament that our connectivity is working end-to-end because Bob is able to access this public IP on the internet. Now that said, let's go ahead and simulate an outage and bring down CE1, because I want to show how Bob's traffic will automatically switch over to the secondary router. Bob's traffic is currently going through CE1 to get to this 109 public IP, but when CE1 goes down, it should automatically redirect traffic over CE2 to access the public IP. So let's go ahead and do that. And also keep an eye on Bob's PC to the left. The continuous ping is going fine. So we're going to go to interface fast Ethernet 00 on CE1 and simulate an outage by typing in a shut command. Now, watch what happened on Bob's PC. As you can see, we missed a couple of pings, which means we lost a couple of packets as we switched. Now, it's not too bad, but we still lost a couple of packets. We can tweak timers to make that better for us. But in this example, to keep things simple, I'm going to go ahead and continue rolling. Now let's go ahead and bring that interface back up. And if you guys remember, we have a preempt command, which means our primary router should automatically assume its primary role momentarily here. And as you can see, Bob's PC is struggling. It's able to send a packet, and then it loses a packet, and then it sends a packet again and loses a packet. This is all due to reconvergence that the network is currently experiencing because of the failures that we just had. So as you can see, we still are dealing with convergence issues. And finally, Bob is good to go now, because now the traffic is once again going through CE1 as primary. And as you can see, we lost a ton of packets when that happened. In reality, we would want to tweak these timers down to make the convergence faster. Here's a reference to the commands I typed on these routers. You can keep this in your back pocket as you try to replicate this in your lab. Now, a couple of additional pointers. Priority, like I said, in HSRP, election of an active and standby. HSRP router is based on priority. Priority can be defined within the range of 1 through 255. Default priority is 100. Next, preempt. Once again, when this option is enabled on the active HSRP router, when it comes back online, it assumes its primary role. And if you don't have that configured, then if the primary device went down and it came back online, it will never assume its primary role. It will always stay secondary. And finally, timers. Default timers can be changed from seconds to milliseconds, as I alluded to earlier. And one quick tip is we can create another HSRP group for load balancing by creating a VLAN and subnet. Now let me explain what I mean by that. So this is for you to do in your lab environment. And if you run into any issues, feel free to share your thoughts in the comments below. You see, when we have multiple workstations, so we got Bob up here and we got Dan at the bottom here. If we don't do load balancing, both Dan and Bob will always go through this guy, the CE1. And then the traffic will go down this way. Now, it's okay if it's just two PCs, Bob and Dan, but imagine if you had hundreds of PCs on the blue VLAN and hundreds of PCs on the red VLAN. You wouldn't want all of them to go through a single network point, because then your CE1 will become a choking point. So in an ideal world, what you would want to do instead is you would want Bob's traffic to always take this path at the top, and you would want Dan's traffic to always take the path at the bottom through CE2 to access the wide area network. To do that, we're going to have to set up what's called traffic load balancing. And that's exactly what I'm showing here. In this case, what I'm showing is that Bob's PC has this IP, this is the default gateway it's using, the LAN subnet that it's part of, /24, and then the HSRP configuration that you would have to do on CE1 and CE2, respectively, as shown on the screen. And what you would want to do is create sub-interfaces on CE1 and CE2. And these links between CE1 and the switch and CE2 and the switch, the reason they're purple is because they're carrying multiple VLANs. They're carrying the red VLAN and they're carrying the blue VLAN. And when you combine red and blue, you get purple. You see what I did there? Pretty clever, huh? Now what we'll do is we'll make CE1 active HSRP router for blue VLAN and subnet via high priority. And the HSRP virtual IP that we'll configure here is 10.1.1.254. And what we'll do next is we'll set up another subnet completely separate from Bob's, and it's going to be 10.1.2.0/24, and you can see all the configuration here. We'll create separate sub-interfaces on CE1, CE2, create different groups, and configure them accordingly. And as you can see, what we're doing is we're basically making the CE1 active for blue VLAN, standby for the red VLAN, and we're making CE2 active for the red VLAN, standby for the blue VLAN. And that's pretty much it. Now, in the interest of time here, I'm going to skip the configuration part. But like I said, if you are configuring this in a lab and are running into issues, feel free to drop your thoughts in the comments below. Now let's quickly shift gear to DHCP. DHCP stands for Dynamic Host Configuration Protocol. The whole reason we have DHCP is it automatically assigns IP addresses to endpoints connected to the wired or wireless network. I don't know about you, but I don't like doing anything manually, right? And especially if you have a ton of workstations and IP phones and wireless devices, it's insanity to manually assign anything. That's where DHCP comes in. As soon as you have those devices come and join the network, they get plugged in or connect wirelessly, they automatically get their IP information. Now, DHCP server automatically provides the following information to each DHCP client, whether it's a laptop, a desktop, wired, wireless, IP phone, regardless. This is the information each device gets. Gets an IP address, gets a subnet mask, gets a default gateway IP address, which we just finished talking about. Typically, that's our first hop redundancy protocol virtual IP. We just talked about it, so it's very timely. And it also provides DNS server IP addresses. Typically, you would have redundant IP addresses. And here's how it looks. So I took a snapshot of my laptop here, and as you can see here, it's configured via DHCP. It's picking up its IP automatically, subnet mask. The router in this case is the default gateway that we just talked about, right? Which is a virtual IP. And the DNS server in this case is the Google DNS servers that are specified. These are Google public DNS servers, to be exact. Now, here are some DHCP server features that we can configure when we're on the DHCP server. We can define an address pool. So that is basically a subnet, which is a range of IPs. On the DHCP server, we can define reserved addresses. So basically, this is a list of excluded IPs. And I'll show you on the CLI how that works. Address binding. We can also do that on the server, meaning we can have what's called a MAC reservation, meaning a manually defined IP address MAC to a MAC address. Now, why in the world would you want to do that? So think about it. Like at home, for example, for me, I have address binding set up for my network attached storage or NAS server, and I've also got an IP printer. I've got a network printer that I print to. And I've also done the same thing. I have a MAC address reserved for my printer. And this ensures that the IP address never changes. No matter how many times I reboot those devices, they always get the same IP address. Why is that important? Well, the rest of the devices in the network that need access to these services, like the NAS server or the printer that I have, they point to those devices. And as long as the IP address doesn't change, they can always continue pointing to those devices. And another thing we can configure on the DHCP server is what's called a lease time. Now, whenever you get an IP address from a DHCP server, it's leased to you as the client, meaning you're not handed that IP address for eternity. There's a certain expiration date on that IP address after which it just goes away. But if we needed to keep that IP, we can renew the lease. And by the way, this is not an exhaustive list of features on the DHCP server we can configure. This is just a very small yet important feature list that I wanted to share with you. Now let's quickly look at how DHCP works and the DORA process. So here's Bob. He has a laptop. He physically connects to the switch, and we've got a server that's also plugged into the same switch. So how does Bob's PC or laptop gets an automatic IP address from the DHCP server? So first, what happens is Bob's PC sends what's called a discover broadcast, and it's sent to the DHCP server through the switch, which switch basically forwards as all Fs when it comes to the MAC address at layer 2. And we all know what all Fs at layer 2 means. It's a layer 2 broadcast. All the devices will get it. Only the device that understands that packet uses it, everybody else drops it. Now in this case, DHCP server gets that discover request, and it's able to determine that it's intended for the DHCP server because it's coming from the source of all zeros. The DHCP server then responds back with an offer to Bob, and the reason DHCP server is able to respond back to Bob and not any other PC is because it's got the MAC address in the initial discover. So it responds back to that MAC with an offer, and inside of that offer, and if you were to zoom into that offer packet, what we'll see is an IP address and a lease time. Bob gets it. Bob then sends a request to the DHCP server saying, I like your offer and I would like to accept your offer, and here's my request. Finally, the DHCP server responds back with an acknowledgement leasing that IP to Bob, and now Bob is good to go. And this is where the acronym DORA comes in. Discover, Offer, Request, Acknowledgement. It's the first letter in all of these different packet types. If you combine that together, that's called DORA. So that's the easiest way to remember from an exam perspective, because this could very well be an exam question. Now, by default, what ends up happening is Bob is going to get an IP from the DHCP server, no problem, because switches can send broadcasts all day long as they're layer 2 switches, right? Well, what if we have a layer 3 device in the middle, like which we do in this case? Well, what do routers do when they get a broadcast? Routers hate broadcast. They drop it. So the router is going to drop that broadcast, and if Leah down below wanted to get an IP address from the DHCP server, the packets will never make it through. The packets will always get dropped right here. As soon as the packets are received at this interface on the router, they'll get dropped. So how do we fix that problem? This is where DHCP relay agent comes in. So what we do is we set up a DHCP relay agent on this interface pointing toward the DHCP clients. And when the DHCP clients respond or send a discover broadcast, that discover broadcast is received on this interface, and it's transparently then passed along to the rest of the network until it gets to the DHCP server. And the DHCP server consequently is then able to respond back to that device that sent the initial request for the IP address. And that's how DHCP relay agent works. And at this step, what I would like to do is quickly jump on CLI and configure DHCP so you get some hands-on experience. And I'll keep it very simple here. As you can see, we have Bob to the left. The LAN subnet there is 10.0.0.0/24. And to the right of CE1, we got the DHCP server. And the subnet here is 192.168.0.0/24. And a couple of things I want to talk to you about is first the DHCP server config overview. So what we'll do from a high level perspective is we'll specify excluded addresses first. And I'll tell you why we need excluded addresses once I'm on CLI. We'll then define a DHCP IP pool. We'll specify a network, we'll specify a default gateway, and we'll specify DNS servers. This is the server-side configuration. Once that's done, then our client is going to be able to pull the configuration that we have defined on the server. Now, the DHCP relay agent config is very simple. What we'll do is this interface right here that is pointing to Bob, we'll go ahead and specify what's called an IP helper address, which points to the DHCP server, which would be 192.168.0.2. And with that, CE1 is going to be able to take that broadcast from Bob and being able to pass it along to the DHCP server and vice versa. Now at this point, let's go ahead and jump on CLI. Now I've got a pretty interesting lab here for you. All of these devices that you see are actually Cisco routers. For lab purposes, I decided to show you how you configure a Cisco router as a server, DHCP server to be exact. How do you configure a Cisco router to be a DHCP relay agent, and how you can set up a DHCP router to actually be a DHCP client. I thought that would be interesting for you to see, but in reality, in a production environment, most likely would have a dedicated DHCP appliance and a dedicated DNS appliance that provides that functionality to you. But for lab purposes, in understanding the mechanics, this will do fine. So let's go ahead and configure our DHCP server here. So here I am on the DHCP server. I'm going to go to global configuration mode. And the first thing I want to do is I want to go ahead and exclude the range of IPs that potentially might be allocated to devices. So for example, 10.0.0.0/24 network has this .1 allocated to the router. Now that would have to be excluded because CE1 shouldn't be getting any IPs from the DHCP server. These are the IPs that we want to manually assign for a good reason, and that is you don't assign your critical network infrastructure elements automatic DHCP IPs. You want to manually assign IPs so you can route properly and define your access control lists and things of that nature. Whereas your workstations and your laptops and desktops and wired devices and wireless devices and IP phones, all those should get IP addresses automatically. So let's go ahead and define the exclusion first. So IP DHCP excluded address, we'll say 10.0.0.1, and we'll end the range with 10.0.0.20. Now, you can define a much larger range if you wanted to, but for my purpose, 20 is a good number. You can also define another excluded address range on top of the one that I've defined. Let's say if I had another range that was not contiguous, let's say another range was 10.0.0.100 through 120, and this way I'll have an additional range of excluded addresses. But in this instance, this should do fine. Now let's go ahead and define our IP DHCP pool. And basically pool, as the name suggests, is a range of IP addresses that are defined. In this case, within the DHCP pool, we define different DHCP parameters. We'll first start off with the network parameter. We'll say 10.0.0.0/24. As you can see in the diagram below, because that's the network that we want to define for our workstations. What you want to do next is you want to do default -router 10.0.0.1, which is this interface right here, the fast Ethernet 00 on CE1. You want to define that. That will actually be the default gateway IP. And if you guys recall, we just finished our discussion on first hop redundancy protocol. This should be a virtual IP of your FHRP. That's what you would want to define here for redundancy purposes. And finally, we'll define our DNS servers. And what we'll do is we'll say 192.168.0.2. Let's assume our DHCP server is also a DNS server. In reality, that's not going to be the case. You're probably going to have, like I said, a dedicated appliance, or you might actually even have public DNS servers. And let's assume we have another redundant DNS server. Once again, this is a good practice to have redundant DNS servers specified. And at this point, my DHCP server should be good to go. And let's quickly look at a couple of show commands. Show IP DHCP pool. So this shows us that you have a pool called workstations defined. And right now, we are not utilizing anything. Our utilization is 0 right now. And the total addresses that can be handed out is 254, which makes sense because if you guys remember, the first IP in the range is called a network address, which ends in .0. That cannot be assigned. And the last address, which ends in .255, that is called a broadcast address, and that can also not be assigned because those are reserved addresses. Hence, we can only assign 254 addresses. Currently, we don't have any leased and all that, and that's pretty much it. So our DHCP server is good to go. Now let's jump on to Bob. As we'll go to global configuration mode, go to fast Ethernet 00, and we'll say IP address DHCP. So at this point, Bob should be able to automatically pull an IP address from the DHCP server. Now let's go ahead and look at that. Show IP interface brief. And we don't have an IP address assigned to us yet. Well, the reason is CE1 needs to be set up as a DHCP relay agent, and we haven't done that yet. So if you guys recall, we go to global config mode, we go to fast Ethernet 00, and on this interface, we're going to define our IP helper address. So we'll do IP helper address, and we'll type in 192.168. We'll point to the DHCP server. And that should be it for our DHCP relay agent at this point. Let's go back to Bob, and Bob should be getting an IP address pretty soon. And here it is. Sure enough, Bob was assigned an IP address of 10.0.0.21/24. And let's go ahead and do show IP interface brief. And sure enough, looks good. Let's look at show interface fast Ethernet 00 so we can see more details here. And as you can see, we have an IP address defined with a subnet mask of /24. Now let's quickly take a look at the DHCP server and see how things are looking. So we'll type in show IP DHCP pool. And as you can see here, it says that it has leased one IP address. Now let's go back to the DHCP server and look at show IP DHCP binding. This command shows us the IP address that has been leased out to Bob, and it also shows the client ID right next to it. And another very important aspect here is the lease expiration that's attached to it. Now, the time is a bit off on this device. This is like the default clock. That's another aspect that I will cover later today, where we'll set up an NTP server to fix the clock on our local device. Now let's shift our attention to DNS. I'll quickly give you a walkthrough of DNS. DNS stands for Domain Name System. It operates on the principle of a client-server model. DNS server provides a name resolution to network endpoints. What that means is DNS translates a host name or a URL, which stands for Uniform Resource Locator, to a corresponding IP address. So, in other words, the whole reason DNS was designed was, as human beings, we're good with remembering names rather than an IP address. For example, instead of going to www.google.com, if you were to type in an IP address, it's nearly impossible that you're going to remember all these IP addresses for different websites. It's a lot easier to go, when I go to Facebook or Amazon or Twitter or whatever. As human beings, that's how our brains are wired. It's a lot easier for us to remember names than numbers. And this is where DNS comes in. DNS takes the host names that we can easily remember as human beings and automatically on the back end correspond to the appropriate IP address and display the resource that we're trying to access. As a best practice, configure redundant DNS servers for high availability or HA. Here are some of the most popular public DNS servers in the world. My personal favorite is Cloudflare. It's actually a pair of DNS servers. Primary is 1.1.1.1 and secondary is 1.0.0.1. They claim to be the fastest DNS servers on planet Earth, and I have found that to be true. Now, next up is Cisco OpenDNS. You have the addresses right in front of you. That's a company Cisco had acquired a couple of years ago called OpenDNS, and it's now become part of Cisco umbrella. And the IP addresses that you're looking at are publicly available for anyone to use, and they provide security services on top of DNS with malware protection and all that. So it's pretty interesting if you're interested in security features instead of just a plain vanilla DNS service. And another very popular public DNS service that a lot of people use is Google public DNS servers, 8.8.8.8 and 8.8.4.4. They're also really fast, but I've noticed Cloudflare is in its own league altogether, just absolutely earth-shatteringly fast. Now let's quickly discuss what is DNS and how it works. So we talked about what DNS is. Now let's talk about how it works. So we have Bob, and his PC has an IP address of 20.1.1.1, and there's a DNS server on the internet that has a public IP of 40.1.1.1. Now step one is Bob sends a DNS name resolution request. So let's say Bob opens up a browser and goes to www.cisco.com. That's what we call a DNS request. Now, next thing that happens is the source port on Bob's PC, it's also called a private port from a private range of ports, is automatically allocated. Let's say in this case 49.799. And the destination port, because DNS runs over port UDP 53, is 53 because that's the destination. And the source IP in Bob's case is 20.1.1.1, and the destination IP of the DNS server is 40.1.1.1. Now, a couple of things I want to bring to your attention is, like I said, this at the top is considered a DNS request. The source port and the destination port combined, this is your transport or layer 4, and the source IP and the destination IP combined, this is your layer 3 header. And the information makes its way to the DNS server. The DNS server then responds back to the name resolution reply, and it says the IP address of cisco.com is 80.1.1.1. The source port is its own port. The destination port is the previous port defined by Bob, and the source IP is DNS server's own IP, and the destination IP is Bob's IP, of course. And the final step in the process is, at that point, Bob now knows how to communicate with Cisco.com web server at the bottom right of the screen, which happens to be at 80.1.1.1. And Bob starts talking directly to the web server. It no longer has to go and talk to the DNS server anymore because the DNS gave it what it really needed to be able to communicate with Cisco.com. And then we have the source port. Once again, it's going to be a randomly generated port. Destination port in this case is going to be port 80, which is for HTTP. Bob is going to form a TCP connection, a three-way handshake with the web server. And the source IP is going to be Bob's IP, destination IP is going to be Cisco.com's IP. By the way, this 80.1.1.1 is a fictitious IP. This is not the real Cisco.com IP, used for the purpose of this example. Now let's zoom out a little bit and see what the DNS server did for us that we looked at on the previous slide. So here's Bob again. So the step one is Bob types in Cisco.com in the browser. It goes to the internal DNS server, which for majority of the people, it's your ISP server, or it could be the public DNS server I talked about, like the Cloudflare or Cisco or Google. And that server will get your request. And once it gets that request, assuming it doesn't have an answer for it, if it does have that information in its cache, it will immediately respond back. By the way, taking a step back here, if your PC already knew how to get to Cisco.com and there was a cache in the browser, the PC won't even bother going to the DNS server. It will just automatically take you there. But this process happens because we don't have an entry in our local database on our machine. So our machine then goes to the DNS server to see if it's got that information. Now, assuming the public DNS that we're connecting to doesn't have that information either, then what ends up happening is it ends up going to a root level domain server. And it says, look, I got this request for Cisco.com. Do you know where that is? Well, the root level domain server, there's only few root level domain servers, by the way, around the globe. Some big universities actually maintain root level domain servers. There's a handful of them. The root level domain server says, well, I don't know the answer, but I do know the top level domain server who may know the answer to that. And the top level domain servers are .com, .org, .gov, .mil, .tv, etc. So because you're trying to get to Cisco.com, it says that I'm going to send you to the .com top level domain server. Now that server says, well, I don't know exactly where Cisco.com is either, but I do know second level domain server that knows exactly where it's hosted. And at that point, the second level domain server redirects the request to the authoritative server, the actual server where Cisco.com is hosted. And at that point, that server responds back directly to our public DNS server. And at that point, the public DNS server responds to us. By the way, this entire thing that we just looked at, which took me a couple of minutes to explain, this happens in a blink of an eye. It's super duper fast. By the way, this is also known as recursive DNS lookup. Recursive means the request is constantly redirected and it bounces around different hierarchy of servers until the traffic gets to the point where the actual DNS server responsible responds back to our public DNS server and we end up getting an answer for it. And that is DNS for you. Now let's quickly shift our attention to NTP. NTP stands for Network Time Protocol, and the primary purpose in life of NTP is to synchronize clocks on our network devices. And it uses UDP port 123. Now you may be asking a question, why NTP? Why do we need to use NTP to synchronize our clocks? Keeping time in sync on all network devices is very important. In particular, it's important to be able to look at logs on our devices that represent different events that happened, like an interface going down or device rebooting, things of that nature. We need to be able to do the interpretation and analysis of our logs. And NTP allows us to have an accurate time with appropriate timestamps on our log messages. And that helps us do what's called event correlation, where we get to look at all the different events that happened on our device versus some of the other devices on our network, and figure out what actually transpired that caused a certain outage, for example, on our network. Another reason NTP is important is for the use of digital certificates. And if you have ever looked at a digital certificate, there's a very important field embedded within a digital certificate called expiration date. And without an accurate time, network devices may not function properly if you've got digital certificates handed out to your endpoints for security reasons, and it will wreak havoc on your network. So NTP, you must configure NTP to make sure things operate correctly on your network. And another use case for NTP could potentially be that if you have a security incident that happened in your environment where you think you were hacked, when you have synchronized timestamps, you can do what's called forensic analysis and do a hop-by-hop investigation of what actually transpired throughout the chain of events in your network that led to a certain security incident. And you also want to find out what kind of damage did the bad guys cause. And thanks to NTP, when the time is all synchronized across the board, you can see that a hacker came in via a WAN circuit on your router, and then from there they hopped onto a switch, and then from there they communicated with a particular server and maybe downloaded certain files or maybe uploaded some type of malware to your server through the NTP. And the timestamps, we can do that forensic analysis to see exactly what transpired. And finally, there's a concept within NTP called a stratum level. And stratum level number indicates a believability of the NTP server, or the NTP source, I should say. And it also indicates device's proximity to the reference clock. So there are some clocks globally that are used to provide very, very accurate time. And there are NTP servers on the internet that you can utilize to be able to configure your devices that have a very, very low stratum level. And stratum level 0 is considered the highest NTP stratum level, which means it's the most believable device. Whereas with the device with a stratum level of 15 means that's the lowest NTP stratum number, and that's the least believable device. When it gets to number 16, it's no longer believable. So something you have to keep in mind. Here's a list of different internet time servers on the internet. And this list right here is furnished by NIST, which stands for National Institute of Standards and Technology. And they maintain a list of servers that communicate with different time sources on the internet to be able to provide you with very, very accurate time. And they have both IPv4 and IPv6 servers specified on this list. I'll provide a link in the description of this video. And what we're going to do finally is we're going to do NTP configuration on our devices. And the way we're going to do this is, let me give you a quick walkthrough of this diagram. So the very first thing that's happening is we have these internet time servers that are being represented by time.nist.gov. Okay, so this is once again the list that I was showing you. And if you use this URL, time.nist.gov, this is a URL to NIST's load balancer, which means there's a bunch of servers right behind this URL. So you get to use their servers in a round-robin fashion. Instead of pointing to a specific NIST server, this gives you the ability to be able to point to a whole bunch of servers that NIST maintains, and you have the ability to do that in a round-robin fashion. So it's good for high availability reasons. Here we have R1. So within our corporation, this is our edge router. We'll make that an NTP master. NTP master is a device that is supposed to have a highest stratum level within your environment. And then R2 in our network will make that an NTP server. Another important aspect that I want to bring to your attention is you see this IP here, loopback 10.0.0.1/32. The reason I have this loopback here on R1 is because all the NTP servers in our environment that would want to learn and synchronize their clock with the NTP master, it's ideal to provide loopback interface instead of providing a physical interface, because what if I had multiple redundant links? So if this was fast 0 below and the one above was fast 1, I don't want to tie my configuration to the physical interface. It's better to provide a loopback interface which never goes down, regardless of what's happening with the physical paths or the physical links on this network. Our loopback interface will always be up. So this is considered a best practice. Now let's quickly look at some of the steps that we'll be taking to configure our devices. Here's how we'll be configuring our devices. First, we're going to specify the time and the time zone locally. So on R1, we're going to say clock time zone, PDT for Pacific time zone with daylight savings, -7. We're going to then say clock summertime PDT recurring to specify we're currently observing daylight savings time. And finally, we're going to specify the exact time on our device. So we'll say clock set 1300, meaning 1 p.m., 27 June 2021. We'll then do a basic NTP configuration. We'll specify our name server, which in this case is the Cloudflare DNS server on the internet. We'll then specify the NTP server, which in our case would be time.nist.gov. We'll then turn our router 1 into NTP master, and we're going to specify the stratum level. We're going to say our stratum level is 2. And finally, on R2, what we're going to do is we're going to go ahead and set up an NTP server 10.0.0.1 to point to the loopback on R1. And that's pretty much the only thing that we're going to need to do on R2, besides, of course, setting our clock and time zone locally, because it helps to set up a time and time zone locally on all the devices that you want to participate in NTP. This way, they're getting a bit of a head start, and they're pretty close to being accurate, but not perfect. But once you do that and you specify the NTP server, your devices then start going to communicating via NTP protocol to start synchronizing itself with the NTP master. With that, let's jump on CLI and get the ball rolling. Here I am on R1. I'm going to go ahead and go to a global configuration mode, and I'm going to type in the command clock time zone PDT -7. I will then say clock summertime PDT recurring. And this will specify our daylight savings time. We'll then go to the privilege exec mode and type in clock set. I'm going to try to match the time locally here, 17:20, which is 5:20 p.m., 27 June 2021. And that should be it. If I were to do show clock now, I should be able to see that it says it's 5:20 p.m. on my device, and it's Sunday, June 27, 2021. So that's pretty cool. So now this gives our device a head start, and it's now ready to be able to synchronize itself with the time.nist.gov. Here's the next step. We need to go to global configuration mode to do our NTP configuration. So far, we only set clock on our device. Now let's go ahead and start setting up NTP. So we'll type in IP name server 1.1.1.1, which is the Cloudflare server on the internet, but feel free to use Cisco OpenDNS or Google public DNS servers or any other DNS server of your choice. And then after that, you type in NTP server and then the name or the URL of the server, which in our case is time.nist.gov. Now, I'm going to get an error message here, and the reason is I'm unable to translate because my device is actually not connected to the internet. I'm unable to contact the Cloudflare server on the internet. Instead, I'm going to go ahead and specify an IP address, and I'm just going to pretend that the time.nist.gov translates to 209.1.2.24. I just totally made that up, but you get the point. If you actually had your router connected to internet and you were able to communicate with the DNS server, then the URL that I typed in earlier, you're going to be able to translate and you're not going to get an error message. Reason I got an error message is because I'm not connected to the internet in this lab. Okay. What we want to do next is we want to go ahead and specify this device as the NTP master with the stratum number of 2. Now I could have chosen a stratum number of 1, but I did 2. This way, any other device in my network that wants to synchronize its time, it's going to know that I'm not the actual internet time server. Instead, I'm a device that's 1 or 2 hops away from the internet time server, which accurately represents what's happening here. And then finally, we're done. So we're going to go back to the exec privilege mode, type in WR, which is the same as copy running config to startup config. It's the same thing. Okay, when you type in WR, it accomplishes the same goal as copy running config to startup config. So at this point, we're secure. Our configuration has been written. Now what we need to do is we need to jump over to router 2. And on this device, we're going to specify an NTP server, which points to the NTP master. We're going to say NTP server 10.0.0.1. And that's it. We're also supposed to set up a clock, right? So let's go ahead and do that. We'll do clock time zone PDT -7. We'll then do clock summertime PDT recurring. That's good. We're going to go to privilege exec mode. We're going to type in clock set. At this point, we're at 17:28:00. And that should do it. If I were to do show clock, looks good. Let me go ahead and do copy running config to startup config. And that's looking good. So now we have both devices configured. Now, one thing that I need to do is I actually need to enable these interfaces, right? So let's go ahead and do that. Right now, our devices are basically plain vanilla config. So I'm going to go ahead and type in IP address 172.16.1.1, and I'll do 252, no shot. I'll go to the other device on router 2 and type in interface fast 00, IP address 172.16.1.2, 255.255.252, no shot. And that should bring up our interface, and that is good. We also need to create a loopback if you remember. So we'll do exit, we'll do interface, loopback 0, and we'll type in IP address 10.0.0.1, and we'll make that a host route, a /32. Okay, now let's go ahead and type in show IP interface brief. And I'm also going to write my configuration. At this point, our router 1 is configured properly. And let's go ahead and take a look at router 2. And it seems like it's also configured properly. We're going to write the config. We're going to do show IP interface brief just to make sure. Let's also try pinging the other device and make sure we can get to the other device. And sure enough, we can get there. So that's good. Now let's do show NTP status. That's a show command you want to run. As you can see, our clock right now is unsynchronized and our stratum is 16. So if you guys remember, as I alluded to earlier, when the stratum level is 16, that means it's unbelievable and no other device can learn NTP information from us. At this point, it may take upwards of 10 minutes to be able for the clocks to synchronize. I'm not going to sit there. Maybe we can come back and take a look at it at a later point, but should be good to go. I'll also do show NTP status on R1 to see what's going on here. Here it says our stratum level is 2 and we are indeed synchronized. So that is good. I like it. There's another command we can run here, show NTP associations, and that shows us who we are associated with, which happens to be the loopback on R1. And we can also look at show NTP status again to see if we have been able to synchronize. That hasn't happened yet. We're not going to sweat. We're going to wait on it and see what it does. Let's double check our clock. Our clock looks good. It's set to today. So that's excellent. That wraps up the NTP section. Now let's quickly take a look at SNMP. SNMP stands for Simple Network Management Protocol. SNMP is an application layer protocol, exists on OSI layer 7. It's used for managing and monitoring network devices in real time. It uses UDP port 161 and 162. There are 3 different versions of SNMP. There's SNMP version 1, SNMP version 2C. Finally, SNMP version 3 came along. SNMP version 2C and 3 are the most widely adopted versions globally. SNMP operates on the concept of client-server model. And the first component is the server. So SNMP Manager is a server. It can either run on a PC or a server, and it's responsible for running the NMS or Network Management System. Now, typically, you wouldn't want to run it on a PC. Typically, an SNMP Manager is properly set up and installed on a dedicated piece of appliance, on a dedicated piece of hardware server. Could be a virtual server too, but the bottom line is that it's a dedicated device for capturing SNMP traps and SNMP events. And finally, we have an SNMP agent. That's a client that runs on a network device being a router or a switch or a firewall. And that device is responsible for managing a list of database variables called Management Information Base or MIB. Now let's quickly talk through the different SNMP elements. So as I alluded to, switches and routers, they're considered SNMP agents and they run MIBs or Management Information Base on them. And you have the SNMP Manager, which is basically the SNMP server, also called NMS, Network Management System. And what you do is, if these endpoints, the SNMP agent proactively sends information or logs to the SNMP Manager or the NMS system, that's considered a trap. And UDP port 162 is utilized to do that. Whereas when the SNMP server requests as an SNMP information to be shared, that's considered polling. And it uses UDP port 161. You would monitor events like bandwidth usage on the device or a particular interface. You would look at CPU utilization, memory utilization. You look at disk consumption. You look at things like interface status, up or down. These are some minor examples of SNMP MIBs. Now, just to put things in perspective, a typical router could have thousands, upwards of 5,000 MIBs defined, and same thing goes for switches. So you have a lot of information that you can potentially pull and a lot of traps that you can send to the NMS system. Now let's go a little bit deeper into SNMP polling and traps and also speak to the SNMP security. As I alluded to, SNMP Manager or NMS, it polls the SNMP agent to obtain information. So the example is, as a user, I can sit on an NMS server or an SNMP server, and I can send what's called an SNMP GET request to see if a certain interface is up on a router. Now, conversely, SNMP agent can also initiate communication with NMS via sending a message called trap. So an example is a switch, which is considered an SNMP agent, can proactively send an alert to NMS about a certain interface that just went down. And finally, from an SNMP security perspective, the earlier versions of SNMP, version 1 and version 2C, used SNMP communities, which were clear text passwords. So there was actually no concept of security in version 1 at all. SNMP version 2C was a slight enhancement of version 1, but all it did was allowed authentication, but it was clear text password, so that's not good enough. And it used community strings, read-only and read-write community strings for these two versions. As a best practice, when you have SNMP configured, what you want to do on your endpoints, like your SNMP agents, like routers and switches and firewalls, is you set up what IPv4 and IPv6 access control lists, or ACLs. And the whole reason you would want to do that is to define the NMS hosts or the SNMP servers, so your devices know exactly who the servers are and who they need to trust in order to be able to communicate and provide information. Because the last thing you want is some random rogue host on your network doing SNMP polling on your devices. That's not a good place to be. And SNMP version 3 was the first version that introduced the concept of message integrity, authentication, and encryption. So it's a full package when it comes to utilizing security. You should always, always, always be using SNMP version 3 when configuring your network. Now, let's quickly look at Syslog. Syslog is a logging protocol that allows network devices to generate messages for events and status changes on the local device. Local device being router, switch, firewall. These syslog messages are generated and stored locally on a network device. However, you can also choose to send these messages to a centralized syslog server. That is actually a preferred mechanism of storing syslog messages. Syslog uses UDP port 514. Now, at this point, you might be thinking that it's a bit confusing. We just talked about SNMP, which is designed to capture monitoring information, yet we have another protocol that does the same thing. What's the difference? Well, there are two big differences between the two. Syslog's primary use case is to analyze historical data. Okay, so an event has already occurred and now you want to look at it. So it's good for forensic analysis, so to speak, after the fact, right? So that's more of a reactive measure. Whereas SNMP provides real-time visibility, so you can actually see what's happening on the device at any given point in time. And you can also push configuration changes. Now, even though SNMP was designed initially with configuration in mind, but in reality, that actually never caught on. So in real world, you would not really see SNMP being used for pushing configuration changes. And if you're aware of the whole SDN realm, software-defined networking, which we'll talk a lot more about later in the course, SDN is now responsible for actually pushing configs and things like that to our routers and switches and firewalls. And we'll talk about that later. Second big difference. Syslog is a push-only mechanism, meaning it's a one-directional thing, meaning a device creates a log and it pushes it to the syslog server. Whereas SNMP, the device can decide to actually send an SNMP trap to the NMS server, or the NMS system can pull information from the device using polling that we talked about earlier. So you see the differences? These are minute differences, but they add up to a lot when you understand the specific use case for each. Now there's another element of Syslog that we need to look at. Syslog has what are called severity levels. So the messages that we see on our devices have different severity levels that are specified, and that helps us understand the criticality of the message being seen on the device. So for example, the first two values, 0 and 1. 0 stands for emergencies. If the system is unstable, you're going to get severity value of 0. And severity value 1 is alerts, and it means immediate action is required. Severity level 2 means it's critical and you need to pay attention to it. Severity level 3 means some sort of error event has occurred. Severity level 4 means it's some sort of warning that you need to pay attention to. Severity level 5 means it's an unusual event, but it's not an error message. Severity level 6 means it's informational, it's a normal operational message, there's no action required on your end as an administrator. And finally, level 7 is debugging, and that's application debugging on your device, and it's initiated by the user. And typically it's used for if you're trying to debug, let's say, OSPF, or if you're trying to debug IP packets, you would want to initiate that debugging message locally so your device can start generating debug messages that you can then later analyze and figure out if your device is misbehaving or if your protocol is misbehaving. It may help you understand why that is actually happening. And one important tip that I want you to keep in mind is when you enable logging locally, you can select a severity level, and that automatically enables all other levels under that selected level. So let me give you an example. Let's say you specify severity level 5. That means you're going to be able to see all the messages 0 through 5, but you're not going to be able to see level 6 or level 7 messages. Let's jump on a command line so you can see that in more detail. Now, before we jump on the command line though, I want you to look at a couple of different commands here and understand the impact. So remember, we talked about the fact that syslog allows you to generate log messages. The first place where you can see the log messages is the console. So when you are consoled into the device via the console port, you can see the different logs on that device. For that, you type in logging console on your router or switch or firewall. Another element you can consider is if you want to allow users that are remotely connecting to this device, not via the console port, but rather via telnet or SSH, you can give them the ability to be able to see the logs. And to do that, you actually need to manually enable that via the logging monitor command in global configuration mode. Also, on the local device where the console messages are being generated or the syslog messages are being generated, you could type in a command logging buffered, and what that does is starts storing all the logs in your random access memory or RAM. Okay. Now be careful with that because it's a RAM. What that means is if your device reboots, all the information goes away. So ideally what you would want to do in real world is you would want to log your messages to a syslog server. And to do that, you type in a command logging host, and then you type in either the URL or the IP address of that host. Okay. Other two supplementary commands that are very important that go along with syslog are service sequence numbers and service timestamps. Now, the service sequence numbers, as the name suggests, enable sequence numbers. So when an event happens, there is a sequence number right next to it. And similarly, when you enable service timestamps, it enables timestamps to each and every log message that is generated. And if you combine the two, it's very powerful because you can see the exact sequence. You can see the chain of events that happen on that device in a very particular order. And you can also see the timestamps associated with that. Very, very helpful in event correlation and also in any type of forensic analysis. Now let's jump on CLI and take a closer look. All right, so here I am on R1. Let's go through the commands that we just talked about. So I'll go to global config mode, and I'm going to type in the command logging console. That helps me log my messages to the local device, which is really good, which means when I make changes, I can see the different messages. So let me give you an example. If I type in interface loopback 100, watch what's going to happen. There you go. A log message came up. So let me quickly give you a walkthrough of what that means. It's also called a syslog message format. The first thing that you see here is the timestamp. So this whole thing to the left, to the very left, is the timestamp. Then right next to that is called a facility. This line proto is the facility. This is the service on this device that generated this log. Number 5 is the severity level that we just talked about. Right next to that is a mnemonic. So this up-down is a mnemonic that shows what's really going on. And finally, the last piece here to the very right of our device is the description of what actually happened. So in this case, line protocol and interface loopback 100 changed state to up. And that's exactly what we did. We created this interface and it came up. Now let's jump back on CLI and keep going through a couple of additional commands. Now let's look at logging monitor. So if you remember, this is to allow people that may remotely connect to this device via telnet or SSH to be able to view logs. Okay, so that's important. Another thing you want to do is, let me give you an example. If I were to go all the way back and type in show logging and hit enter, look, I got nothing. Okay, all it's showing me is that syslog logging is enabled, console logging is enabled, and level debugging means this is level 7, which means you're going to be able to see all the levels 0 through 7, because that's the level we chose. It also shows we have monitor logging configured, but you see it says buffer logging is disabled. So we do not have buffer logging. So what does that mean? Meaning on this device, we do not have historical data. All we're seeing is the logging messages on the console. But when I disconnect from the console, these messages are going to disappear. So that's not good, right? What we should do is go to global config mode and type in logging buffered. And what that will do is, if I were to go back to interface loopback 100, for example, and type in a command shutdown and give it a second, and then type in the command no shutdown, and then go all the way back to the exec privilege mode, you see a couple of things happen here. We had a link that went down, and then we had the line protocol that went down, and then we had link eventually come up, and we also had the line protocol come up. If I were to do show logging now, watch what you will be able to see. You see, now after I enabled buffer logging, now the events are being captured in the RAM on my device. And as long as my device stays up, I'm going to have access to these logs. But if my device reboots for some reason, all of these logs are going to go away. Now that's not a good thing, especially from network visibility and troubleshooting standpoint. You want to have access to historical logs so you can always go back in time and see what's going on. And as a matter of fact, some businesses are regulated businesses, and if they're part of a government entity, they might be mandated by law to keep logs stored on a server somewhere. So let's go ahead and do that. So we'll go back to the global configuration mode and we'll type in logging host, and then we can either type in the host name, URL or the IP address. Let's just say the logging host is 10.10.10.10. And what this will do is any type of logging message that's being generated locally on our device, not only are we going to be able to see it on our console and also in the buffer, but that message will also be sent to the logging server where it can be stored indefinitely. Now let's enable sequence numbers, and let's also enable timestamps. All right, we'll do copy running config to start up config because we made a bunch of changes so far. And you see what happened here. Just because of the fact that I came back from configuration, that generated a sys message, okay? And it says configured from console by console, which means I'm on a console port and I configured something on the console. And it says that logging host has been configured and start stop has been initiated. So the events can be sent to this particular syslog server. Now, here's what's interesting. You see, I enabled sequence numbers and timestamps. Pay attention here. So check this out, guys. This right here is our sequence number 42. The next sequence number that was generated was sequence number 43. And right next to it is the timestamp. So this is really, really cool because now we're adding more intelligence to our logs. And by keeping the sequence numbers along with the timestamps, now we can do event correlation across a number of devices. If there's a security incident that happened or something went down, we can correlate all the logs and figure out what exactly happened and when. And that is Syslog for you. Now let's quickly talk through SSH. It stands for Secure Shell Protocol. Basically, it's a terminal emulator that allows you to connect to network devices in a secure fashion, and it uses TCP port 22. And like I said, it allows you to connect securely to network devices. Here is a 6-step process that you can use to configure or to set up SSH on your router or a switch to allow remote devices to be able to SSH into that device. So step 1 is we configure device name, which in this case is host R1. Step number 2 is we define our domain name, which in this case is najkazi.com. Step 3 is we define a local user account. So I created a username of Naj and password of Cisco for the purpose of this lab. In real world, of course, you'll set up an appropriate username and a very secure password. Fourth, we'll set up encryption keys for security session. The way we do that is define crypto key. We then enable SSH version 2. There are 2 different versions of SSH, SSH version 1 and 2. You definitely want to enable SSH version 2. It's more secure. And finally, we change the default authentication protocol to SSH. And we could also optionally define Telnet as fallback under our VTY lines or virtual terminal lines. Now, one thing I'm going to warn you is Telnet is not secure at all. So you should actually not be using it in real world. But for lab purposes, I'm just showing you how you can set up Telnet as a fallback mechanism. So the first thing we do is we go to R1 and we type in line VTY 0 through 4, and then we define transport input SSH as the primary mechanism and Telnet as a secondary mechanism for connecting to R1. And that's it. Now let me quickly jump on CLI and show you how to properly configure this. And then we'll also initiate an SSH session from R2 into R1. So let's go ahead and configure R1. We're going to go to global configuration mode. We already have our host name set up. So I'm going to go ahead and type in IP domain name to specify our domain server or DNS server. I'm going to call it najkazi.com. But you can specify your real domain name server or DNS server in your environment in real world. I'm going to type in username Naj, and I'm going to type in password of Cisco. I will then go ahead and set up a crypto key, generate RSA, generate keys, modulus, and we'll pick the highest possible modulus for higher level of security. We'll then do IPSSH version 2, because that's the version you want to set up. And finally, this is what ties it all together, is we go into the VTY lines and we define our transport input to SSH as primary and Telnet as a fallback. Since I'm using packet tracer, it appears I'm limited to what I can do. So you can scratch the idea of secondary. That's okay. We'll just set up SSH on this device. This is actually better to just have SSH anyway. It's more secure. So now what we'll go ahead and write our configuration from R2 now. The next thing we want to do is we want to SSH into that device, right? So we're going to define our username. We want to say Naj. And now we need to define our host, which is 10.0.0.1. So I'm on R2. I'm trying to SSH into R1. It's asking for password. If you guys remember, password is Cisco. I went ahead and slightly tweaked the username because for some reason, Cisco Packet Tracer didn't like a 3-letter username. It won't let me SSH. So on the fly, I changed the username to Najkazi, and it then lets me log in. So let's go ahead and give it a shot. So we'll go ahead and type in SSH. We then want to specify -L. You want to specify our username. And finally, we want to type in the IP address that you want to connect to. And then it asks for password, which in my case is Cisco, and I'm in. And that's it. Now I'm on R1. I'm SSH'd into that device from R2. That wraps up the SSH section. Now let's talk about TFTP/FTP. FTP stands for File Transfer Protocol, and TFTP stands for Trivial File Transfer Protocol. Now the keyword trivial means that it's a lightweight version of the FTP protocol. Both are application layer protocols. They live on layer 7 of the OSI model, and they operate on the principle of client-server model. FTP is a reliable protocol. It uses TCP ports 20 and 21, whereas TFTP is an unreliable protocol and uses UDP port 69. The whole purpose in life of both protocols is to allow a client to connect to a server for file transfer purposes. So either you're uploading something to an FTP or TFTP server, or you're downloading something from the FTP or TFTP server. That's the entire purpose of these two protocols. Now, why have multiple transfer protocols? And that's a good question. Why can't we just have a single file transfer protocol? Well, TFTP is an unsecure type of transfer protocol. It does no authentication. It does not do any encryption, but it's fast and it's very efficient. And if you think of it, the best example I can give you is when an IP phone that's connected to the network comes online for the very first time, or when it reboots, when it comes back online, it has to go and download its configuration. By default, IP phone does not have a file locally saved on it. It has to go and download its file. So it can go and communicate with the TFTP server, download its file, so the phone has the intelligence to be able to connect to the call manager and all that. And as you can imagine, if there was security involved, it would be a big hassle, right? Somebody would have to type in the credentials on the phone. That's not cool because that just creates more hassle. So TFTP comes to rescue there. FTP, on the other hand, is more secure than TFTP, but it only provides authentication though, which means, username and password, but it does not provide confidentiality or encryption. So for that purpose, SFTP or Secure FTP was designed, and it uses both authentication and encryption. But instead of using port 20 and 21, it uses SSH port, TCP port 22. Because what it does is it encrypts and encapsulates FTP traffic inside of SSH or Secure Shell over port 22. Now, a couple of use cases of TFTP. As I alluded to, you have an IP phone, it boots up and grabs its config from the TFTP server. In this case, the IP phone is the TFTP client. Now, another scenario could be we have Bob who's running a TFTP server on his laptop, and there's R1 that wants to download a copy of iOS image that Bob is serving on his TFTP server. In this instance, Bob's laptop is a TFTP server, and R1 acts as a TFTP client. Now, the use cases for FTP and Secure FTP are you may have a router that's connected to an FTP server, and that router downloads a copy of iOS image that's centrally stored on that FTP server. Now, a lot of users in real world actually have a centralized repository of all the iOS images where they keep what are called golden images. Golden images are the ones that are approved by that company, and they're certified to work within customers' environment. You've tested them in the lab, all the different functions and features you're using in your environment. Those images work flawlessly in your environment. So what you do is all the different variations of your routers and switches in your environment, you go ahead and grab those golden images and save them in a centralized repository on that FTP server, and those devices can then download those images. In that case, R1 would be an FTP client. Now, Secure FTP, that's another case where R1, that is an SFTP client, uploads a copy of its configuration securely to the FTP server or SFTP server. Welcome to CCNA 200-301 course. Today, I'm going to cover Section 4, Part 2. This is a continuation of the previous IP services section. Today, I'm going to wrap it up with NAT and QoS. Here are the topics I plan on covering today. I'm going to first do a deep dive into NAT. I'll do a NAT overview, talk through a few NAT concepts, then I'm going to talk about the different types of NAT, and finally I'll wrap it up with configuration. I will then get into the QoS section. I'll provide an overview of QoS, classification and marking, queuing, shaping and policing, and finally, congestion avoidance. Let's go. Let's first talk about NAT. NAT stands for Network Address Translation. NAT is about mapping private IPs to public IPs. And the private IP address range is defined in RFC 1918, and here are the three ranges. So the first range defined in RFC 1918 is 10.0.0.0 all the way through 10.255.255.255. It could also be abbreviated as 10.0.0.0/8. The next range is 172.16.0.0/12. And the final range is 192.168.0.0/16. If you were to look at this diagram here, guys, you got the PCs at the bottom that are connected to a switch. And we have a LAN IP range 10.1.1.0/24. And on the external side of our NAT router, the range is 98.228.196.0/29. Now, what ends up happening when we enable NAT is that the NAT router takes our private IP address and maps it to the public IP. So what that means is you see an IPv4 header, this 32-bit source address is swapped. So what NAT router does is it takes this source address that initially came from, so let's say if one of these guys down here below, let's say if Bob is using a machine that ends an IP address of 10.1.1.100, this guy right here. If this guy wants to ping some machine on the internet, that traffic is going to go through the switch up to the NAT router. NAT router will then perform a translation. It will swap out the source address of the LAN with the source address of the WAN, and it will do that mapping for us, and eventually the traffic shows up on the internet. And when the internet device sees that traffic, it actually sees the IP address of the external side of our router. It never sees that the traffic actually came from the inside of the router. It assumes that the traffic came from the outside of the router, and it's able to respond back. And you may be asking yourself a question at this point: why is that the case? Why do we need NAT? Can't we just route traffic everywhere on the internet? And you would be correct. Yes, you can, but here's the challenge. Remember, ISPs or internet service providers deny private IP address space of RFC 1918 on their internet edge routers or internet PE routers. PE stands for provider edge. They drop that traffic. ISPs by default have access control lists or ACLs in place to drop traffic that originates from the RFC 1918 private IP addressing space, because that traffic doesn't belong on the internet. That's the whole point of this RFC 1918. And that's exactly what allows different companies around the world to use the same IP addressing. So case in point, in your home office, you may have your machines be configured with the IP address range of 192.168.1.0/24. And at work, you may actually have the exact same space. And yet, at home, you can access the internet, and also at work, you can access the internet. Well, how could you do that? If there were potentially millions of people using the same addressing space, which is actually the case, then how could they access the internet? There would be a conflict. Well, what ends up happening is NAT, or network address translation, is what takes the private IPs, maps it to the public IP or IPs. It just depends on the configuration, and we'll talk through those details in a bit. And that traffic eventually makes it to the internet. That's the whole idea of NAT. Now let's dig slightly deeper. So if we were to take this NAT router and draw an imaginary line that delineates between the LAN private IP address represented in green going south and the WAN or the public side going north, the whole idea is to logically delineate between the private and the public side of our router. And what NAT does in this case is it takes the source IP of, let's say, the machine at the bottom, .100, access a website located on that web server 80.1.1.1. When it opens up a browser and wants to access that web server, if you were to zoom into the layer 3 packet, we'll see what we're seeing on our screen here to the left. Source IP is 10.1.1.100 and the destination IP is 80.1.1.1. When this traffic makes it to the router, the NAT router then will swap out that LAN IP with the WAN IP. It's going to change it to 98.228.168.3 before the packet is sent to the web server. When the web server gets that traffic, it's never going to see that it came from 10.1.1.100. What it's going to see is that the traffic came from 98.228.196.3. It will respond back to that IP, and eventually the NAT router will then do what's called a translation between the public and the private IPs, and eventually that traffic will find its way back to Bob's PC of .100. Now, to continue building on that, another concept that you want to think about is the LAN side from a NAT perspective is also called the inside of our network. And the outside interface of our router facing the internet is considered outside. There's a terminology in NAT that I want you to familiarize yourself with to really understand how NAT works. The first term is inside local address. Now, as the name suggests, it's inside of our network and it's local to us, meaning 10.1.1.0/24 range cannot be routed on the internet. Because like I alluded to earlier, RFC 1918 IP address space is blocked by all the ISPs around the globe. Nobody allows it. So that traffic will die at the edge of our internet boundary. So that's defined by local inside address. The other term that's very critical for you to know is inside global address. And sometimes people get a little confused with this term, but I want you to pay close attention to it. The IP address of 98.228.196.1 on the outside of our router is actually considered an inside global address. And the reason it's considered inside global address is because it's inside of our network, but it's globally routable. But it's inside, meaning it's in our jurisdiction. It's in our administration. It's in our control. That's where the term inside comes in. Now, when the router creates a NAT translation table, it actually maps the inside local address to the inside global address. Like literally, it uses that terminology when we're doing show commands, and I'll show you that momentarily. But that's exactly how the router is able to keep track of all the traffic that's going through it. So this web server that we're trying to access on the internet, 80.1.1.1, is considered an outside global address. Why is it outside global address? Well, it's outside of our network, outside of our control, outside of our administration. We're not controlling it. Whoever has that web server is in charge of that IP, right? It's their domain name and IP mapped to that domain name. And it's global because it's routable on the internet. And the final term that I want you to pay attention to is outside local address. Now, this is a unique bird. In 99% of the situations, you're never going to come across this. So in reality, you shouldn't actually even worry about it. But for completion's sake, so think of it as the name suggests, it's outside local address. So local address means it's not routable on the internet, but it's outside of our control. It's outside of our administration. So think of it as if you acquired another company and now you want to connect your network with that company's network, and they have their own local IP that you want to route to. In real world, you're going to come across it maybe less than 1% of the time. So I would suggest don't even worry about it. The terms you really want to understand are inside local, inside global, and outside global addresses. There are 3 different types of NAT. The first type that I want to talk about right now is static NAT. It's a one-to-one mapping between local and global IPs. So for example, your ISP might assign you a public block of 98.228.196.0/29, and then you may have your own LAN private IP block of 10.1.1.0/24. And what you might do is you might go ahead and map these manually. It's a very manually driven configuration. And the way the NAT router translation table, after you have done configuring things, the way it's going to look like is you're going to have, for example, 10.1.1.100 machine mapped to 98.228.196.3. You may have the other machine, the one that ends in .101, mapped to a different IP, 196.4. And then the third machine, the one that ends in 102, might be mapped to 196.5. So you have 3 different entries that actually manually define how your NAT is going to be configured. Now, before I move on to the other types, I think what would make it a lot easier if I went ahead and showed you this on a command line. So let me go ahead and jump on command line. So here I am on the command line interface. I've got the diagram for you below so it's easier for you to manage. Instead of 3 machines that I was showing in the previous slide, I only have 2 machines. To the left, I have Bob and Leah connected to a switch. Then that switch connects into the CE NAT router. CE here stands for Customer Edge NAT because it's at the edge of our network. And then we have an internet circuit that's coming in from our ISP. And our ISP gave us a block of /29, and we're connected to their internet provider edge router. And then I have a loopback created on the provider edge to represent this web server of 80.1.1.1. Okay, it's not an actual web server as you're seeing in the diagram. I'm just trying to simulate a web server through a loopback interface just to keep things simple and easier. Now that said, I'm currently on the CE NAT router, and let me go ahead and configure static NAT because that's what we just finished talking about. So the first thing I'm going to do here is I'm going to go ahead and go to my global configuration mode, and I need to go ahead and define my inside interface and outside interface. So step one is define my outside interface. So I'll do IP NAT outside. Okay. So this says that my fast Ethernet 00, which is pointing to my provider edge internet circuit, that's the outside of my NAT. And I'm then going to exit, and I'm going to type in interface fast 1/0 and type in IP NAT inside. That suggests that our fast Ethernet 1/0 represents the LAN side of our network. Once I'm done, the final step in static NAT is that I'm going to manually define my NAT entry. So in global configuration mode, I'm going to type in IP NAT inside source static, and then I'm going to go ahead and type in my inside local address first. So 10.1.1. Bob's PC first, which is 100. And then I'm going to define my inside global address, which is 98.228.196.3. The reason I'm using .3 is because, as you can see in the diagram here, we can't use 0 because that's the network address. .1 is assigned to the provider edge. .2 is assigned to our router's interface. So .3 is the first available IP in this range. And the other NAT entry that I'm going to create here is for Leah's PC. So I'm going to type in 10.1.1.101, and I'm going to give it the inside global address of 98.228.196.4, and I am done. So now I'm going to go to Bob's PC, and I'm going to ping 80.1.1.1, and I'm successful. I'm now going to go to Leah's PC and type in ping 80.1.1.1. So as you can see in this diagram, guys, I went to Bob and Leah's PC, and I was able to successfully ping the web server located out on the internet through my infrastructure in between. So what that tells me is that NAT is doing its job because I'm able to successfully hit the IP address of 80.1.1.1. So to demonstrate that NAT is working correctly in our machine, I'm going to type in show IP NAT translations. And this is showing me that I actually pinged, which is the ICMP message. I pinged this machine right here, 80.1.1.1, successfully from my machine, which is the outside global address. And then it also shows that Leah's PC, which is right here, 10.1.1.101, was also able to ping 80.1.1.1 on the internet. So that's pretty cool. Now, another command that I want you to keep in mind is show IP NAT statistics. What this command shows us is that we actually have 2 active translations in our NAT translation table right now, and they're both static type of NAT entries because we manually created them. So that's static NAT for you. The next type of NAT I want to talk about is dynamic NAT. Now, it's very similar to the static NAT, with the biggest difference being that it's dynamic one-on-one mapping. Before, we manually did the mapping. This time, it's more of a dynamic mapping between local and global IPs, and I'll show you exactly what I mean when we're on a CLI in a moment. Now, the ISP assigned block is the same as before. Our LAN block is still the same. And the big difference here is instead of doing one-to-one mapping, it's a lot easier if you could just map a pool of LAN IPs to a pool of WAN IPs. When we have a couple of entries, that's easy. But if you have hundreds and hundreds of machines that need to be mapped, it's a waste of time to do one-to-one mapping. It's a lot easier to just dynamically define that. Now, how the router maintains its translation table is going to look exactly the same as static NAT. The only difference is this time it's dynamic. Now let's quickly jump on CLI so you can actually see the difference between static and dynamic. So here I am back on the customer edge NAT router again. I'm going to go to global configuration mode, and I'm going to go ahead and start configuring dynamic NAT this time around. Now, this is a 5-step process. The first step is that I'm going to define my inside and outside interfaces. So I'll do interface fast 1/0, and I'm going to say IPNAT inside. I'm then going to go to interface fast 00 and say IPNAT outside. So these steps are identical to what we did previously with the static NAT. Now, here's where the difference starts. We're going to first define our access list. Let's just say access list 10. We're going to permit our LAN range, which is 10.1.1.0, and with the wildcard mask of 0.0.0.255. And by the way, in this case, what this access list is doing is instead of permitting, even though we're using the keyword permit, here we're actually matching. So when the traffic comes into our NAT router that matches this access list, we're going to do something with that traffic. So that's what's happening here. Now, I know we haven't talked about access lists yet. That's the next section that I'm going to do when we move to the next section, section 5 of this exam. But until then, just hang in there with me. Just consider this a super high-level overview of access list. And the next thing we're going to do here is I'm going to define my IP NAT pool. So I'm going to say IP space NAT space pool. I'm going to call it DN for dynamic NAT. And then I'm going to define my starting IP. So I'll say 98.228.169.3. Once again, the NAT pool that I'm defining is the NAT pool of the inside global addresses, right? And then I'm going to define the final IP in this range, which is 98.228.196.6. And I'm going to provide the net mask value of 255.255.255.248. And that is how you define your NAT pool. And the final thing that you want to do that kind of brings it all together is the access list that we created and this pool that we just created. We now have to connect these two things together. And the way we do that is we type in IP NAT inside source, and we're going to call on the access list that we created, and then we're going to call on the pool that we created called dynamic NAT, and that pretty much creates the configuration piece for us. And I'm now going to go to Bob, and I'm going to go ahead and ping that IP again, and sure enough, I'm still able to access the web server on the internet of 80.1.1.1. Going back to the NAT router, I'm going to type in show IP NAT translations, and it shows me that my machine, or I should say Bob's machine of 10.1.1.100 is able to successfully ping the IP of 80.1.1.1. And same thing with Leah. Leah was able to also successfully ping. And we can also see that because it says ICMP protocol. That's what this flag is, pro means protocol. And that wraps up dynamic NAT. All right, before I explain the last type of NAT, I want to show you a quick command that is very helpful. So if you want to clear your NAT translations, here's the command that will wipe off all the NAT translations in your current NAT table. It's clear IP NAT translation star. Right after that command, when you type in show IP NAT translations, all the translations are gone. Now let's go back to the slides and wrap up NAT. This is the final type of NAT that CCNA talks about. By the way, there are some additional NAT types, but they're beyond the scope of CCNA. We'll probably cover some additional level of depth in CCNP, but even beyond that, there's carrier grade NAT. And so I encourage you to do some Google search if you're interested in learning beyond what's covered in CCNA. But at this point, I know for some of you, it's like drinking from a fire hose. I will wrap things up with this third and final type of NAT. It's called PAT. And PAT stands for Port Address Translation. What happens with PAT is we take a bunch of LAN IPs and we map that to a single public IP. And where it comes in handy is because, as you guys know, we're out of IPv4 addresses. We actually ran out of IPv4 addresses a few years ago. And port address translation is what has allowed the life of IPv4 to be extended, because we don't need, for every single LAN IP, we don't need a one-to-one mapping with a public WAN IP. We can have hundreds or even thousands of LAN IPs that are mapped to a single WAN IP address that's publicly routable on the internet. And PAT is also called NAT overload. And the NAT translation table looks different on the router when it comes to PAT. And what ends up happening here is that, as you can see, the 10.1.1.100 address has colon and a port number in front of it. This is called an ephemeral port or private port. And the reason it's called ephemeral is because it's short-lived. After it has served its purpose, it just goes away. And it's a range of port addresses that you can use. For more details, watch my previous video I did on transport layer. And the first address that we show in this table gets mapped to the inside global address of 98.228.196.2 colon 50,101. Now, what ends up happening is the router automatically generates these port numbers. And they're different from the port numbers that are generated by the machines or the operating system. If you're using a Mac or Windows, they generate their own dynamic ports or private ports. But in this instance, the router also generates its own set of dynamic ports so it can keep track of the communication that happens. And then so on and so forth, as you see on the screen. But the common denominator here, as you can clearly see in the inside global address section of the table, is that it's the same address, the one that ends in .2, but it has different port numbers attached to it. Hence the name port address translation, aka NAT overload. Now let's quickly jump on the CLI and take a look. Now let's configure PAT on our router as shown below, CENAT. I'm going to go to global configuration mode. And the first step is, it's a 4-step process. The first step is we define our inside interface. So I'll do interface fast 1/0 and I'll say IPNAT inside. I'll then go to my external interface and say IPNAT outside. So we're done with 2 steps. The third step here is I'm going to go ahead and create an access list. I'm going to call it access list 10. I'm going to say permit 10.1.1.0. We have done this before. And the final step, we need to go ahead and map this access list to the action that we want it to take. So now we're going to say IPNAT inside source. We're going to call on the access list here, which is 10, And we're going to say interface fast 00, which happens to be our outside interface. And you're going to add the keyword overload and hit enter. And that's it. So now what I'm going to do is I'm going to go to Bob and I'm going to try pinging 80.1.1.1. Sure enough, I can ping it. I'm now going to go to Leah and try to ping. Sure enough, I'm successful. Now let's go back to the CE-NAT router and let's go ahead and look at show IP NAT translations. And here's our translation. Now, the common denominator here, as you'll see, is our inside global address remains the same. But as you can see, it came from two different hosts. It came from Bob sitting on .100 and Leah sitting on 101, clearly shown under inside local address. And the outside global address, of course, is the address of the web server here. And it's ICMP traffic, which is ping. And that wraps up the NAT section. Now let's shift our attention to QoS. Before I get into the mechanics of QoS, let's ask ourselves the question, why? Whenever you learn a new piece of technology, it's crucial to take a step back and ask yourself, why does this technology exist? What problems is this technology designed to solve? If you make this a habit, I promise you, your level of understanding will be completely transformed. With that, let's jump into why QoS. First, QoS stands for quality of service. Here I've got a very small network, and what I have in that network is two servers, each connecting at a 10 gig level. So I've got potentially 20 gig worth of capacity being utilized from downlink's perspective. But if you look at the uplink on the switch is limited to 10 gig. So that's a 2-to-1 speed mismatch. And then when we go from the switch to the router, the WAN circuit that we have is 1 gig. So that's actually a 10x mismatch. So as you can see, as we continue going upstream in our network, we have more choke points. And the speed mismatch causes packets to sit in the buffer, which is a place in memory. And traffic just sits there until it's processed. And what causes traffic to sit in the buffer? If way more traffic is coming into the device, then its ability to be able to deliver traffic on its outbound interface, then that traffic has to be queued somewhere. It has to sit in a buffer somewhere. And that's where QoS comes in. As I just finished talking about, these are the two network choke points, the uplink from the switch into the CE or the customer edge router and the WAN circuit that is terminating on our CE. Now, here are today's network challenges. So if you think about your voice flow, for example, if you happen to be on a Zoom call or Skype or Microsoft Teams or WebEx, your voice packets are very small. Contrast that to somebody who's on YouTube watching a 4K video or ultra high definition video. It's going to absolutely crush your voice flow. And that's not a good thing. That's a terrible thing. There is a way to manage that, but it is a challenge that we have to look into. Also, your business mission critical traffic must be prioritized over less critical traffic. So if you happen to be a retail shop, definitely the credit card swipe is the most critical traffic to your business. That has to be prioritized over guest Wi-Fi, for example. Also, the real-time traffic, such as voice and video, is time and delay sensitive. I'll talk more about the real-time traffic in a bit. And finally, in today's network, the expectation is that there's going to be zero downtime. Network that's always available all the time, like any other utility, like water or power. Now that said, let me give you a quick overview of QoS. So hopefully up until this point, I've built a business case for you to understand that we need traffic management technique. And that's exactly what QoS is. Because when we have a traffic mismatch or choke points in our network, that traffic has to be dealt with. And that's where QoS comes in. It helps us manage peak bursts in our network. Now, one key thing I want you guys to keep in mind is if your network is congested all the time, QoS is not going to solve your issue. You absolutely need to upgrade your bandwidth. QoS will only come to rescue if your network is congested at certain times of the day. For example, first thing in the morning when people walk into the office to log in, you're going to see a little peak there. Also, certain times of the day when there are certain activities that get kicked off, like some sort of backup, that can be managed with QoS. But if your network is congested all the time, you have bigger issues. You absolutely need to upgrade your bandwidth. The whole idea of QoS is to provide unfair advantage, as I like to call it, to certain types of traffic on our network. And naturally, you might be asking yourself a question, why would we want to provide unfair advantage to certain traffic? Well, let me give you an analogy. So if you have a 10-wheeler truck, like the one you're looking at, and then you have a beautiful Lamborghini right behind that 10-wheeler, well, the Lamborghini could go 200 miles an hour, whereas that truck might only go up to 80 miles an hour. Well, we got an issue. Plus, the truck is much bigger, and let's imagine if it's a single lane road, Lamborghini is going to be stuck behind that truck for a while until we get out of the one lane situation. So in our network, what we do is we create unfair advantage for certain types of traffic, which in this case is a Lamborghini, to allow it to have priority so it can actually get past the truck because it can move faster. Other examples could be like ambulances and fire trucks having the ability to use emergency lanes to be able to provide services to the community. So we're, in a sense, providing an unfair advantage to them so they can provide better service to the community. Similarly, in QoS, we have the ability to allow certain type of traffic to be able to provide better customer experience to our users. And there are 4 key attributes of network traffic that we must absolutely know about, and we have to know them cold to understand and master QoS. First is bandwidth. Second is delay. Third is jitter. And fourth is packet loss. Now let me dig deep into each. So what's the bandwidth? Now, bandwidth is the speed or capacity of the interface in bits per second. So for example, Bob's laptop might be connected into this customer edge router at 1 gig, and the other interface on the CE might be plugged into the web server at 100 meg. Now, as you can see, there is a 10-to-1 mismatch when it comes to bandwidth or speed. So what this would do is the laptop will have the ability to send a lot more traffic into the CE than the CE is capable of forwarding over to the web server. Now, this web server might have different types of traffic. It may have, of course, the web traffic, and it may also serve some other, if it's a unified server, it might have the ability to process voice and video. So to deal with this traffic mismatch and to do this efficiently, what the router would do is it would create different queues. Okay, so it will create, let's say, QA, it will create QB, so on and so forth. And it might say that, hey, all the voice traffic can be put into QA, and all the data traffic could be put into QB. And the voice traffic will get a high priority over the data traffic because the data traffic can be dropped. If you guys remember UDP and TCP, voice and video use UDP, whereas data uses TCP. So TCP traffic can be retransmitted at layer 4 or transport layer, whereas voice traffic gets dropped. If it gets dropped, it gets dropped. It doesn't get retransmitted. So we have to give it a high priority. So if there's a mismatch like this, voice will always be processed and sent to the web server, whereas data traffic can be selectively dropped. So this is a very high-level rudimentary example, but I'll dig a lot deeper as we continue moving forward. The next thing I want to talk about is delay. Delay is the time it takes for a packet to travel from source to destination. So Bob could be the source and web server could be the destination. It's the amount of time it takes for the packet to travel. And that's what we call a one-way delay, because that's how long it takes for a packet to go from Bob's laptop to the web server. But if you were to measure traffic in both directions, for that flow to go from Bob to the web server and then come back around, that entire thing is called round trip delay. Because what we're capturing now is the amount of time it takes for the packet to go back and forth. The third element here is jitter. Now, jitter is a variation in one-way delay between continuous packets or a packet flow. So for example, Bob may send multiple packets. So let's say the first packet sent experiences a latency of 100 milliseconds. The second packet may experience a latency of 120 milliseconds. And then the third packet sent may experience a latency of 150 milliseconds. So as you can see, between the first and second packet, we have a discrepancy of 20 milliseconds or delay of 20 milliseconds. And between the second and the third packet, we have a delay of 30 milliseconds. This difference in delay is called jitter, and it's an absolutely terrible thing, especially for voice and video real-time traffic. And finally, packet loss. Now, packet loss is the amount of lost packets on an interface represented as % of lost packets. So in this example, if Bob sends 10 packets and the web server only gets 5, that means we had a 50% packet loss, and that is terrible. In times of congestion, traffic gets dropped, and QoS tools can help us manage that aspect. Now let's talk through different types of traffic. I've got this chart here to show you how different types of traffic in our network is treated and whether or not it's delay and jitter and packet loss sensitive, because that is the most crucial thing to know before we learn the mechanics of QoS. What I have on the left is network traffic types. So the first type of traffic that I have here is network control traffic, which is reserved. The second type of traffic is voice and video, that's real-time traffic. The third type is mission critical, and the fourth type is bulk data, things like email, file transfer. Now, the network control traffic is reserved. That is not something we can change or manipulate. Routers and switches automatically prioritize their network control traffic on anything else. When I say network control traffic, what does that mean? Things like spanning tree at layer 2 or OSPF or BGP at layer 3 or routing protocols. That traffic must be prioritized because that's what allows switches and routers to build paths and traffic flows. So that path has to be available for the network to continue operating. So that is always super prioritized. And network control traffic is delay sensitive, jitter sensitive, packet loss sensitive, because it absolutely has to function before anything else functions. Now, voice and video traffic is also delay sensitive, jitter sensitive, and packet loss sensitive. The mission critical traffic typically is delay sensitive, may not be jitter sensitive, and it may not be packet loss sensitive, especially if it's TCP based. It can always be retransmitted, so it's not really sensitive to packet loss. And bulk traffic, because that's primarily all TCP traffic, it's not delay, jitter, or packet loss sensitive at all, and it's considered the lowest priority traffic in our network. Now let me quickly cover best practice service levels when it comes to voice and video. So for voice over IP, what's the best SLA or service level agreement according to Cisco? Cisco says as long as the delay, one-way delay, is 150 milliseconds or less, if the jitter is 30 milliseconds or less, and if the packet loss is 1% or less, then that's considered a good quality voice service level agreement, or SLA. Now, why do we call it an SLA? This is sort of an agreement with the business that the network is going to provide a certain level of quality to certain types of traffic so the business can continue operating smoothly. Because you can imagine if the voice quality is bad and you have a customer on the other side who's very upset, and every other word that they're saying you cannot hear because of a bad network quality, they'll get even more upset. And that's terrible. That's where the SLA comes in. Now, next up is video SLA. And according to Cisco, if the bandwidth is between 384 kilobits per second to 20 plus megabits per second, it depends whether we're dealing with a 720p or 1080p or a 4K ultra high definition traffic. Also, the delay one way between 200 to 400 milliseconds, jitter between 30 to 50 milliseconds, and packet loss of 0.1% to 1%. That's considered a good quality video SLA for any business out there. Now, as you can clearly see, video traffic is more sensitive to packet loss than even voice traffic. So something to keep in mind, whereas video traffic is less jitter sensitive and less delay sensitive, clearly. Now let's take a step back and walk you through what it takes to implement quality of service in real world. So this is based on my experience as an engineer in the industry. When I'm talking to my customers, this is my approach of collecting all the data points to be able to figure out how we're going to deploy quality of service. So the first thing you would want to do is gather customer requirements and identify types of traffic that they have in their network. The next thing you do after we have identified the traffic is divide that traffic into different type of classes, specifying if it's voice, mission critical, best effort, so on and so forth. And finally, in step 3, you define your QoS policy for each class. So you may say voice gets the highest priority, mission critical gets the next level priority after voice, and best effort you could care less because it's mostly TCP based, web surfing and all that. If it gets dropped, that's okay. It can always be retransmitted. Now, let me zoom into each step to give you a more deeper understanding of what I mean. So step 1 is customer requirements and traffic types. So here, the first step is we gather business requirements. So we identify business critical applications. So we ask the business, we audit the business, right? We go and talk to different business stakeholders and we go, hey, what are the key business applications you run in your network? So the customer might say, I have email, I have SAP or Oracle, and I've got these different storage systems and all that. And that helps you then create your quality of service policy. And the next thing you do is you also gather network requirements. So you identify various types of traffic on the network, traffic like voice over IP, traffic like video, traffic like database, and video surveillance, for example. And then after you have all those data points that you have gathered from your business and network audit and interviews, you then use that information to define service levels for these different applications and traffic types. And that leads to step number 2, which is you divide that traffic into different classes. So the email traffic will get the best effort type of mapping. The application traffic may get the transactional level, which is a guaranteed delivery. The e-commerce and web browsing, because that might be critical to your business, will get guaranteed delivery as well. And you'll classify it as mission critical traffic, whereas voice would be considered low latency, super mission critical, and you'll put that in the low latency, whereas best effort doesn't get any delivery guarantee. And then you have scavenger class, which is less than best effort. Maybe for your business, this could be social media type traffic or certain websites like Netflix and others that are super bandwidth hungry and they might bring your network to a crawl. What you do is you just proactively give those classes super low priority so they don't crush your network during times of congestion. And the final step is step 3, you define QoS policy for each class. So as you can see on the right-hand side, when you're all done with step 1 and 2, you may say, hey, ABC Corporation gets this network QoS policy, Voice traffic is an absolute priority. ERP system is critical priority. Manufacturing system is critical priority, whereas web surfing is not allowed during business hours. And you create a QoS policy. And what that means is you define different service levels of QoS for each class of traffic. And one thing I want you guys to keep in mind is QoS is a per hop behavior, or PHB. What does that mean? Everything that we have talked about so far, each device in our network, each router, each switch must have quality of service configured on it for this policy to operate correctly. So let's say if you have a server that gets plugged into a switch, and then that switch plugs into another switch, and then that switch plugs into a router, and eventually it connects to the internet, that entire chain must have QoS configured. Every single hop along the way must have QoS configured. Otherwise, it's not going to work. Okay, that's the only way it's going to work, is when everybody understands how the traffic must be treated when it arrives and that traffic sits into the queue at each hop. Now let's shift our attention to QoS tools and techniques. So the first one is classification and marking. That's the act of categorizing traffic into different classes, and then you put labels on each packet as it comes into the network. So case in point, I have this router at the bottom of the screen, and we got these packets coming in. And what we'll do then is we'll categorize those packets or put labels on those packets. So as you can see, I've got blue, orange, yellow, green. And then once we do that, the next step is we'll define queues, because that traffic, if the incoming traffic is more than our outgoing capacity or the bandwidth, then the traffic is going to have to sit in a queue. By default, routers and switches implement what's called FIFO queue, which stands for first in, first out queue. That's not really quality of service. That is just first come, first serve basis, if you will. Now, it's a good strategy when you go to a restaurant, or you want to go watch a movie, or when you go visit a particular store during Thanksgiving. All good, but FIFO is absolutely terrible way of dealing with traffic. So what we do is we use QoS, which allows us to create multiple queues for providing priority treatment. So on our router, we'll literally create different queues, as I'm showing on the screen here. And then once those queues are created, we then look into shaping and policing. Now, shaping and policing is a strategy within QoS that allows us to throttle or rate limit traffic. So what does that mean? Let me show you through this animation. So we have these packets that are coming in, right? We labeled them or we colored them, then we put them in queues, and then they zoom through the queues. And then we decide based on our strategy what we're going to do with each queue. So in this scenario, for example, the top queue, the blue one, as you can see, I'm allowing all the packets to go through. So this might be voice, and the one below it might be our mission critical traffic, the orange one. And the one below that might be the best effort traffic, the yellow one. And then the green one might be the scavenger traffic, which is absolutely terrible traffic in our network. We don't want it, and will severely limit it in ratio compared to the other packets that need priority on our network. And finally, we can employ a technique called congestion avoidance, and it's used to deal with packet loss. And the whole idea is we proactively discard some packets to begin with before filling our queue. That ends up leading to congestion. So just kill those packets and don't even allow them to get into the queue. Now, let me go deeper into classification and marking. Now, classification, as I alluded to previously, is the process of looking at packets and then putting those packets in different classes based upon a certain predefined criteria, like access control lists. Predefined criteria could be the incoming interface, IP precedence, DHCP, source or destination address, or application. Now, I will go deep into IP precedence and DHCP momentarily, so don't worry about those terms for the moment. Without classification, all you get is FIFO, which isn't really QoS, and I explained that on the previous slide. Cisco suggests classifying traffic as close to the source as possible. So what that means is, if you think about the access layer, right? So you have a server or a PC plugged into a switch. Now that's the very first point in the network where the device is connecting into our network. According to Cisco, we would want to classify our traffic right then and there at the access layer level. This way, we're able to deal with that traffic in a very nice way across all the hops. If we don't do QoS at the very first hop that traffic jumps on our network, then it may not get the type of treatment we want that traffic to get. So that's the logic behind classifying traffic as close to the source as possible. And then the next element that is very important is marking that traffic. And what that means is putting a label on each packet or coloring each packet. So here's an analogy. If you think FedEx, they have different types of shipment: ground shipment, 2-day shipment, overnight shipment. Now, let's say if you paid a lot of money for an overnight shipment and your envelope didn't get to its destination the next day, you'll get very upset because you paid a lot of extra money for the overnight shipment compared to ground or the 2-day shipment. Similarly, in the network, we have a very similar type of strategy that we can employ using QoS by labeling traffic with different types of priority and how we want that traffic to be treated throughout our network. Finally, labeled packets can be subjected to different QoS treatment. Now, before I go deep into marking, I want to take a step back and talk about another aspect of classification called NBAR. And NBAR stands for Network-Based Application Recognition. It's a dynamic way of identifying applications and protocols layer 4 through 7. So if you guys recall, the other aspect of classification that we can leverage is access control lists or ACLs. And it's manually driven. We have to do this by hand, whereas with NBAR, it's not so much manual. You type in a couple of commands ahead of time, and then NBAR engine runs on the router or a switch, any device capable of running an NBAR, and it automatically starts to identify traffic. So think of it as if when you enable NBAR, you enable an additional level of intelligence on your device that makes it layer 7 capable. That makes it smarter. That makes it smart about layer 4, about application layer. NBAR performs protocol discovery and is better than using an ACL because it's not manual. It's all automatic. It can perform automatic protocol discovery. NBAR does what's called DPI or Deep Packet Inspection, which basically means is it has the ability to look beyond the TCP UDP header at layer 4, and it looks into the payload. And what exactly does that mean? So if we were to go ahead and look at this packet right here, we've got IP header, that's layer 3 header. To the right is layer 4 header, where we get to look at the source port, destination port, and all that. But what NBAR gives us the ability to do is to do a deep packet inspection, look into the subport level. So what that means is if you were to open up your browser and access google.com versus accessing netflix.com, your router, after having NBAR enabled, now has the ability to differentiate between the two. it knows google.com versus netflix.com. And what we can do is we can set our quality of service parameters in such a way that Netflix traffic is more scrutinized, so it doesn't take up a lot of bandwidth on our network, because, you know, Netflix now supports 4K video streaming, and that can absolutely crush small packets on our network. And that's why we would want to set up QoS to begin with. So NBAR is a really cool way of gaining an additional layer of intelligence into our network. The version of NBAR that's currently supported on a global scale is called NBAR 2. It's also known as Next Gen NBAR. And by the way, NBAR is a Cisco proprietary technology. It's only supported on Cisco devices. Now, that said, other vendors have their own flavor of NBAR. So it used to be a secret sauce of Cisco. It's no longer a secret sauce. Other vendors have similar technologies that they use, but those technologies are also proprietary to them to do deep packet inspection. Now let's focus on marking. So marking is an act of putting a label on our traffic. So we can identify between voice and video and email and different types of traffic we have. There are two main categories of marking to begin with. We have marking at layer 2, and we have something called class of service or COS at layer 2. And if you're leveraging MPLS, we have MPLS experimental bits. MPLS experimental bits is more of a WAN edge technology, whereas class of service or COS is applicable to local area network or LAN. Now, we also have marking at layer 3. And at layer 3, we have two main types of marking. We have DHCP or Differentiated Services Code Point, or IP precedence. I'll now go deep into these markings. Marking at layer 2, class of service. So if you were to take an Ethernet frame and zoom into it, there's a field within an Ethernet frame called 802.1p, user priority field. That is the field that is called a class of service or COS. It's 3 bits in length. 802.1p supports up to 8 classes of service. From a binary perspective, that's 2 to the power of 3, which equals 8. 802.1p marking is only preserved through the LAN, and when that traffic hops over the wide area network, that marking is lost. What that means is we have to figure out a way to somehow map our layer 2 QoS markings over layer 3 network. Now, here's a COS values table. As I mentioned, COS is a 3-bit field within the Ethernet header. That means 2 to the power of 3 equal 8 values. Here's how the 8 values are represented in this table. So to the left, we got the COS or class of service value, and to the right is the application. Now, a couple of things I want to bring to your attention, and it's very important that you grasp this from the get-go, is because it's going to help you identify and learn QoS, as it's going to make it simpler for you to identify and learn QoS as we continue moving on, is that COS 6 and 7 are reserved. So what that means is we cannot modify these. These are things like routing protocols, the different management functions on the router. Basically, these are the most essential functions of the router, kind of like a heart and brain of the router. Without those two components, the router cannot function. That's why these two COS values have been reserved for those particular functions, for the router to be able to provide the highest quality of service to the different functions that are important for its survival, if you will. Now, the first value that we can start manipulating or start configuring is CoS 5. So we can map our voice to CoS 5. We can map our video to CoS 4. We can map our call signaling to CoS 3, high priority data to CoS 2, medium priority data to CoS 1, and best effort data to CoS 0. Now let's look at marking at layer 3. So if we were to look at an IP header and zoom into the toss byte, which is a field within an IP header, it's an 8-bit field, starts 0, goes all the way up to 7. The leftmost significant bits within the toss byte are called IP precedents. These are bits 5 through 7, as you can clearly see here. And the leftmost significant bits 2 through 7 are called diffserv or differentiated services code point or DSCP. And the least most significant bits, the two most least significant bits are called IPECN or explicit congestion notification. Now, we don't worry about IPECN anymore. That was more of a frame relay technology concept, which is extremely rare. In most of the instances, you'll probably never even configure or touch frame relay, so you can pretty much ignore IPECN. The key is understanding IP precedence, which is the leftmost 3 significant bits, and then the DSCP, which is the last 6 most significant bits. IP precedence could also be represented as IPP, and that gives us 8 possible classes. Now, some people may consider this not enough granularity because if you guys recall, when we looked at the CoS map previously, 2 out of 8 values are reserved, which only gives us 6 different classes we can create. So that's not enough granularity. Now, if you look at the DSCP, which is 6 most significant bits of toss byte, that gives us 2 to the power of 6, which is 64 possible classes. And that gives us almost too much granularity. And we have to find the fine balance between the two. And finally, DSCP is backwards compatible with IP precedence. So what that means is if you have traffic that's marked with DSCP bits, and it gets to a point in the network that doesn't understand DSCP, it can still be mapped to IP precedence. So that's what that means. Now, let's talk through the IP precedence / class selector DSCP value table. So initially, toss byte was defined with a 3-bit IP precedence. Then came along DSCP. Class selector was introduced for backward compatibility when the DSCP was introduced. So here's what it means. So as you can see in this chart, the leftmost column in this chart is class of service, which we looked at earlier. To the right of it is IP precedence. And as you can see, CoS maps directly with IP precedence. Like literally, it's a 1-to-1 type mapping. And similarly, class selector is for backward compatibility. That's what makes DSCP compatible with IP precedence. And the rightmost column that we have here, so at the very top, we got the decimal DSCP value of 56. The one below that is 48, 40, so on and so forth until we get down to 0. And you can see how they are mapped. And that's how the backward compatibility is provided and preserved from LAN to WAN and also from layer 2 through layer 3. There's another important aspect of QoS called assured forwarding. And assured forwarding is a form of differentiated services, and it's defined in RFC 2597. And it defines a set of 12 DSCP values categorized in 4 different queues. And within each queue, we have 3 different levels of drop priority or drop probability. So let me quickly walk you through this. So we got class 1 through class 4, as you can see on the screen here. And what we have within each class. So you can think of each class, let me explain. So you can think of each class as if it's a queue. So class 1 being Q1, class 2 being Q2, so on and so forth until we get to Q4. Within each queue, we have different drop probabilities. What does that mean? If we have a packet that's marked with AF11 in class 1, and if we have another packet that's marked with AF13, AF13 will get dropped first if there's congestion, as opposed to AF11, because AF11 has low drop probability. So within each class, the value to the leftmost, it's a preferred type traffic, whereas the traffic in high drop probability will get dropped before the traffic in the low drop probability. And similarly in class 2, same idea in class 3 and 4. Now, another thing I want you to consider is the absolute worst class and highest drop-off probability is 38. As we go up in classes, the drop probability increases, whereas when we go from left to right, the drop probability also increases. So the absolute worst is AF43, and the absolute best is AF11, based on this chart we're looking at. Here is the best practice QoS markings recommendation. Now this gives you a full end-to-end idea of class of service and quality of service. So let me quickly walk you through this. So in this chart, what you're looking at is the class of service 6 and 7 is reserved, right? So that maps directly to IP precedence. Per hop behavior is the class selector. And then the DHCP value is 56 and 48. These are all reserved. And what matters to us is we start classifying and marking our traffic at COS value of 5 and below. Video conferencing is 4, critical data is 3, call signaling is 3, transactional data is 2, bulk data is 1, best effort is 0, and scavenger traffic within our network could be CS1. Now this could be peer-to-peer traffic or essentially bad traffic. It's worse than best effort, okay? It's bad for our network. It could be peer-to-peer traffic. Some forms of peer-to-peer traffic are considered illegal, especially when it comes to downloading movies and things of that nature. So that's absolutely scavenger traffic. We might even consider Netflix at work a scavenger type of traffic, right? Because it's hurting the rest of our users in the network, especially if people are watching movies in ultra high definition. So what we would do is we would classify traffic, Netflix traffic as scavenger, and we'll give it a very, very low bandwidth. And we'll drop that traffic over voice or video type of traffic. Now, another question you may have at this point is how many classes of services do I need? You might be confused at this point. Now, ideally what Cisco suggests is that you should have no more than 11 classes of service defined within your network, because it gets to be way too much to manage. Because remember, each hop, layer 2 and layer 3 hop in our network has to have class of service and quality of service configured. It gets to be way too much to do end-to-end. So in an ideal world, you should only have between 4 to 5 different classes of service. Now, what I've configured over the years, most of the networks I have configured fall between 4 to 5 classes of service, up to 8 classes of service. 11 gets to be a bit too much. Now, if you're a service provider, of course, the more classes you have, the better it is for you. But as an enterprise customer, you should stick between 4 to 5 classes, potentially up to 8 classes, no more. Because otherwise, as you can see at the bottom of the screen, the level of effort and the level of time that it takes you to configure this significantly increases as you go from lower number of classes to higher number of classes. And another important aspect for you to consider is end-to-end QoS strategy. The key to providing end-to-end QoS strategy is to map layer 2 COS markings to layer 3 QoS markings and vice versa. So as you can see here on the screen, we got IP header that has DHCP marking. It maps directly to the Ethernet header and vice versa. As the traffic goes between LAN to WAN and then from WAN back to the LAN, we can copy those markings from layer 2 to layer 3 and from layer 3 back to layer 2. Now, within the core of the service provider, what we have is, if it's an MPLS service, we have experimental bits. And these could also be mapped from COS or RTOS or type of service into the MPLS. So this way our service provider can honor those markings and QoS end-to-end through the core and edge of the service provider network, in addition to our campus and edge network. Another important aspect of QoS is called QoS trust boundary. Now, what is a trust boundary? It's a logical parameter of your network. So what does that mean? Here's an example of a network. We have a laptop that's plugged into switch 1, which is plugged into switch 2, which is plugged into a customer edge router, which is plugged into a WAN circuit. Now, in this example, our trust boundary is defined right at the edge of our switch. Switch 1 becomes our trust boundary, which means the access port, the laptop, is untrusted, whereas the traffic from switch 1 all the way through to the CE router is all trusted because this is in our control. As an administrator, I'm going to jump onto switch 1 and configure quality of service. I'll do the same thing on switch 2, and I'll do the same thing on my CE router. So my QoS that's in my control is considered trusted, and that's where the trust boundary is defined. Once again, trusted means the QoS markings are honored, whereas untrusted means if somehow the laptop is marking traffic, most likely we're gonna not honor those QoS markings and remark the traffic at the edge of our switch, our access switch. And another important aspect for you to keep in mind is Cisco suggests that you should mark traffic as close to the source of the network as possible, which means right at the edge of our access network, our access layer, we would want to mark traffic. Now, the next thing I want to look at is if we have an IP phone in the mix, which has a laptop or a desktop plugged into it, our trust boundary shifts. Instead of switch, now the IP phone becomes the trust boundary, because if it's an Cisco IP phone, it has the ability to mark its own traffic. So we don't necessarily need to do that on the switch anymore. Now it's the responsibility of the phone to mark its own traffic. We now just have to classify traffic on our switches and routers to make sure we're able to intelligently identify and classify that traffic. Now, shifting gears, going slightly deeper into quality of service, a very important aspect is called queuing. Now, if you guys remember, why do we need queuing? Well, the big idea is we got a bunch of ports that are on the LAN side of our router, and they might be very high-speed links, multiple 10 gig ports, but our WAN circuit may only be a 100 meg circuit. Now, that's a huge mismatch. We have tens of gigs worth of traffic coming into our router, and then the WAN circuit is severely limited. It's only 100 meg. When that happens, the traffic has to sit in a buffer or a queue for a limited amount of time before that traffic gets processed. This is where queuing comes in. So let's do a deep dive into what happens inside of a router. Now, step one is router receives traffic on its receive interface. Step 2 is we perform ingress services. We may have an access control list, we may have a NAT policy, we may have a PBR or policy-based routing setup. These are all ingress services. The third thing that happens is we have to make a forwarding decision for that traffic. So now that traffic has come into the router, what does the router do with that traffic? Does it drop it or does it forward it? It has to look into its routing table to determine that, right? Once it's done that, and let's say it makes a decision that it has to go out of the network, now at that point, once the forwarding decision has been made, the traffic now hits the egress services engine. Once again, this could be access control lists, NAT function, etc. And we then get to our output queue. Now here, the packets literally get shoved into a queue. And finally, the traffic gets to the transmit interface, which means it's ready to exit our router. If a network device has a single output queue, it uses FIFO, or first in, first out queuing scheduler. Now, we have talked about FIFO before. That means as the packets come in, they go out. We don't provide any preferential treatment. Nobody's special. Every single packet is treated equally. Now, one important aspect for you to keep in mind is hardware queue always uses FIFO scheduler. Whereas the software queues, we have the flexibility to create and configure multiple software queues. So I want you to understand, now this is slightly beyond the scope of CCNA. This is more of a CCNP, CCIE concept. But I think it's important for you to understand that right from the get-go. So you have a level of understanding that there are different types of queues. The hardware queue is the physical queue, the physical interface itself of the router or a switch. Whereas the software queue is the ability that we have that allows us as network administrators and network operators to be able to configure our device and configure different queues within our network for quality of service. Now, there are different types of queuing mechanisms. The first one is called class-based weighted fair queuing. Now, how does this work? So we have a receive interface, and the receive interface receives traffic. We then classify traffic, which means we have some sort of a classifier, either an access control list or NBAR, some sort of mechanism in place to identify traffic and mark that traffic, right? So classifier not only classifies or identifies traffic, but then it also puts a label or color the packets as they come in. We then take those classified packets and create multiple queues and put each packet type into each queue. And then the last component of queuing is called a scheduler. And scheduler is where things get really interesting. Here's where we get to decide how we want to deal with that traffic. If there are certain queues we want to provide higher preferential treatment to, scheduler is where we get to define that. And the most common way of dealing with that is called round robin. And eventually the traffic hits the transmit interface and goes out. And once again, the physical aspect of the transmit interface is always FIFO queue. Now, a couple of things for us to keep in mind. Class-based weighted fair queuing guarantees a minimum amount of bandwidth to each class. So the idea here is we're defining the minimum for each class. For example, when I say Q1 gets 15% of the bandwidth, that means I'm defining the minimum amount of bandwidth that Q1 can get. It can get more, but that's the minimum. When I say 40% for Q2, that's the minimum Q2 will have, and 45% will be the bare minimum for Q3. And when we add up all these values, that adds up to 100%. Now, what is round robin? I mentioned round robin, right? So round robin, it's a form of load balancing algorithm, and it allows us to cycle through the queue in order, taking turns with each queue. So that means when packet comes into Q1, that traffic gets dealt with. Once that packet has moved on, then we go to Q2. We take one packet, move it forward. We then come to queue 3. We take that packet, move it through the queue. We then go to queue 1 and rinse and repeat. And the whole cycle keeps repeating over and over again. That's called round robin. Now, the big thing I want you to keep in mind is, as the name suggests, class-based weighted fair queuing. Weighted means, as you can see, each queue has a different percentage of bandwidth allocated to it, which means queue 3 will get better opportunity to send packets compared to queue 2, and queue 2 will have preferential treatment over queue 1 because both queue 2 and queue 3 have a higher minimum percentage allocated to them. Now, the next up is LLQ, or low latency queuing. As you can see here, we have a receive interface, we have a classifier. Now, the difference here is we have an additional queue. Here we have voice, data 1, data 2, and default. And in our scheduler, what we can do is we can allocate a certain percentage of bandwidth to our special queue called voice queue. This is also called a strict priority queue, which means every time there's congestion in the network, our voice packets will always be handled first. Once all the packets sitting in that queue have been processed, we'll then move on to other queues. And once again, it's very similar to class-based weighted fair queuing. We are now just adding another layer to our queuing, and that's where LLQ comes in. LLQ can cause queue starvation, and that's why we police the traffic. So what does that mean? So remember how I mentioned previously that in class-based weighted fair queuing, we define minimum bandwidth? Well, in this case, the voice queue will have the maximum bandwidth defined, meaning we're not going to be able to send more than 20%. But it's strict priority queue, meaning nobody else can use this bandwidth either. It's 100% dedicated to us. So it's sort of like that emergency lane idea where an ambulance or a fire truck will always have the ability to have preferential treatment because it's providing a service to the community and potentially saving lives. Here, we're saving people's phone calls, which are very important. Because UDP traffic, once it's dropped, whereas data traffic, TCP traffic can be retransmitted and resent. Finally, LLQ uses the concept of maximum bandwidth, as I alluded to a moment ago, and excess traffic gets dropped, which means we have to be smart when we set up our LLQ and we define the percentages, because anything beyond that will get dropped. So typically what we do is, from a real world perspective, we look at how many SIP sessions or voice calls our network can handle based on the SIP trunk that we have from our service provider. And then based off of that, we reverse engineer and come up with a value that can be mapped to the LLQ. Now, the other concept I want to talk about is shaping and policing. This is also related to queue management in a sense that both shaping and policing monitor each packet as it comes in and measure the number of bits per second over time. And typically, shaping and policing are used at the WAN edge of our network. The primary goal of these tools is to keep the bit rate at or below the configured interface bandwidth. But when it's exceeded, if we have a shaper defined, what shapers do is they hold packets in queues to delay the transmission. So class-based weighted fair queuing that we just finished talking about is a form of shaper. Whereas we also have policers where we discard packets. And the LLQ part of weighted fair queuing that we talked about would be considered a policer because we're discarding packets there. Now let's zoom into each. Let's first talk about policing. Traffic policing drops or remarks traffic when the traffic exceeds a certain configured threshold. And the output appears as a sawtooth. So as you can see, traffic is coming into our interface and we apply a policer to it. And what ends up happening is we have a certain threshold defined and the traffic can never exceed that threshold. And when it hits that threshold, then the traffic just significantly drops. And then it starts to build up again and drops again. And that's where we're seeing these like peaks and valleys. And this is what's referred to as sawtooth. And policing can be applied to both inbound and outbound traffic on a link. Now, let me give you a quick real-world perspective of setting up policing. So let's say we have this network. To the left, we have a San Jose branch, and to the right, we have a branch in New York. And in between, we have a service provider network. Let's say it's an MPLS network. And our CIR, or Committed Information Rate, SLA, or Service Level Agreement with our provider is 500 meg. Now, even though we got gig interfaces on these routers, the actual committed information rate that we are paying for and we're getting a SLA for from our provider is 500 meg. That's half the capacity of a gig interface. So what that means is the service provider will enforce an ingress policer at that port that is coming into their provider edge, both into New York and San Jose. And this keeps our network from pumping too much traffic into the service provider. Because as you can imagine, if the service provider is serving thousands or tens of thousands of customers, and they're selling these services to all these different customers, and every single one, if they started to pump maximum number of traffic, that could cause severe congestion into the service provider core. And the customers that are paying big money to get better quality service will have to suffer. And that is bad business. So what service providers do is they set up policing at the edge of their network to control traffic. Now, service provider has two choices here. They can either completely kill any traffic above 500 megabits per second, or what they can do is, if their backbone is not congested, let's say if the provider edge San Jose and provider edge New York, if the core in between is not congested, what the service provider may consider is, hey, instead of dropping any traffic beyond 500 meg, what I'll do is I will go ahead and mark that traffic as low priority through my core. And if I don't have congestion, I'll let that traffic go through. But the minute I start experiencing congestion, I will go ahead and drop any traffic beyond 500 meg in my core. That is an absolute possibility. And that's why I alluded to earlier that policing allows us to either drop traffic altogether or remark traffic with a low priority, for example. Now let's talk through shaping. Traffic shaping retains excess packets in the queue and schedules their transmission over increments of time. And what that means is traffic is coming into our ingress interface, we apply a shaper to it, and when we do, as you can see, it's a very smooth line that we have, and we don't have those peaks and valleys that we saw earlier with policing. Now, shaping can only be applied to outbound traffic on an interface. And shaping requires sufficient memory to buffer delayed packets. And this is where class-based weighted fair queuing and LLQ comes in that we just finished talking about. So you have to keep in mind that if you're going to be applying shaper, that your switches and routers have sufficient memory in them to be able to handle all that traffic that's going to sit in a queue before the packets get processed. Now, shaping slows down packets, which is a bad thing because it creates delay and jitter. For voice and video, it's a terrible thing. Now, let's quickly take a step back and think about how network devices send traffic. So the way network devices send traffic is they send traffic at the line rate. So what that means is if I have a gig interface, I will always try to send traffic at a gig speed. As I showed you an example earlier when we were talking about policing, if the committed information rate from our service provider is lower than the physical interface capacity, well, we're going to have a mismatch. If I have a gig interface, but if I can only send traffic at half the capacity, I need to somehow figure out a way to slow traffic down. The best way to do that is we're going to actually divide that traffic into different chunks. There's no magical way of slowing down traffic. Instead, what we do is we send traffic and then we wait. We send traffic again and then we wait, and rinse and repeat. And what we do is we set up what's called a shaper time interval. So once we have shaper time interval configured, what it does is if you have a gigabit physical interface and a CIR of 500 meg, what that means is we're going to send data 50% of the time and then wait another 50% of the time. So that means is we're only sending traffic half of the time and we're waiting the other half doing nothing, just literally waiting. And that's how we manage the slowdown of the traffic. We cannot slow down the interface. We just create multiple time intervals to send traffic. Here's another way of looking at it. So let's say in this example, the x-axis represents time and the y-axis represents bandwidth. That means T0 to T1 equals 1 second shipping time interval. That means if you're sending at half a gig rate, we're sending traffic 500 milliseconds, and then we're not doing anything and we're waiting for the next 500 milliseconds. We then send traffic again for 500 milliseconds, which is half a second, and then we wait another half a second and rinse and repeat. That means we're shipping at 50% of line rate. So our line rate is gig, and we're sending traffic at half a gig. Now, let's dig slightly deeper. Now, if you recall, to maintain good voice quality, we need a 150 millisecond one-way delay. But currently, we're sending traffic at 500 millisecond and then waiting another 500 millisecond. Now, that's not good. How do we fix that? Well, the way we fix that is we create shorter and shorter time intervals. So we take the T sub C, which is 1 second or 1000 milliseconds. We send at 1 gigabit for 500 milliseconds and then wait for 500 milliseconds as we talked about earlier. We then divide it up by 10 and we go 0.1 second. That's 100 milliseconds. We send at 1 gigabit for 50 milliseconds and we wait for 50 milliseconds. And then we divide that by 10 again and we get 0.01 second. That's 10 milliseconds. We send at 1 gigabit per second for 5 milliseconds and we wait for 5 milliseconds. Now, according to Cisco, 10 milliseconds is the best time interval you should use for dealing with real-time traffic like voice and video. Now, the opposite of congestion management is congestion avoidance. And this is a QoS feature that allows us to randomly drop packets before the queue fills up. So the idea is, let's drop traffic so the queue never fills up. And it's applicable to whether you have single queue or multiple queues. It allows us to monitor our queues, and if they exceed a certain threshold, we just start randomly dropping TCP traffic. Now, the most basic form of congestion avoidance is called tail drop. So let me give you an example of a tail drop. If this is a queue on your screen and we have all these packets coming in, 1, 2, 3, 4, 5, the minute we get packets 6 and 7 that have no space in the queue because our queue is full, we'll go ahead and drop those packets and any other subsequent packet that comes in because our queue is full. That's called a tail drop because literally that traffic is at the tail of the queue. Now let's take a step back and think about how TCP works, because congestion avoidance is applicable to the TCP traffic. So step 1 in TCP is we do a 3-way handshake between sender and receiver. After the 3-way handshake is done, step 2 is we do TCP windowing, which is a negotiation of a window size and bytes between sender and receiver. And there's another concept within TCP windowing called TCP sliding window. What that means is as the sender and receiver start to send traffic in TCP, with every successful acknowledgement, we keep doubling the size. We go from 1 to 2, 2 to 4, 4 to 8, 8 to 16, so on and so forth. And it keeps doubling the size. That's called sliding window. Until the receiver loses a TCP segment. And as soon as that happens, we shrink the window size in half. Now, this is a very, very bad thing. And what that leads to is TCP slow start and TCP global synchronization. Now, let me explain these concepts of TCP slow start and TCP global synchronization through a visual means here. So if you look at this chart here, we have 3 different flows being represented. Flow A in red, flow B in yellow, flow C in blue. When there's no traffic, the queue is empty. Multiple TCP sessions start at different times. So initially we have flow A starting, then a little bit later we have the flow B starting, and then the flow C starts. Now over time, the window size for each class is increased to the point that the queue fills up. Now TCP was designed this way for efficiency reasons, right? To keep increasing the size to maximize the number of packets that are being sent and or shared or transmitted between sender and receiver, and we spend less time waiting and more time sending. But because of this nature of TCP windowing, the queue at some point is going to fill up. And when that happens, we have tail drop. And tail drop is not a good thing, right? Because it causes TCP sessions to go down at the same time, and then it causes TCP slow start. So let me explain. As you can see, we have the tail drop happening right here. You see, this flow A was building up to the point that our queue was filled, and boom, we had a huge drop. Then the TCP windowing started to work its magic, and it kept doubling until it hit a point where the queue was filled again. We had another tail drop, and then the same cycle repeats. Then we hit another tail drop, cycle repeats, another tail drop, cycle repeats, another tail drop. That is a very inefficient way of using a network. Now, when a single flow is affected by this tail drop, we call that TCP flow start. But when multiple flows, which in this case is flow A, B, and C, all get affected by it, we call it global synchronization or TCP synchronization. That is a bad thing, causes inefficiency in our network. As I just finished explaining, when we have multiple TCP sessions that are being dropped, it temporarily creates space in the queue, right? Because everything is just going down, so more space is created. Now our queue is empty, and then the window sizes get to increase again, because this is how a TCP sliding window works until the tail drop happens. And we want to avoid this situation. This is a problem, and we got to fix it. Now, how do we fix it? There is a technique within congestion avoidance called WRED, or Weighted Random Early Detection. It's an idea where we prevent a queue from filling up by randomly dropping packets when they exceed a certain threshold. Weighted random early detection pays attention to the markings. Packets marked with high priority are less likely to be dropped, meaning voice and video are less likely to be dropped, whereas traffic that has best effort, like maybe web surfing or email, has the ability to get dropped more often. So you can think of WRED as a hitman. So you hired this hitman to take out all the bad packets. That's what weighted random early detection does for you. So as you can see in this example here, at the head of our queue, the green portion, we initially start out where the queue is empty. We then get to a point where we hit our minimum threshold. Now this is literally a threshold that we define on our router or a switch to define our congestion avoidance. And then, so there's no drops happening in the green zone. But then in the blue zone between maximum threshold and minimum threshold, we start to drop certain traffic. Once again, most likely, we're not going to drop our voice and video. We're going to drop other types of traffic. And eventually we get to the point where we have queue that's full, and then everything starts to drop there. We don't want to do that. And this is where the hitman comes in. Hitman shoots packets that are in the blue zone to make sure that the queue never fills up to begin with. Now here's the summary of QoS tools and techniques that we just finished talking about. This is like a step back of everything we covered. I understand if you're getting exposed to this concept for the first time, it may feel like drinking from a fire hose. That's why I decided to take a step back and provide you a high-level perspective again. So to the left of this table, we have QoS tools like classification, marking, congestion management, shipping, and congestion avoidance. In the middle, we have Cisco IOS QoS features we can use for each of these tools. And then to the right is the behavior. Now, feel free to go ahead and take a snapshot of this and put this in your back pocket for exam reasons or real-world reasons. But this is a very handy-dandy chart that can help you. You can also think of it as a quick cheat sheet for the different types of QoS tools and what features are available to you when it comes to Cisco IOS. And the very final thing that I'm going to wrap this entire section with is the end-to-end QoS view from a real-world perspective. Now, end-to-end QoS means we have the enterprise QoS, which is our local area network, and then we have the service provider QoS, which is our wide area network or WAN. Combined together is what is end-to-end QoS. So in this example, to the left we got campus, to the right we got a branch, and for the campus to talk to the branch and vice versa, we have the service provider cloud in the middle. Now, how would you go about setting up QoS in this network? The first place where you would configure QoS is campus access. You would set up speed and duplex settings, classification and trust on IP, phone and access switch, multiple queues and switch ports, and priority queuing for VoIP. The next place where you would want to set up QoS is your campus distribution. Here you have layer 3 policing and marking, multiple queues and switch ports, priority queuing for VoIP, weighted random early detection with data queue for congestion avoidance. The third place where you want to set up your QoS is WAN edge. You define your SLA or service level agreement here. You have classification and marking, LLQ or low latency queuing. You have link fragmentation and interleaving. Now, we didn't talk about link fragmentation and interleaving, but this is a blast from the past. It was more applicable to slow speed links in the past or frame relay and all that, where we used to do TCP header compression and VoIP header compression. That is no longer necessary in a high-speed world, but it's still there if you want to use it. And then you have weighted random early detection and shaping. Now, the key concept that I want you to understand is when you have a service provider and you buy MPLS service from them, make sure that the quality of service that you have configured on your network will be honored through the service provider edge and core. For example, if you have 8 classes of service within your LAN, but your service provider can only honor 5 classes of service, you're going to have an issue because you're going to have to somehow either map between 8 to 5 classes or do something to avoid any packet drops through the provider cloud. So what I would suggest is make sure your LAN and your WAN QoS has the same number of classes, okay? And it's important that you talk to your service provider when you're initially buying MPLS service. It's a very important topic. And you would want to do your capacity planning for different queues. You would assign a certain queue to voice versus data. You would want to look at differentiated services through the backbone. You look at low latency queuing, and you'll look at, once again, congestion avoidance through the provider core. And that is a wrap. Welcome to CCNA 200-301 course. Today, I'm going to cover Section 5, Part 1 of the CCNA exam, Security Fundamentals. In particular, today we're going to discuss IPv4 ACLs. Here are the topics I plan on covering today. First, ACL Overview. Second, Standard ACLs. Third, Extended ACLs. Fourth, Named ACLs. And finally, I'll wrap it up with real-world perspective on ACLs. Let's go. Let's first cover ACL Overview. ACL stands for Access Control List. Each ACL contains multiple ACEs or access control entries. And you can also think of an access control entry as an ACL statement. So basically, ACL is a collection of statements, or ACEs. ACL either permits or denies traffic. That's a very basic function of an ACL. So as you can see, the picture here, ACL is analogous to a coffee filter. So if you think of a coffee filter, what does it do? It traps the coffee grounds, but it allows the flow of liquid to go through. Similarly, ACLs filter traffic in our network. Each ACL is either applied inbound or outbound on an interface. ACLs actually do a lot more than permit or deny. And here are some of the things ACLs do. They filter ingress or egress traffic on an interface. They filter routing updates to and from neighboring routers. They are used in policy-based routing. They're used in network address translation. And when we use them in NAT, they're primarily used for not permitting or denying traffic, but they're used for matching traffic. In VPN, similar functionality as NAT. They're used for matching traffic. And QoS, same idea. We use ACLs to match traffic. You can either create a numbered ACL or a named ACL. There are three main types of ACL: standard ACL, extended ACL, and named ACL. Now, named ACL is not a new type of ACL. It's actually a spin on standard or extended ACL, and I'll get into those details momentarily, but just keep in mind that named ACL leverages either a standard or an extended ACL. Each ACL is processed top to bottom. Each access control entry can only have one set of conditions, either permit or deny. If no match is found, next ACE is processed in that list. If a match is found, that's it. Processing stops, no further ACEs are executed, and the whole idea here is first match logic. Meaning, if you think of an ACL as a sequence or a list of statements, as soon as the router finds the first match, it stops executing. Because that's it. It found the match and it's done. So for example, if you have 10 entries in your ACL, if the first entry matches the packet, that's it. The 9 other statements in your ACL will be ignored because we have found our match. Now, order of statements is important in an ACL. The most specific or restrictive statements should be at the top of the ACL, and the least restrictive should be at the bottom, or the more general should be at the bottom of the ACL. Once again, the reason it's important is it's literally a list, and whatever is at the top of the list has the highest level of importance because that will get processed first. And the more general statements should be at the bottom of the list. Each ACL contains an implicit or invisible deny any at the bottom of the list. So this is a big gotcha. And one important thing to note is only one ACL can be applied per interface per direction. Now what that means is if you have an interface, you can have an inbound ACL and also an outbound ACL. But the inbound ACL is going to have to be different from the outbound ACL for obvious reasons, right? But you cannot have two different inbound access lists applied to a single interface or two different outbound access lists applied to a single interface. It doesn't work this way. You can only have a single ACL applied to an interface in each direction. Now let's shift our attention to standard ACLs. This type of ACL filters only based on the source address and the packet header. What do I mean by that? Let me explain. So if this right here is a packet, and let's say this right here is the payload, which is the data, And right here, we'll have source IP, and in the header, we'll also have destination IP. Now, what ends up happening is, in this scenario, when we apply an ACL, the ACL will only pay attention to this field, the source IP field. And that's exactly what I mean right here when I say that ACLs, the standard ACLs, only pay attention to the source address. It lacks granularity. Because standard ACLs either permit or deny traffic at a protocol level, at IP level, they don't really have the ability to give you a lot of granularity. Standard ACL number ranges start from 1, go all the way up to 99, and there's another expanded range that starts from 1300, goes all the way up to 1999. Now, from a best practice design perspective, you should place standard ACL as close to the destination as possible. And I'll walk you through the design and show you why that is important. And finally, here's the CLI syntax. So if you're on a router, we'll type in the command access-list space, and then we'll choose 1 through 99 or 1300 through 1999. And then we'll say either permit or deny, and then we'll have the matching parameters. So the first step is the creation of the access list. Once the access list has been created, the next step is that we go to the interface and we apply it to the interface. So in this scenario here, we're saying interface fast00 IP space access-group space out space 1, which happens to be our ACL number. Now, always remember, it's a two-part thing. Part 1, you have to create an access list, and part 2 is you have to apply the access list to the interface. If you don't apply it to the interface, access list is not going to do anything. It's just going to sit there without doing anything. Now, let's quickly talk through the wildcard mask, because ACLs require a wildcard mask. Now, wildcard mask can block a range of addresses or a whole network with just one statement. Zeros indicate which part of an IP address must match the ACL. Ones indicate which part of an IP address doesn't have to specifically match the ACL. Use the host parameter in place of 0000 wildcard, or use the any parameter in place of 255.255.255.255 wildcard. And here's a quick chart. So if you want to match the entire IP address exactly, then you're going to have to say 0.0.0.0. And if you want to match anything, then you'll say 255.255.255.255 at the very bottom. And that means all 32 bits can be matched because those are don't care bits. Now let me do quick whiteboarding to explain wildcard mask compared to the standard subnet mask that we are used to. So if you look at a subnet mask, let's say a /8 subnet mask, what do we have? We have 255.0.0.0. If you have /16, that's 255.255.0.0. And if you have /24, that is 255.255.255.0. Now, what happens in a wildcard mask is, by the way, in one of the earlier videos, I covered the wildcard mask, but consider this a review. And review never hurts, so I decided to give it a shot so you guys can solidify this concept in your head. So to the left is the subnet mask, but here let's do the wildcard mask, or WM. So the opposite, so remember, wildcard mask is the mirror opposite of a subnet mask. So mirror opposite would mean we'll go from /8 being 255.0.0.0 to 0.0.0.255. So it's literally the opposite. In this case, for /16, it's 0.0.255.255. And in the case of /24, it's 0.0.0.255. And like I said, this is the mirror opposite of the subnet mask, the wildcard mask. Now, you may be thinking, how about some tricky scenarios? Let me give you a couple of tricky scenarios. How about /12? So let's first look at the subnet mask. So that's 255 dot. Now, 255 is 8 bits, right? So an IP address is divided into 32 bits, which means it's 8 bits plus 8 bits plus 8 bits plus 8 bits. So each octet happens to be 8 bits, right? So in /12, the first octet is 255. What about the second octet? Well, here, what ends up happening is, if you guys remember the handy dandy binary conversion chart, 1, 2, 4, 8, 16, 32, 64, 128. Let's see what 12 gives us. So that's 4 bits. 1, 2, 3, 4. That gives us a 240. If you were to add 128 plus 64 plus 32 plus 16, that gives us a value of 240. So we'll place 240 here, and then we'll do 0.0.0. Now that's a subnet mask. Now, how do we come up with a wildcard mask from this subnet mask? So what's going to end up happening is 255 is going to turn into 0. And here's the trick. What you will do to convert 240 into wildcard mask would be, we'll write down 255 minus 240. What does that give us? It gives us a value of 15. We'll place 15 right here, and then we'll go 255.255. So remember, in wildcard mask, 0 means I care, and 255 means I don't care in terms of bits. So now that you have a good understanding of wildcard masks, I think you guys are ready to jump on a command line. But let's be patient for one more second here so I can explain to you the lab topology. In this topology, we have Bob and Leah on our LAN segment of 10.1.1.0/24. That's to the left of our internal gateway router right here. That's what IGW stands for. And to the right of IGW, we have a switch, and that switch has an accounting server plugged in, and that switch also plugs into the LAN port of our Internet Edge router. That's what iEdge stands for. And then to the right of Internet Edge is an internet circuit coming in from our service provider that is allowing us internet access. This is how our topology is set up. And I'm going to use the same topology today to explain standard ACLs, extended ACLs, and named ACLs, because that makes it easier to constantly look at the same topology and refer back to it. Now that we have looked at the topology, let's look at the first lab. So here's the first lab. So we have a security policy in our network that suggests that Leah should be denied access to the accounting server on the LAN, and Bob should be denied access to the www server on the internet. Now, one more concept before jumping on the command line that I want you to understand is we have these requirements here in front of us. Where do we apply the ACL and in which direction? And let me explain. So the first statement says block Leah from accounting. So Leah's down here and accounting server is up here, right? How do we block Leah from accessing the accounting server? Now, where can we place ACLs? Where there's only two places where we can have ACLs in our network. Either the internal gateway router, or IGW, or the internet edge, or iEdge router. Now, accounting server happens to be closer to the internal gateway. So what we'll do is we'll have to apply an ACL on the internal gateway router. And by the way, this is a layer 2 switch, so we can't apply ACLs here. Okay, just to clarify. So now the next question is which interface? Because remember, ACL is not applied to the entire router. ACL is applied to the interface. Either we can apply it on fast 1/0 or fast 0/0. Where should we apply this ACL? Now, let's think back. If you guys recall, when it comes to standard access lists, the recommendation from Cisco is that we place the standard ACL as close to the destination as possible so we don't block traffic. Now, here's what it means. If I were to apply this access list on fast Ethernet 1/0 in the inbound direction, what's going to end up happening is, because standard ACLs only match on the source, Leah's IP will be blocked from accessing anything on the entire network, to the point that Leah won't even be able to ping Bob's PC. It's going to be completely cut off from all access to the network because we're applying this ACL really close to the source, and we don't want to do that. We have to apply it as close to the destination as possible. So through the power of deduction, we have realized that we can't apply it here, so we're going to have to apply it on fast Ethernet 0/0. Now, another thing that's important is, where should we apply it? In the inbound direction or the outbound direction on fast 0/0? Well, one thing for you to keep in mind is, as Leah traffic comes into the router, it comes into fast Ethernet 1/0. But the traffic goes out on interface fast Ethernet 0/0. So that means if we were to apply this ACL, it's going to have to be applied on fast Ethernet 0/0 in the outbound direction, because that's the flow of traffic in our network. If we applied it in the inbound direction, it's not going to work, because Leah sits on fast Ethernet 1/0 side, and the traffic is received on that interface and then sent out on the interface to the right, which is fast Ethernet 0/0. So this is very important, and the reason I'm spending some time here, guys, is because when I was new, this used to trip me up all the time. And I want to make sure it's crystal clear in your head how you're going to think through when you have a problem in front of you, how you're going to think through it and come up with a strategy to apply the ACL. Now, how about the second item in our security policy? Deny Bob from accessing the web server on the internet. Now, Bob happens to be right here on the left, and the web server happens to be all the way to the right on the internet. Now, to block Bob, where should we do that? On the IGW or iEdge? Well, remember, we have to go as close to the destination as possible, right? So we're going to actually have to apply Bob's access list on the iEdge router. And once again, which direction should we apply it in? If we do it in the inbound direction on fast 0/0, we may be cutting off Bob's access too soon. So what we need to do is actually apply it on fast Ethernet 1/0 in the outbound direction as the traffic leaves the internet edge router toward the internet. And that is essentially as close to the destination as possible based on the best practice recommendation. Now I believe we are ready to jump on the CLI. I'm on Bob's PC. It's actually a router, but I'm pretending to be a PC. Let's see if I can go ahead and ping the web server all the way through the internet. So I'll do ping 80.1.1.1. And sure enough, Bob, who happens to be on the leftmost side of our network, is able to ping a web server that happens to be on the rightmost side of our diagram here, which means the connectivity in the middle is all working for us. And let's run the same test on Leah's PC and see how that goes. And once again, we are successful. So both Bob and Leah have full connectivity all the way through our network. Now, let's look at our security policy. It says first, we need to deny Leah from accessing the accounting server. So as discussed earlier, I'm going to go to IGW, our internal gateway router, and I'm going to create an access list. So I'm going to type in configure terminal, and I'm going to create an access list. Here's how you create an access list. Access-list, and we have a ton of options here. Because this is a standard ACL, we're going to focus on standard ACL. We'll do access list 1 space question mark, and now we have the ability to either deny or permit. We're going to go ahead and deny access, and the source in this case happens to be Leah's PC, so we're going to type in 10.1.1.101, and we'll type in our wildcard mask. And because we need to match every single octet in the source, we're going to have to type in a wildcard mask of 0.0.0.0. That means match everything exactly. And that's it. Because remember, this is a standard ACL. So the only thing we can filter on is the source IP, which happens to be Leah's PC IP. So when I do that, I'm done creating my access list. The next thing we need to do is go ahead and apply the access list. Now remember, we are supposed to apply this access list as close to the destination as possible. So we're going to go to interface fast Ethernet 0/0 and type in IP space access hyphen group and type in the number of our access list, which happens to be access list 1, and then the direction. Is it going to be inbound or outbound? Well, I articulated earlier, because fast Ethernet 0/0 is where the traffic is going to be going out of from Leah's perspective, we're going to have to apply it in the outbound direction. And that's it. At this point, let me go back to Leah's PC here and see if I can ping the accounting server 10.2.2.99. And sure enough, I'm unable to do so. All U's mean unreachable. Now let's go back to the internal gateway router or IGW and type in do show access list command to display all the access lists on this router. There is an issue with this access list. Can you spot what the issue is? If you want to pause this video for a moment, go right ahead. See if you can spot the issue. Well, here's the challenge. We don't have a permit any statement at the bottom of this access list, and that is necessary. So what we should do is go back to global config mode, type in access list 1 permit any. Just to get some practice, let's go ahead and blow up or remove the previous access list. So we'll type in no access list 1. And what we should do now is type in access list 1 deny, and we can type in host. So this is a variation of what we did earlier. Remember before I typed in the exact IP address of Leah's PC and then a wildcard mask of 0.0.0.0? That's the long method. The short method is we choose the keyword host and we type in 10.1.1.101 and hit enter. And then to complete this access list, we should type in access list 1 permit any. And that should complete our access list. Now we can go ahead and type in show access list, and here we are. Now our access list is created properly. Now let's go back to Leah and see if we can get to the accounting server, 10.2.2.99. And we're unable to do so. The way we can verify that is by coming to the access list and typing in the command do show access list. You see the difference between before and after. Now what you will see is when I look at show access list, right in front of the statement that actually matched, you'll see how many packets actually matched this access list. So this is a quick troubleshooting and verification mechanism to ensure that your access list is working the way you intended it to work. So that's great. Now let's look at statement number 2, block Bob from accessing the web server. Now what we need to do is we should go to the Internet Edge router, go to global config mode and create this ACL for Bob. So we'll type in access list 1 deny host Bob's PC, and then we'll type in access list 1 permit any, because there's an implicit deny at the end of every single access list. It's invisible, you cannot see it, but it's a big gotcha, so keep that in mind. We'll go to interface fast ethernet 1/0, we'll type in IP access -group 1, and we'll do it in the outbound direction. And that should do it. So if I go to Bob's PC now and try to ping the web server, we're getting unreachables. So our traffic is being denied. But if I were to ping, for example, 10.2.2.1, which happens to be the LAN interface of the iEdge router, up until that point, I'm able to successfully reach various devices within my network. Now let's quickly go back to Leah and see if we can ping the internet server. Leah is unable to reach the web server on the internet. Why is that? Leah should have access to the web server. We only intended to deny Leah's access to the accounting server. Well, once again, guys, standard access lists are, in real world, typically they're troublesome because you see what's happening here is we applied the access list on this interface, fast ethernet 00 on IGW right here in the outbound direction. So what that means is Leah's access is not only cut off to the accounting server, but her access is cut off from all other devices on the network. That includes this link right here. That includes this link right here on the WAN, including the web server on the internet or any other device on the internet. Leah is essentially cut off from the entire network. The only device Leah can reach is Bob's network, or basically that LAN segment that it's attached to, but it is unable to communicate with any other subnet because of the access list. And that's why standard access list is a bad idea. And this is a perfect segue into the extended ACL. Now let's quickly shift our attention to extended ACLs. This type of ACL filters on the following 5 parameters: source IP address, destination IP address, source port, destination port, and protocol. Combined together, we call that a 5-tuple. And this makes extended ACLs highly granular because we are able to match on so many different fields within the IP packet header. Here are the extended ACL number ranges. We go from 100 through 199, and the expanded range goes from 2000 through 2699. Now, best practice design suggests that we place the extended ACL as close to the source as possible. This is the opposite recommendation compared to the standard ACLs. And it's for a good reason. Because we have so much granularity, we have the ability and flexibility to apply extended ACL as close to the source as possible. And here's the CLI syntax. So we go to global config mode, type in access-list space, we pick a number, then we say either permit or deny, and then we have matching parameters. Here's an extended ACL lab. So in this lab, what we're going to do is we're going to deny Bob from accessing the accounting server. Then what we'll do is we'll block Leah from accessing Telnet on both routers. We'll block both Bob and Leah from pinging the WAN link. We'll then perform edge filtering, denying RFC19 address space from the internet, and I'll explain why. And finally, we'll allow all other traffic. So that is our security policy. So let's get cracking on command line. Here I am on CLI. This time around, we're going to apply extended ACLs. So what I'm going to do is, first of all, I'm going to go ahead and delete the standard ACL we have. So I'll do show access-list and see the access list that I have that I need to go ahead and delete. Also, I'm going to quickly do show run and do section 00 to look at Ethernet 00. That's where I have the ACL applied. So I'm going to go to global config mode. First, I'm going to go ahead and delete the access list. So I'll do no access list 1. It's gone. Next thing I need to do is go under the interface and type in no IP access group 1 out. And now the access list is completely deleted and has been disabled on the interface. Now, what I would like to do next is create an extended ACL that allows me to create the security policy. Now, if you were to pay attention to the security policy, what we'll notice is that lines 1, 2, and 3 can be combined together. And because you're supposed to apply the extended ACL as close to the source as possible, we can combine these 3 items in our security policy and apply them on the IGW. So let's go ahead and get cracking. So the first thing we'll do is we'll type in access-list space question mark. Because this is an extended access list, we can start at 100. So I'll start at 100. And then we'll say deny because we're blocking Bob. And what exactly are we blocking? Now, in this case, we're blocking Bob from accessing the accounting server to begin with. So we'll say IP, and then we'll say host 10.1.1.100, and we're denying access to host 10.2.2.99, and that's it. That's the first item in our security policy. Now let's go ahead and cover the next item. Okay, now this one is going to be slightly different because we're denying telnet on both routers, which means we need to match on a TCP port. So here we're going to say TCP host 10.1.1.101, and I'll say host, and I'm going to basically have to cover different interfaces because Leah, if you think about it, Leah can telnet into IGW either on the LAN segment, or it can use the 10.2.2.2 address, or she can use the 10.2.2.1 address to get into the internet edge router, or she can use 64.13.232.137 address to be able to telnet. So we're going to have to block all those addresses. So to cover that, I'll go left to right. So I'll say host 10.1.1.1. That's the fast Ethernet 1/0 interface on IGW. And I'll say equal telnet is port 23. Next, I'll say access list 100 deny TCP host 10.1.1.101 to host 10.2.2.2 equal 23. The next statement is going to be deny TCP host 10.1.101 host 10.2.2.1 equal 23. And finally, access dash list 100 deny TCP host 10.1.1.101 host 64.13.232.137 equal 23. So these four statements should completely block Leah from accessing either of the routers, from using any of the IPs that are configured. So that's statement number 2 on our security policy. What does statement number 3 say? It says block both Bob and Leah from pinging the WAN link. So to do so, we're going to type in access-list 100 deny. And this time around, we're going to say ICMP. And we're going to say host. Let's start off with Bob first, 10.1.1.100. And we're going to type in host 64.13.232.136 or 137. Hit enter. And I'll type in access list 100 deny ICMP host 10.1.1.101 to block Leah from being able to ping the WAN link. So I think at this point, our access list covers the top 3 items on our security policy. And if you remember, the last thing we always want to have is permit IP any. So now let's go ahead and do show access list to see how our access list looks like. That's a pretty decent size access list. And as you can see, we have 8 entries in our access list. The first entry is denying Bob from accessing the accounting server. Entry 2 through 5 is blocking Leah from telnetting into either of the routers. Entry number 6 is blocking Bob from being able to ping the internet edge WAN link. And statement number 7 is blocking Leah from accessing the internet edge WAN link. And then we have permit IP any. So at this point, the access list is created. Now we need to go ahead and apply the access list. Now, in this scenario, because we apply this as close to the source as possible, we're going to apply this access list on fast Ethernet 1/0 and IGW, which happens to be directly connected to that LAN segment where Bob and Leah are. Now that we have created our access list, let's go ahead and apply it to fast Ethernet 1/0, and we'll say IP access group 100 in the inbound direction. Let's go back to Bob, and the very first thing we want to do is ping the web server on the internet. Make sure we have connectivity all the way through. And sure enough, we can ping all the way through, which means we shouldn't have any issues in between. So that's good. Now, let's go step by step. So our security policy said Bob should be denied access to the accounting server. Let's see if that's the case. Let's ping 10.2.2.99. Sure enough, the accounting server is unreachable for Bob. Now, how about the other IPs in the same subnet where the accounting server is? For example, 10.2.2.2 on IGW or 10.2.2.1 on iEdge. Let's see if Bob can ping those. 10.2.2.2. Sure enough, looks good. 10.2.2.1, sure enough. So as you can see, it's very precise, the extended ACL. It only blocked access to the accounting server, yet on the same subnet, Bob is able to reach other devices. So that's beautiful. Standard access list doesn't allow us to do that. Now let's go to Leah and see if Leah is able to ping the web server on the internet all the way through. And let's see now if she can telnet into 10.1.1.1. Nope. Destination unreachable. It was actually denied. How about 10.2.2.2? Nope. How about 10.2.2.1? Nope. How about 64.13.232.137? Nope. Leah was denied access to telnet on either of these routers. That is beautiful. So our security policy is looking pretty solid. And finally, neither Leah nor Bob should be able to ping the WAN link. So let's do ping 64.13.232.137. It says unreachable on Leah's PC. How about Bob? Ping 64.13.232.137. It says unreachable again. Now let's go ahead and check out that ACL that we created on IGW. Let's do show access list and look at all these beautiful matches. Don't you love that? Pretty much every single item on our list, there is a match, which means our ACL is working beautifully, just the way we intended it to work. Don't you love it when all your hard work pays off? That's awesome. So at this point, we have taken care of the first 3 items. Now, item number 4 on our security policy is a unique one. It says perform edge filtering, denying RFC 1918 address space from the internet. So what does that mean? Let me explain what that means. So this is part of what we call an infrastructure ACL. Okay? You should Google it and you'll find out what that is. Okay? It's you'll find a link to a Cisco document that gives you exactly what you need to configure. But this right here is a subset of that infrastructure ACL. So what that means is, because we have RFC 1918 addresses configured on our LAN, right now we're only using the 10 subnet, but nothing is stopping us from using the 172 space or the 192.168 space, right? What we should not expect is any of the RFC 1918 private IP address space to be showing up from the internet. Because if that traffic is coming from the internet with private space, it means the traffic is being spoofed, and most likely a bad actor or a hacker is trying to break into our network. So by applying an edge filtering at the edge of our network, which in this case would be the internet edge router, we can create what's called anti-spoofing on our network, and it will block private IP addresses from showing off the internet. Now, we should allow our private IPs to go out to the internet, but not the other way around. Traffic shouldn't come back from the internet with the source of private IP address space, because that would be a security violation. So let's go ahead and configure that on the internet edge. So here I am on the internet edge router. I'm going to go to global config mode and I'm going to create an extended ACL, access list 100. I'm going to say deny, and let's get started with the first entry in our ACL. This would be deny IP 10.0.0.0, which is 0.255.255.255. That's a wildcard mask, and the destination would be any. The next entry in our access list will be deny IP 172.16.0.0, and with a wildcard mask of 0.15.255.255 space any. And the third entry will be access list 100, deny IP 192.168.0.0, 0.0.255.255, any. And the final statement in our ACL will be access list 100 permit IP any. That's it. We have now created our access list. Well, where should we apply it? As always, as close to the source as possible. So I'm going to go ahead and type in internet fast 00, and I'm going to say IP access list or access group 100 in. As a matter of fact, that's not going to work. It should actually be the other way around. So I'm going to go ahead and remove it. I'm going to exit, go to interface fast ethernet 1/0 and type in IP access group 100 in. So basically, we should be expecting this traffic to be coming from the internet. So we have to apply it to the internet facing interface, which happens to be fast ethernet 1/0. Okay, so that's it. At this point, we have applied our access list. Let's do show access list. And it's right here. Now let me go back to Bob and ping 192.168.1.1, which happens to be an IP on the internet. Now, one thing to clarify is this IP is not configured in our infrastructure, as you can see. What I did was I created a couple of loopback interfaces on the internet router that has these IPs to demonstrate a point. Now let's try to ping 172.16.1.1. And this basically is simulating that if somebody is coming from the internet, that traffic will be denied. And I'll prove that to you when I show you the matches in the ACL. And finally, we'll do ping 10.20.20.1, which is not in our infrastructure. Okay, but once again, it's a loopback I created on the internet router to simulate somebody on the internet. Now let's go ahead and look at our access list again. And sure enough, you see what happened? When Bob was trying to ping any of these IPs, they were denied access. They were actually denied access in the reverse direction. When the traffic is coming from the internet edge router dropped that traffic because we told it to do so. Because the traffic that's originated in the RFC 1918 private address space should never be received from the internet. So that's it. And we're allowing all other traffic. So let me prove that to you. If I go back to Bob and ping 80.1.1.1, sure enough, it's successful. So we can ping the web server on the internet, but everything else is being denied. If I were to do show access list again, sure enough, when I ping the web server, you see there's a match on that entry in our ACL. That wraps up our extended ACL section. Now let's quickly shift our attention to named ACLs. Now, named ACL leverages either a standard ACL or an extended ACL. There are three major differences, though, when it comes to named ACL compared to numbered ACLs. Names are easier to remember, plus they can provide context. So what that means is, if you remember, when we created access list 100, what does the number 100 actually mean? So the one who created the ACL, you would know, but let's say a year later, another engineer in your organization is looking at that ACL, it's going to be hard for them to decipher what that ACL is designed to do. But if it's a named ACL, you'll see in a moment when we go to CLI, when we create named ACLs, that they are contextual and they provide much better understanding of what the ACL is trying to accomplish. Next, named ACLs are hierarchical in nature. So what that means is, previously we created our ACLs in a global configuration mode. What you'll see is when we create the named ACLs, we go under a config-ext-network ACL mode. Okay. It could either be EXT or STD for standard. We'll talk about it in a moment. And finally, it's easier to edit ACL, meaning you can delete individual lines or you can add new lines, and it's easier to manipulate in a named ACL, whereas with standard or extended ACLs that are numbered, you'll actually have to go back and blow up the entire ACL in order to add or remove some entries within the ACL. Which means you have to go to the ACL, show ACL on your router, copy the entire ACL in a text pad or notepad, and then go to the router, delete it, then copy the entries from your notepad, add that new entry or delete that entry that you want to delete. As you can see, there's a lot more involved in doing that. It's a lot easier to make changes to named ACLs. Here's how the CLI is going to look like. We're going to go to global config mode and type in IP space access hyphen list space standard, and then we'll give it a name. And what's going to end up happening is the prompt will change from global configuration mode to standard network ACL mode, as you can see on your screen. And the other type of named access list is IP space access hyphen list space extended space the name of the ACL. And then once again, the prompt changes from global config to extended network ACL mode. Now we'll get to look at this on a command line in a moment. The security policy is identical to what we had previously. So what we'll do is we'll go back to the command line. We'll delete the previous ACLs we had created on IGW and iEdge and go ahead and create brand new access list that is a named access list and go from there. To do so, let's first of all go ahead and remove the access list from the interface that it's applied to. The previous access list, right? The numbered extended access list. And we'll also say no access list 100. That's it. That access list is completely gone. We'll do the same thing on Internet Edge. So I'll go to Fast Ethernet 1 and say no IP access group 100 N. And the next thing I would like to do is remove the ACL. So I'll say no IP, no access list 100. That's it. Our access list is also gone from the Internet Edge routers. Let's quickly do show access list as a quick verification on both routers. Do show access list, and sure enough, the access list is gone from both IGW and Internet Edge. Now let's go ahead and configure our named access list. We'll first start off with IGW, and we'll call this IP access list. So you see the difference here is instead of saying access list, we say IP space access hyphen list space extended, and we'll say deny dash Bob dash and dash Leah. So as you can see, now we're seeing very clearly that this ACL will deny Bob and Leah access to certain things on our network. So as you can see, we can see the value of a named ACL. It provides context to what the ACL is intended to do. So we'll first type in deny IP host 10.1.1.100, that's Bob, to host 10.2.2.99, that's accounting server. We'll then say deny TCP host 10.1.1.101, that's Leah, to host 10.1.1.1, port 23, that's Telnet. And we're then going to go ahead and say deny TCP host 10.1.1.101 because it's still Leah, to host 10.2.2.2 equal 23, that's Telnet. Once again, deny TCP host 10.1.101 host 10.2.2.1 equal 23. And finally, deny TCP host 10.1.101 host 10 64.13.232.137 equal 23. We'll also deny ICMP traffic, which is ping. First, Bob will be denied ping access to 64.13.232.136 segment. So it's a /30 segment, as you can see. So we'll do 0.0.0.3. And we have one more deny statement. This time we're going to deny Leah access to the same segment. So not only it can't ping the internet edge router's IP, but also the provider edge router that's on the internet. Okay, that's what we're trying to do. We're blocking that entire destination subnet of /30 on the internet, which happens to be for us 64.13.232.136. And that's it. And the final statement here will be permit IP any. That's it. If I do show access list, now you can see our access list says we're denying Bob and Leah. And it's very clearly articulated what's being denied and what's being allowed. And what we're going to do now is go ahead and apply this. Where are we going to apply this, guys? Do you guys remember? As close to the source as possible. So we'll do interface fast Ethernet 1/0, and we'll say IP access group. And now you have to type in the name instead of a number and specify the direction in the inbound direction on internet gateway. And do show access list. At this point, there are no entries that are matching, but let's go ahead and test it out. So I'm on Bob now. Let's see if I'm denied access to the accounting server, 10.2.2.99. Sure enough, I'm denied access to the accounting server. Now, Bob, let's see if Bob can ping the web server on the internet. Sure enough, he's able to successfully do so. Now let's go to Leah and see what the situation is on Leah's end. So is Leah able to ping the web server on the internet? Sure enough, that means we have connectivity all the way through. And also, let's now see if Leah is able to telnet into IGW on any of the IPs that it has. 10.2.2.2. Nope. It can't get to IGW. How about Internet Edge? Let's do 10.2.2.1. Nope. It's being refused access. And now let's try 137. It's being refused access. Now let's see if the third item on our security policy works. Are we able to ping the WAN link from Leah or Bob? You shouldn't be able to. So let's do ping 64.13.232.137. Nope, we're getting unreachable. And Bob should be seeing the same thing. Ping 64.13.232.137. We're getting unreachable. So that is beautiful. It seems like we're able to take care of all the items, at least the first 3 items on our security policy. And let's go ahead and do show access list, and absolutely beautiful when I see matches everywhere. That means my access list is working like a charm. So that's awesome. Now what we want to do is we want to go to our iEdge router, Internet Edge router, and go ahead and create the edge filtering denying private IP addressing space of RFC 1918 off the internet. So in the global config mode, we'll type in IP access list extended, and we'll call it RFC 1918-filter. So you see how beautiful this is? We know exactly what this ACL is designed to do. Now we're going to say deny IP 10.0.0.0, 0.255.255.255, any, then we'll say deny IP 172.16.0.0, 0.15.255.255, any, and deny IP 192.168.0.0, 0.0.255.255, any, and the final statement is going to be permit IP any. And that wraps up our access list here. Let's see if it's doing what we think it should be doing. It looks good. Let's go ahead and apply it to Internet Edge. Now, let's think through this. Where do we need to apply it? We need to apply it on the WAN interface. Okay, the internet-facing interface, our Internet Edge router. So we'll say fast 1/0. We'll say IP access group. We'll type in the name. Ideally, copy and paste it instead of manually typing it in, because you may make a mistake and that's not a good thing, and type in the keyword in for the inbound direction. At this point, if Bob were to ping any of those IPs that are on the loopback of the internet router, he shouldn't be able to ping those. So let's test that out quickly. 172.16.1.1, 192.168.1.1. Now we should be seeing a bunch of matches on our Internet Edge router. So let's go ahead and do show access list. And sure enough, we're seeing a bunch of matches on the denial of traffic that is being sourced from the RFC 1918 space out on the internet. Now let's go to Bob and ping the web server, and sure enough, we are able to do that. And now if I were to go back and do show access list again, we're seeing a permit IP any match, which happened to be the 80.1.1.1 address that I just pinged. So that wraps up our named ACL section. Now let's shift our attention to a real-world perspective on ACLs. So remember, deploy standard ACLs as close to the destination as possible. Deploy extended ACLs as close to the source as possible. More specific statements in an ACL should be at the beginning or at the top of the ACL. And remember the concept of first match logic. So if you think of an ACL as a giant list, the first entry in the list has the highest preference, and the last statement in that list has the lowest preference, meaning if the match is found in the first statement, that's it. Router stops checking the ACL. At that point, it's done processing the ACL. Also, always have a permit statement at the end of each ACL, because there's an invisible or implicit deny at the end of each ACL. Also, think deeply about the placement or direction of ACL. Always ask yourself, which interface should you apply the ACL to, and in what direction should the ACL be applied? Next, you can have two ACLs applied to an interface. So you can have one ACL applied in the inbound direction and one ACL applied in the outbound direction on the same interface. But you cannot have more than one inbound or more than one outbound ACLs applied to the same interface. And if you want to disable the ACL without deleting it, all you have to do is just remove it from the interface that it's applied to. So the way you do is you go into the interface configuration mode and you say no space IP space access dash group space the ACL number or name and then the direction. And this perspective is very important because you'll see when you start configuring ACLs, these bullets, I suggest you print this out and keep it in your back pocket as you're configuring ACLs, either in a lab scenario for your CCNA studies or CCNP studies in future, but also from a real-world perspective as you're applying ACLs in a production environment at work. These tips will save you a lot of pain and suffering. Welcome to CCNA 200-301 course. Today, I'm going to cover Section 5, Part 2 of the CCNA exam, Security Fundamentals. Today's video is dedicated to doing a deep dive in security. This is going to be one of the most exciting videos, I promise you. Let's go. Here are the topics I plan on covering today. First, network security overview. Second, common security threats. Third, security defense techniques. Fourth, AAA. Fifth, security features. And finally, I'll wrap it up with security devices. Now, before I get into any of the topics, the first thing I want to cover today is a couple of studies and stats by National Cybersecurity Alliance, plus Gartner, and ISC2 Workforce Study in 2019. Cybercrime damage estimated to hit $6 trillion by 2021. Every 39 seconds, there's a hacker attack. 95% of cybersecurity breaches happen due to human error. 25 billion devices connected to the internet. That's the Internet of Things, or IoT explosion that we're experiencing right now. And in 2018, hackers stole 500 million personal records. Now, at this point, you might be saying, okay, Naj, stop it. We get it. We see the trend. It's very depressing. Do you have any good news to share, or are you going to keep hitting us with all this negative stuff? And my answer is, I'm not sharing these stats to scare you or to make you feel depressed. On the contrary, I wanted to demonstrate the fact that we have so many problems, but with every problem, there's an opportunity. Currently, there are over 4 million jobs available in the cybersecurity realm that are unfulfilled. So there's tremendous opportunity for you to go out there and crush it. Now let's shift our attention to network security overview. Let's say you just started a brand new business. You got 3 employees, Bob, Jen, and Dan, and they need access to a certain server. So let's say this is an accounting server that they need access to update records and maybe sell coffee, manage inventory, things of that nature. Now, this is what we call an enterprise closed system. As you can clearly see, this network is not connected to anything outside. It's a completely closed system because you have internal employees talking to an internal server connected to an internal switch. And this is what we call a perfect security. And the idea here is that if you're not connected to the outside world, you're perfectly secure. To take this concept even further, if you want an absolute perfect security, completely disconnect all of your devices from the internet. Disconnect your computer from Wi-Fi or wired connection, whatever have you. That will give you the most perfect security that's out there. But you see a problem with that? The problem is it is perfect security, but you don't have access to anything. And that's the delicate dance that we're going to talk about between security and availability. You want the ability to be able to connect to the outside world. You want to be able to access things while maintaining security in your environment. How do we do that? That's what today's session is all about. Now, let's take the previous network to the next level. Let's add more complexity to our network. We still have Bob, Jen, and Dan, but now things are getting to the next level. We have our server move into a DMZ segment. We also have an extranet segment to connect to our extranet business partners. So for example, to fulfill coffee orders and things like that, instead of having to call those people, we may just have a network connection into our partner so we can place orders and transact business over that extranet. And we may also have a wide area network connection to be able to connect to the internet. And that may include connecting to certain web servers and things of that nature. Now, this is a very different environment compared to the previous picture we were looking at, where we weren't connected to anything outside. Here, we're connecting to a lot of outside networks, and out on the internet, we may have bad guys. On the extranet within the business partner network, you never know. Maybe they have a disgruntled employee who's not too happy with the business, and they might want to hack anybody that's connected to that extranet network. And you never know. Someone in your own internal network, let's say Bob, could be a gray hat guy, where he's a good guy during the day, but maybe a bad guy at night. So what you may want to do is you don't want to assume that it's okay to allow people access to everything that are on the trusted side of your network, which in this case would be the local area network. The LAN would be considered the trusted side of the network, right? You want to make sure you're scrutinizing the LAN, the DMZ, which stands for Demilitarized Zone, the WAN, wide area network, and the extranet. And this is what's called an attack surface. Now, we're going beyond CCNA here, but I think it's important for you to understand as we start talking security as a larger, more comprehensive topic, is the fact that this router has 4 different interfaces, and that represents an attack surface. We can have an attack from a wide area network. We can have our extranet partner attack us. We can have one of our employees launch an attack. And even the DMZ segment is not fully protected, depending on how we have our access control lists set up and the firewall policies and things like that. There may be some gaps that bad people or bad actors can take advantage of to be able to steal information and steal credentials and wreak havoc in our environment. Here's some terminology you want to familiarize yourself with when it comes to security. The term vulnerability. It's a weakness or a flaw in the network or a system. An example could be a bad piece of code embedded within an operating system. So for example, your iPhone, it gets an update every couple of days, or Android, or Microsoft Windows, or Mac, you name it. Any operating system that's out there, you'll constantly see these patches being released because there's always some vulnerabilities embedded within a code. And if you look at something like Windows or Mac, those OSs have potentially millions of lines of code, and it's very easy for a software developer to make a mistake. It may be an honest mistake, but it could end up causing your business a lot of money. So that's a vulnerability. That mistake, that weakness, that flaw represents an attack surface that a bad actor can take advantage of to get into your network. The other term you want to think about and know and be familiar with is exploit, a tool used to target vulnerability in order to gain control of the network or system. An example could be a hacking app like a keylogger designed to steal information. A lot of keyloggers, what people do is they put them on a thumb drive, on a USB thumb drive, and then they may go ahead and plug that USB thumb drive in your PC or your Mac. And the next thing you know is every single key that you're typing in on your keyboard is now being captured. And this way they can steal information. So for example, if you went to bankofamerica.com, what follows is most likely your username and password. They can figure that out. So as you can imagine, that's bad. And that's what an exploit is. It's a tool. The next term you want to be familiar with is threat. It's an intent or action that leads to a disruption of it or a destruction of a system or an asset. Who performs this action? This action is performed by a threat actor or a hacker. An example is a hacker exploiting a vulnerability to steal credentials. So we talked about exploit. That's a tool. We talked about vulnerability. That's a weakness. A hacker can take advantage of a weakness in our system and use a hacking tool to steal credentials, which could be keylogger. And the final term I want you to be familiar with is risk. The potential for loss, damage, or destruction of a system or network as a result of a threat exploiting a vulnerability. So this builds on all the different terms that we have learned so far and connects them together in a connective tissue. An example could be a revenue-generating website being unavailable to customers. So that's a risk. So let's say Amazon.com, one of the most popular websites in the world for placing orders. Can you imagine Amazon.com being unavailable because somebody hacked or attacked Amazon.com? That would be absolutely terrible, because that would mean potentially tens of millions of dollars worth of loss just maybe in a matter of hours. So what we need to do is evaluate risk. And based on that risk profile, we want to figure out how to protect our network. Now that we have looked at the terminology, now let's shift our attention to common security threats. But before we do, though, I want to bring something to your attention. There was a really nice piece on CBS News on 60 Minutes that you can search on YouTube. It's available for free on ransomware. And they talked about how cyber criminals hold data hostage and why the best solution is often paying a ransom. I mean, that's insane. They're actually suggesting that you should go ahead and pay the bad guys. And check this out, guys, if I continue reading this. Targets have included hospitals and municipalities, but the FBI says anyone on the internet should expect to be attacked by cyber criminals. That's one of the government agencies admitting that we are all vulnerable. Another piece of article I want to share with you guys by New York Times. Colonial Pipeline is a company on the East Coast. They are the operator of fuel lines. They were actually hit by a ransomware attack, and they ended up paying $5 million to be able to get their data back. And we'll talk about how those attacks happen and some of the mechanics behind them momentarily. But check this out. The payment clears the way for gas to begin flowing again, but it risks emboldening other criminal groups to take American companies hostage by seizing control of their computers. So in other words, this type of attack allows the bad guys globally to get inspired and pay more attention to developing more advanced type of ransomwares, because this was a successful attack. They were actually paid to allow Colonial Pipeline to get their data back. So that is very serious. And as a matter of fact, they had FBI involved. And I believe FBI informed Colonial Pipeline that the only way to get their data back is to actually pay the bad guys. There was no other way around it. So that is very serious, guys. So now that I have your attention, let's look at a couple of different type of attacks. So the first attack we're going to look at is called address spoofing attack. So in this attack, what we have is a hacker. And let's imagine we have a corporate server, and we'll call that a target. And the hacker would construct an IP packet with a source IP of 200.21.199.250. Now, the IP in red in our IP packet, take a look at your screen. It's not available anywhere. It's some fictitious made-up IP by the hacker. And there's a reason why it was crafted this way. You'll see it in a moment. And the destination IP is set to 199.1.9.24, which is our target machine. So that packet is sent to the target machine. And what does the target machine do? It sends an IP packet reply. So the source IP then becomes the corporate server IP, but the destination IP is the source that the hacker had initially set, right? So basically, this packet is going nowhere. It's going in no man's land. And why is this type of attack bad? Well, it's using up resources on this corporate server. Now, this is one example and one packet. Imagine millions of packets or tens of millions of packets being sent to a corporate server, now that would be really, really bad. And once again, the idea is to just exhaust the system of its resources, CPU resources, memory resources. So that's the address spoofing attack. The other type of attack is called denial of service or DOS attack. Here we have a bad guy. We have a target corporate server. In this case, what the bad guy does is crafts a TCP SYN message. So in a TCP three-way handshake, as you guys know, the first packet is TCP SYN. Once again, it sets the source IP to a fictitious IP that doesn't exist. Now the target server gets that message and it sends what's called a TCP SYN-ACK. That's the second stage in our three-way handshake. And once again, that IP is going nowhere. That packet is going nowhere because it's a fictitious IP. That IP doesn't exist. But what it's doing on our server is that it's using up server TCP state table. So once again, CPU and memory resources on this server are being abused to the point that our state table gets full and we can no longer provide service to legitimate customers that might need access to this corporate server. And this is also called a TCP SYN flood attack because we're flooding the corporate server with the TCP SYN messages. This is an ugly one. The next level up from the DOS attack is called distributor denial of service or DDoS attack. That's another very nasty one. Here we have a hacker who installs a CNC server or a command and control server. This is also called a botnet. And then we have a target machine, which once again is a corporate server. And what this bad guy does is scans the internet looking for machines that don't have security. So literally, like they scan millions and millions of machines on the internet, and people who don't have a firewall at home and have zero security at the edge of their network, bad guy goes ahead and controls those machines by infecting them, and they turn into bots. And sometimes these bad guys can send some sort of like an email or some sort of embed a bot into a website. It can infect machines in different ways. But the ultimate result is that these machines turn into bots. And at that point, what the bad guy does is that instead of sending a single message to the target server, it now has all these bots that are part of a botnet. And with a single command, all of these bots can send message and bombard the target server. I'm only showing 5 machines, but imagine 500 machines or 5,000 machines sending messages to a target machine. And you can also think of these bots as a zombie. That's another term that you will hear when you read articles and things like that. So keep that in the back of your mind. It's like a zombie, an army of zombies, right? Attacking humans or victims. And these are also called victims because these are innocent victims. They have no idea that their machines are being used for nefarious purposes. And the bad news is that if these attacks are really bad, sometimes FBI or CIA could actually be knocking on the door of these people that are running bots on their machines without even knowing, without even realizing that they're causing this DDoS attack. So that's a really, really nasty one. Another type of attack is called reflection and amplification attack. Here, once again, we have a bad guy and we have a target machine and we have a reflector in the middle. So now what's happening is, if you guys recall, the spoofing attack, once again, the IP is spoofed. The source IP is not the hacker's IP, but the source IP is the target machine's IP. Now watch, it's a clever attack. So that packet initially is sent to the corporate server. Corporate server then sends an IP packet reply to the machine that it's supposed to send the reply to, which happens to be the target. But remember, the original packet didn't come from the target, it came from the hacker. So the corporate server in the middle is once again an innocent victim who doesn't know what's going on. It's doing what it's supposed to be doing. It gets an IP packet, it sends an IP packet reply. But it's called a reflector attack because the guy in the middle becomes a reflector. Once again, the previous example that I was showing you of the DDoS attack, you can also think of this corporate server. Instead of a corporate server, imagine a bunch of bots in the middle acting as reflectors and then doing this on a massive scale. That's another really bad one. And now let's talk about man-in-the-middle attack. That's a really interesting one and a pretty sophisticated type of attack. So to the left, we got a client. To the right, we got a server. In the middle, we got a default gateway. The guy on the left sends an ARP request saying, who has 172.16.1.254, because our client is looking for that server IP. So it sends that message to the switch. Well, what does the switch do? If it doesn't have a MAC address already learned, it goes ahead and floods that packet out all ports. So every single port gets flooded except the port that it initially received the message on. That's how switches behave. And eventually, that server will get that request and reply back saying, here is my MAC address. Ultimately, that's what we're trying to do, right? That's ARP, Address Resolution Protocol. We have an IP address of the other machine, but we do not have a MAC. And in order to communicate on a local area network or a LAN, we need to be able to have a MAC address so we can craft our frames to be sent to the machine on our LAN. And this would be the normal traffic flow. Up until here, it's all good. It's all green. It's all kosher. There's nothing bad going on. But now let's talk through what happens in the case of man-in-the-middle attack. So once again, the client sends an ARP request. Now what ends up happening is both the server and the bad guy gets the ARP request, but let's assume that the bad guy got the request before the server did. And what the bad guy is going to do is going to send an ARP reply saying, hey, by the way, if you want to talk to the server, send that traffic to me. And it provides its own MAC address. Well, what ends up happening then is here's how the traffic flow looks like. Client sends data to the hacker, and then the hacker modifies the data and forwards it over to the server. Now, check this out, guys. It's a sophisticated attack because the guy in the middle is trying not to disrupt the service. He's trying to be, quote unquote, invisible through this transaction. He does not want to give the client or the server an impression that there's something malicious going on here. And client doesn't know because the client is completely clueless. Client thinks, hey, this is the way it's supposed to work. And the server doesn't know any better. The server also continues to forward traffic through the guy in the middle. And that's what the man-in-the-middle attack is all about. And what this ultimately does is it creates a condition called ARP poisoning, where the ARP table on the client and the ARP table on the server gets poisoned because we have the wrong information in our ARP tables respectively, and we are none the wiser. Now let's shift our attention to malware. The very first type of malware that I'm pretty sure you're most familiar with is called a virus. A malware designed to spread from one device to another, and virus depends on the host to activate it, very much like a human virus. Right? So for example, you may have the cold virus sitting in your throat, but until you provide certain conditions for that virus to activate, it will just sit there dormant until you activate it. Similarly, computer virus depends on the host to activate it. You as a host has to do something for that virus to be able to spread itself from one machine to another. The other type of malware is called worm. That's a nasty one. A worm is a standalone malware designed to self-replicate and propagate. It's activated independently on its own. Now the difference is, in contrast to a virus, a worm just completely independently activates itself without any human intervention. So it makes it very, very scary. The third type is a Trojan horse. So just like that city of Troy, Trojan horse, if you have watched the movie Troy, I'm sure you know all about Trojan horse. It's a malware disguised as a legitimate software. It could be used as a spyware for spying on the user, for example. And Trojan horse must be installed by a user to activate. Once again, Trojan horse acts very similar to a virus, but it's disguised as a legitimate software. Okay, that's the difference. That's why they typically tell you that do not download random pieces of software on the internet, because you might inadvertently download a Trojan horse that might be a spyware running on your machine. And the final type of malware that I want to touch on is the nastiest of all. It's called ransomware. And it's currently the #1 threat that's out there in the wild. It's a malware designed to encrypt files on a system, making them inaccessible, and then the hacker demands a ransom to decrypt them, hence the name ransomware. Ransomware could infect the system in the form of Trojan horse or a worm. So ransomware is a broader category that actually encrypts files, but a ransomware could also include a Trojan horse or a worm. Now, whoa, what happened to our machine here? Relax, guys. This is just a screenshot. This is what happens when you get hit by ransomware. In this case, somebody's website has been hit with a ransomware. It says, oops, your website have been encrypted. And it says, these are all the files that have been encrypted. It says to recover them, you can certainly do so, but you must pay. And then it shows you how you pay. And there's also a little timer to the left, as you can see. Typically, they give you 24 hours or 48 hours, or there's some sort of sense of urgency attached to this threat. And basically, they're holding your machine hostage. And if you don't get back to them, then all of your files get deleted. And here they're asking for a payment to be made in Bitcoin. Typically, that's how they would want you to pay, in a form of Bitcoin, because it's hard to trace. Like if you sent money with a credit card or through a bank transaction, it can be tracked. But with Bitcoin, it's a lot harder to track. Now let's look at security threats from a bit of a different angle, human vulnerabilities. So as you can see in the picture here, you have an average looking guy who could be a super villain. You just never know. So the first type that I want to talk about, and it's a very sophisticated type of attack, guys, it's called social engineering. Hackers use social skills with malicious intent to steal information. An example could be a cyber criminal pretending to be an IT help desk. So for example, if you have ever worked in a help desk environment, you know how help desk works. And let's say if you're a bad guy, you can call some random company XYZ and pretend to be an IT guy and use sophisticated IT help desk lingo and fool that person into believing that you're indeed an IT guy, and they may give you their username and password, and then you can use that information to break into their machine or their account and then compromise their machine and wreak havoc within that network. The other type of attack that falls under the umbrella of social engineering is called phishing attack. It's a fraudulent message, typically in a form of email, social media message, a text message, or a call, sent pretending to be from a legitimate business to trick a victim into revealing sensitive information. An example could be email demanding immediate IRS payment. So typically during tax season, March through April timeframe, you'll see that there's this increase in these type of attacks where these bad actors on the internet start sending these demand notices pretending to be IRS, and they go, if you don't make a payment to IRS, here's the amount of money you owe in taxes. If you don't pay this within the next 24 hours, you will have FBI busting through your front door, and they put a fear of God in your heart. And for people that are not familiar with this and that are not very security centric, they may freak out and they may end up paying the bad guy. There's another attack called dictionary attack or a brute force attack. Now, this is a type of attack where a relentless attack is launched to find victims' password. An example here could be a dictionary attack tool used for guessing password. So for example, if your password is baseball123, this is a perfect candidate for a dictionary attack because it's a dictionary word and then the numbers are very straightforward, 1, 2, 3. If you had a strong enough machine that had really strong horsepower, you can use a dictionary attack tool to be able to guess that password in a matter of minutes. And another type of attack is called a physical security attack. And that's a type of attack used to break into a physical location using human vulnerability or a physical parameter flaw. So for example, someone pretending to be an employee, and let's say you use your badge, electronic badge, to get into your office, and all of a sudden you see somebody rushing behind you, and they might be carrying a box, and they go, "Could you please open the door for me? I left my badge in the car, and I'm here to just drop off this box, and I'm gonna walk right out." You may allow them to go in. Now, they took advantage of your human vulnerability, right? You didn't check their badge and they kind of pressured you into walking into your office because they were carrying a box and you felt like, oh my God, I don't want to inconvenience them and ask them for a form of identity. I'm just going to let them in. They gotcha. So these are some of the things you want to think about. And another big one, guys, is watch out for recently fired or disgruntled employees. If somebody is not happy at work and they're highly skilled, especially in the security department, or advanced networking skills, or if you fired somebody recently, you gotta watch out. They might launch an active attack and you need to have measures in place to protect yourself. So some of the things you can do is, as soon as an employee is terminated, make sure their access is immediately removed from the system. So make sure it's all automated. You don't need a lot of human intervention. The only human intervention required will be somebody in HR tagging that employee to be terminated. As soon as they tag that employee, Active Directory and all those backend systems automatically just go ahead and remove access for that employee from all the different systems that employee had access to. And according to the US federal agencies, FBI, CIA, NSA, most cyber attacks are launched from within the organization. So while we invest a lot of money in buying bigger and beefier firewalls, in spending millions of dollars in protecting our organizations from an outside threat, you never know. The threat might actually be lurking within your four walls. And what you need to do is not only look for threats from outside, but also have a mechanism in place to look for threats on the inside of your organization. And with that, now let's shift our attention to security defense techniques. The first thing you want to do is develop a security policy. And the way to do that is you define security standards. You develop a policy for protecting companies' physical and IT assets. In most companies, a chief security officer or a chief information security officer, also known as CISO, is responsible for developing the security policy. So that's the most important step, guys. You need to make sure that you have a security policy developed. Then what you do is you take the next step, user awareness and training. That means you design a formal training program as part of your security policy to educate users on how to protect themselves against various threats that we talked about so far, like malware, social engineering, etc. Make security training and certification mandatory for all employees. Make that part of your HR onboarding plan, for example. And then the final step would be physical access control. So which could mean providing a security badge to employees. Limit access to various locations in your company, such as an office, data center, etc., by providing badge access to employees, contractors, and customers. Now, employees may have a lot of access to all the facilities in your environment. Contractors may only be limited to certain locations. And customers may only be given temporary access while they're accessing or attending a meeting at your site, for example. And electronic badge access also provides an audit trail. So a big benefit of having a badge access is it leaves an audit trail. So when somebody walks into a building, when they sign in, when they sign out, you have all those details captured through an audit trail, because the badge identifies who the user is and when they signed in and when they signed out. And if anything malicious happened in that time frame, then at least that audit trail helps you pinpoint if they did something bad while they were physically there on site. And finally, automate the access removal of a terminated employee. I cannot emphasize that enough. Like I said before, as soon as an employee is terminated, make sure not only their access to different systems is removed and IT assets is removed, but also their access is removed to your locations. Because also remember, we hear in the news all the time, bad guys going out there, an active shooter type situation, right? It's absolutely horrific. It's nightmarish. And the best way to protect against that is make sure they don't have access to the office to begin with after they have been terminated. Now, let's look at authentication mechanisms. So the most basic rudimentary form of authentication mechanism that's been around since 1980s is a password. So what you have is a combination of a username and password. Make sure you develop a robust password policy. When you design your security policy, password policy should be a subset of your security policy. And in that policy, you should dictate that you should have long passwords that change periodically, combination of upper and lowercase, alphanumeric, and special characters. And promote and facilitate the use of a password manager within your organization. Personally, I use 1Password, but you could use Dashlane or LastPass. And the whole idea with the password manager, if you're not familiar with password manager, it's a little application that you run on your Mac or PC or phone, and it's literally a password manager, meaning it keeps tabs of all of your usernames and passwords for different websites and different systems that you have access to, and the software generates a password for you. You don't have to keep using the same password with maybe few difference in characters, because if that password gets hacked, then people can get into and try the same password in different variations to break into different systems. With the password manager, on the other hand, each password could be completely unique, and you can make them. I have some passwords that are 30 digits long, 30 characters long password. I mean, that's an insanely strong password. And I possibly couldn't do it. Like if I just sat down and tried to figure it out on my own, no way, Jose. So password manager is an absolute lifesaver, and it's a worthwhile investment. You should do it at a personal level, but also as an organization, you should make that part of your security policy. And the next level to passwords, which has gained a lot of popularity over the past decade or so, is called multi-factor authentication. So for example, on your phone, before logging into Amazon or a website of your choice, you may have multi-factor authentication enabled where they send you a security code, as you can see on your screen here, and you plug in that code into that website before typing in your password so you can gain access. Now, the idea is with multi-factor authentication, you have multiple pieces of information that you need to gain access to the system or a website. And another example that I can give you is piece one could be an ATM bank card. So bank gives you an ATM card, for example. So this is something you have. And piece number two could be the PIN number that you choose after you get your ATM card. This is something you know. So when you go to get cash from your bank, you'll go to the ATM machine, you'll put in your bank card, and after you put in the ATM card, it asks for a PIN code. You type in the PIN code and you're in. You can get cash, you can run different type of transactions. That's a form of multi-factor authentication. And the most common example is the one I gave you earlier, where you're logging into a website and they give you a security code because you gave them your phone number. Now, one thing to keep in mind with multi-factor authentication is unless you provide both pieces of information, you cannot get in. You must provide both pieces of information. It's also referred to as two-factor authentication or 2FA. Now, two-factor authentication means you only have two pieces of information required. Now, in the example of an ATM card, you have a physical card and then you have a PIN. That's two-factor authentication. But multi-factor authentication takes it to the next level. You may need additional pieces of information as well beyond just two to be able to gain access. And what you should do is make multi-factor authentication part of your security policy to promote a strong security posture within your organization. The third type of authentication mechanism is digital certificates. Digital certificates are analogous to a driver's license. And as you can see here on this picture that I have on the screen, a driver's license uniquely identifies an individual that has this license. So you may have multiple people with the same name, but they're completely unique based on different attributes, their date of birth, where they live, the color of their hair, their eyes, all that jazz. That collectively together uniquely identifies that individual. Now, similarly, digital certificate is an alternative form of credential used for the verification of identity. So computer systems use digital certificates to verify the identity. So for example, if there's a digital certificate on a server, it's to make sure that it's a legitimate server, not some rogue bad actor's machine in our environment, but a legitimate server installed by our corporation. And digital certificate is issued by a trusted certificate authority, and it leverages PKI or public key infrastructure. Now there's a lot there, so let me unpack one by one. First, trusted certificate authority. It could be either an internal certificate authority within our corporation, but most likely if it's a public-facing website, for example, let's say apple.com, you'll actually need a third-party trusted certificate authority, somebody like VeriSign. You can look them up on the internet. They actually publish digital certificates. So when you go to apple.com, and you see a padlock in your browser, you can click on it and you'll see that there's actually a digital certificate issued by VeriSign to apple.com. And there's a whole process that takes place using PKI, which is a public key infrastructure. And PKI uses asymmetric key encryption. And when I say asymmetric, that means it's a combination of public and private key. And most of the browsers are programmed with the trusted third-party certificate authority information to begin with. So that helps me identify that it's coming from a legitimate third-party certificate authority server. And then because I trust that, I also trust apple.com. It's a whole chain of trust system at the end of the day. And without getting into too much detail, at a CCNP level, we're going to go deep into this topic, but I'm just trying to keep it high level, trying to help you understand the concept here. Digital certificates are time sensitive and they can also be revoked. So you may have noticed if you have a corporate laptop, you have a certificate installed on it. Servers have certificates installed on them and there is an expiration date. Typically around 5 years is an average from what I've seen. Some companies are more aggressive. You may see 3 years lifetime for a certificate. It just depends on your corporate security policy. And what you also have is the ability to revoke a digital certificate. So for example, if a corporate laptop is lost, an administrator can go ahead and revoke the certificate that was issued to that user on that machine. So if somebody tries to break into the company using a stolen laptop, a digital certificate is no longer trusted. Digital certificates are tough to manage, but provide very strong security. And the final type of authentication mechanism that I want to touch base on today is biometric security. So when I say biometric, different things probably come to your mind, but here we have a finger scanner. So we go ahead and put our finger on this finger scanner, and if our fingerprint matches, we are granted access to either a facility or to a system. It's a form of authentication that relies on users' biological attributes for providing access. So once again, things like fingerprint, face recognition, iris recognition, voice recognition, even weight. So where weight comes in handy is, let's say it's a very secure data center type facility and it's a multi-floor data center. So as somebody gets into an elevator and they're trying to get to the next floor, there could be a mechanism in place that checks that person's weight. And it has a certain threshold let's say if you're 165 pounds, what it looks at is if your weight dramatically changed, if you went from 165 to 265, that ain't right. It's going to refuse access. And there are many other examples, but this is just a subset of what biometric security can do. Now, the thing about biometric security is this is the ultimate form of security. Now, I'm going to admit it's not perfect. There is no such thing as perfect security, but it's pretty close to being perfect because every single human being is unique and all of our biological attributes make us super unique. However, the big thing is it can be very expensive to implement as a physical security mechanism. If you have thousands of sites and you have biometric security deployed everywhere, just the management of that system and maintenance of these biometric scanners and getting all of your employees in the database, all that entire system could be very complicated and very expensive to maintain. Now, I would be remiss if I didn't touch on one of the key concepts when it comes to a defense mechanism called defense in depth. It's a very, very deep topic. I'm not going to spend a ton of time, and this is, once again, I'm kind of going beyond a typical CCNA exam, but I'm trying to give you a glimpse of what it takes to implement security from a real-world perspective, because this topic is very near and dear to my heart. It's all about deploying security in layers. So we have a parameter layer. So this is the edge of our network. This is one layer where you would deploy certain type of security. Typically, firewalls fit into the parameter security. Within the network, making our routers and switches hardened. It's called device hardening. We might actually do that at this layer within our defense in-depth strategy. Then when it comes to the host, this could be a server, and it could be antivirus, anti-malware protection, things like that, right? To protect the host or the server itself. Then that server might be running an application. Now, how do we protect that application? Once again, we could use things like antivirus, anti-malware, different type of mechanisms to protect that application. And then a level deeper is the gold mine, right? Data is the gold mine in our network. This is what the bad guys are after, ultimately. For example, if you're Tesla and you build this beautiful electric car, you wouldn't want your intellectual property and secret research and development data to be stolen by a bad guy, because all of a sudden that data can now be used by a competitor to maybe start a brand new company that is now competing with Tesla at a much better price point. So what you can see here is security is not as simple as going, okay, I'm just going to go ahead and buy a bunch of firewalls and it's like one and done type deal. It's never one and done. You want to peel the onion. You always want to look at security from different layers perspective, and then you have to protect each layer uniquely within your environment to be able to ensure security. Now, once again, even with all these advanced security mechanisms, you're still not going to be able to achieve 100% security. But by deploying security at each layer uniquely, you're severely reducing the attack surface. Each of these circles here we're looking at, each layer within our environment presents a unique attack surface. And by deploying different security techniques, the idea is to reduce the attack surface. Remember, if the bad guy is adamant enough, eventually they're going to break into your environment no matter what you do. It doesn't matter how smart you are or how much money you have spent. Eventually they're going to break in. But if you made it so much harder for them that it takes them months or potentially even years to break in, people want to go after easy targets. They don't have that much time. And if you think about the world we live in today, everybody wants instant gratification. If they're going to try, and after a few days, they're going to probably give up and move on to the other company. And that's the idea. You want to make it so much harder for the bad guy to break into your network that they just go ahead and give up and move on to somebody else. Now let's shift our attention to AAA. What is AAA? It stands for Authentication, Authorization, and Accounting. Very important concept in security. Authentication in AAA answers the question, who is the user? Authorization answers the question, what is the user allowed to do? And accounting answers the question, what did the user do? AAA is implemented via a centralized authentication server such as Identity Services Engine or ICE. Here, let's look at a quick environment. We have a couple of users down at the bottom below, Bob, Jen, Dan, connected to a LAN switch. There's an ICE server also connected to the same switch. Then we have a LAN that has a router and another switch and a firewall. Now, to look at things from a AAA perspective, we use terms like clients, AAA server, resources, right? So these are the resources on our network that we want to gain access to. Now, when it comes to AAA, there are two protocols that are the most popular in the industry. One is called Radius, the other one is called TACX+. Radius is industry standard. It uses UDP ports 1812 and 1813, and it only encrypts password. So it's a little bit less secure, but it's an open standard, and it's been around a long time, widely supported, typically used for authenticated users. And then you have TACX+. It's Cisco proprietary. TACX+ has another version. It's called TACX without the plus, and that's open standard. But Cisco took that TACX and made it a lot better. And that's how TACX+ was born. It uses TCP port 49, and it encrypts the entire packet. That includes the password, the username, including all the attributes. The entire thing is captured. And typically, TACX+ is used for authenticating network devices. And here's what Radius stands for. Remote User Authentication, Dial-In User Service. Whereas TACX+ stands for Terminal Access Controller Access Control System. That's a mouthful. And once again, the idea here, if you were to take a step back here, guys, is let's say Bob wants to connect to a router. Bob sends an authentication request to the router, and router has a AAA configuration, and the AAA configuration says, hey, go talk to this ICE server on our screen. So the traffic from Bob goes from the router up to the ICE, and then the ICE server presents a challenge to Bob, which means it asks Bob, hey, provide your username and credentials that are stored on me, the ICE server. And when Bob provides the credentials, and if they match, then Bob is given access to that router. Otherwise, the access is denied. So AAA server is very similar to, if you're familiar with Active Directory in that sense. It's a centralized database of all the users with their credentials, username and password, and different attributes. Like, for example, a help desk user might be given very limited access to a router, whereas a solution architect or an engineer, senior engineer, might be given full access to that router. And TACX has the ability to do that. Radius cannot be that granular, whereas TACX can be that granular. It can limit what type of access users can get when they connect to a router or firewall or a switch. So that's the purpose in life of a AAA server, and it uses either a Radius or a TACX for that to happen. Now let's shift our attention to security features. So here's an average looking guy with an Ethernet cable who just walked into your office, and they're going to go ahead and plug in their device. Now what you don't know is they may seem innocent, but that person might actually be the Joker in Gotham City, perhaps an agent of chaos trying to bring your environment down. Well, here you are, the Batman, the protector of Gotham City, the judge, the jury, the executioner, and you go kapow, and you take care of that Joker and make sure they are unable to use that port on the switch, even if they were successfully able to plug in their Ethernet cable. And that's what switch port security is all about. So the first feature that I want to draw your attention to is switch port security. And the reason it's important is because of this attack called MAC flooding. So as you can see in the diagram here, we got a legitimate user on the right-hand side who's trying to access different applications on the network. And then we got a hacker on the left, and they're injecting 250,000 bogus MAC addresses per second into our switch. And what that will do is it's gonna eventually bring our switch to its knees. It's not gonna be able to do anything. And this is what you may call a denial of service attack, because essentially at this point, the switch is incapable of processing regular, legitimate requests because it's so inundated with all these MAC addresses that it just ran out of memory and CPU capacity. To protect against that, what we do is we can configure switch port security. And what we can do is we can say, look, we're only going to allow 3 MAC addresses on a particular port. And if that policy is violated, meaning if we learn more than 3 addresses, in other words, when a 4th MAC address is learned, we can shut down that port because we know for sure that that 4th MAC address is anomalous. Somebody has created a bogus MAC address with most likely a malicious intent trying to break into our network. And the way we configure switch port security is on the switch, on CLI, we type in interface fast Ethernet 00. Once we're under the interface, we can say switch port mode access or trunk, depending on what that port is meant for. We can then say switch port security to enable port security on that port. We can then say switch port security maximum, and then type in the number. This number specifies how many maximum MAC addresses are allowed on that port. We can also type in switch port security MAC address, and we can specify an exact MAC address. And if you want more than one, we can keep typing this command with additional MAC addresses. And essentially, it's statically defining a MAC address in advance. So what that does is, if you know for sure that a certain machine is supposed to be plugged into that switch port, you can go ahead and provide that MAC address. Now, it's not very scalable, as you can imagine. If you have thousands of employees and a very huge environment, this is non-practical. You cannot go to each machine and manually assign a MAC address. Now, it will provide great security, but it's not scalable. So to get around that, you can use a feature called MAC address sticky. So the sticky keyword, what that does is that the very first MAC address that's learned on that port dynamically. So let's say there's a machine sitting there, a corporate provided desktop. The very first time that desktop comes up and talks to the switch will learn that MAC address, and you'll then have to do write mem, or actually you would have to write the configuration for that MAC address to be saved into the configuration of the switch. So when the switch boots up, that MAC address remains there. That's what the sticky command does. And one final command I want to bring to your attention is switch port security violation. And after violation, you can select a keyword, either protect or restrict or shut down. Now, if you select protect, that means port stays up, but the traffic from violating addresses is dropped. After that, if you decided to use restrict instead of protect, in this mode, what ends up happening is port stays up, but the traffic from violating addresses is dropped. So once again, going back to that example of 3 maximum addresses allowed, if the 4th address is detected, port will continue to operate, but the traffic from the violating address is going to get dropped. Second thing that happens is switch keeps track of violating packets. And the third thing that happens is switch also sends a syslog and SNMP messages. So here we're keeping track of what's really going on in our environment. And the final one, if you decided not to use the protect or the restrict, you can use the shutdown. Now this is a very aggressive mode. Port immediately goes into error disabled state when security policy is violated. Switch also sends syslog and SNMP messages similar to restrict. And finally, it must be re-enabled manually or through error disabled recovery. And I'll tell you what that command looks like to automatically recover the port after it's been shut down. Or you can manually go ahead and bring it back up by typing in shutdown and then no shutdown to manually enable the port. Now, another important security concept to keep in mind is DHCP snooping. So here in this diagram, what we're seeing is we have a legitimate user here, let's say Bob, and he wants to send a DHCP request so his laptop can communicate over the network. Now, you got a couple of bad actors here. This guy to the left. What he's doing is he's sending thousands of DHCP requests to overrun the DHCP server. And then there's another guy at the bottom of the screen here. He's sending bogus DHCP responses. So what we can do is by using DHCP snooping, we can rate limit this port, let's say to just 10 connections per second or requests per second. And we can put a full stop to any type of bogus DHCP response. And by doing that, we'll allow Bob to send a legitimate DHCP request to the server. If we didn't have this security mechanism in place, these bad guys would inundate the server to the point that it won't be able to process legitimate requests, hence causing a denial of service attack. Now the DHCP snooping configuration. So we type in IP DHCP snooping at a global level to enable IP DHCP snooping at that level. We can also specify IP DHCP snooping VLAN. So this actually ties it to a particular VLAN. So that means we're going to be snooping traffic on this particular VLAN for DHCP requests. We can then go under the interface fast Ethernet 00. Once we're under the interface configuration mode, we can type in IP DHCP snooping trust. If we trust that port, let's say if a DHCP server is plugged into that port, this command would allow DHCP server to behave as a normal DHCP server, which means we completely trust this port. Or we could say we don't really trust this port, and if it's an access port, we don't know who's going to plug into it. So we can say IP DHCP snooping limit rate 10. That limits the total number of DHCP requests to just 10. Anything beyond that would be considered a violation of this security policy. Now, one important note to keep in mind is if the port goes in error disabled state due to exceeding DHCP snooping rate limit, there are 2 optional commands you can configure for auto recovery. And here they are. The first command is at a global level, you can say error disabled recovery cause DHCP rate limit. And what you can do secondarily, you can define the error disabled recovery interval. So you can define after a certain amount of time that port can be recovered automatically without any manual intervention from the network operator. The next thing we want to look at is dynamic ARP inspection. But before we get into the dynamic ARP inspection concept, what I want to define is a couple of different types of attacks that ARP inspection protects against. And what we have is man in the middle, or an ARP poisoning attack. Now, this is something we have already discussed, but check this out, guys. We got this bad guy here at the bottom of the screen. He's an attacker. Look what he's doing. we got this gateway up here. So what this bad guy is doing is sending a gratuitous ARP up to the gateway claiming to be 10.1.1.50. And it's saying to get to that, get to the MAC address of B. Now, the bad guy has a MAC address of B, but check out bad guy's IP address is 25. Why is it telling the gateway to connect to 50? Well, it's because it's trying to impersonate this victim. A legitimate employee in our company is now being victimized because this attacker is impersonating to be them by injecting a source of .50 into that packet that they had just generated, the gratuitous ARP packet to be specific. So the gateway, their ARP table is going to get poisoned because now they're going to say, in order for me to get to 10.1.1.50, which in this case is the employee sitting here to the right, that traffic is going to be sent to MAC B. And B is the bad guy. So little did the gateway know that it's actually sending traffic to the bad guy. And then look at this. This bad guy also generated another gratuitous ARP. But this one was sent to the victim machine saying, hey, by the way, if you need to get to 10.1.1.1, which happens to be the gateway, come to me, MAC B. So it's fooling both the gateway and the victim into believing that bad guy is the one they need to be talking to. Hence the reason it's called man-in-the-middle attack, because now that bad guy is sandwiched and is sitting in between the traffic flow. So what's going to end up happening is that at the end of the day, when victim wants to talk to the gateway, the traffic is going to flow through the attacker's machine up to the gateway and vice versa. So as you can see here, attacker is in the center of this flow, and the attacker can now snoop this traffic and using something like Wireshark and some other sophisticated tools, completely deconstruct everything that's going on in this network, at least the communication flow between this victim and the gateway. So this is a pretty nasty attack, and to address it, we have a feature, security feature called Dynamic ARP Inspection. And let me explain how we can configure it. So here's how we configure Dynamic ARP Inspection. Initially, we go to the global configuration mode and type in IP ARP Inspection VLAN 10. Now what that does is it enables ARP inspection for that particular VLAN. The next thing we do is we type in IP DHCP snooping. So ARP inspection and DHCP snooping are interrelated because not only we want to protect ourselves against a man-in-the-middle attack, but we also don't want a denial of service attack from illegitimate DHCP requests trying to bring our DHCP server down, right? So it's a powerful combination, these two commands. Then we go to the interface. We type in interface fast 800. Could be gigabit Ethernet, but you get the idea. Once we're under the interface config mode, we type in IP ARP inspection trust. So if you trust a particular port, and we know for sure that there's a legitimate device connected to it, we trust it. But if it's an access port, and we don't know who's going to be plugged into that port, then we can type in IP ARP inspection limit rate 10. This limits the total number of ARP packets to 10 per second. Important note to keep in mind, if the port goes into error disabled state due to exceeding DAI rate or the dynamic ARP inspection rate limit, here are the two optional commands for auto recovery. You type in error disable recovery cause ARP inspection. That's a global config command. And the next global config command after that is error disabled recovery interval. And then we type in a number that specifies the number of minutes after which this port will automatically be enabled. Now, let's quickly shift our attention to the security devices. First, let's talk about firewalls. A firewall is a security device designed to protect your internal network from various threats on the internet or the external network. Firewall achieves this by monitoring and filtering incoming and outgoing packets as follows. Now, before we go deep into this, understand that firewall is a packet filter. It filters packets as they're either coming in or going out of the network. Now, what information does firewall actually look at and filters on? It looks at a combination of source IP and destination IP at layer 3. It looks at source port and destination port, whether TCP or UDP at layer 4. It stores state information for each packet to look for deviations. This is also known as stateful inspection or stateful firewall. It could potentially do deep packet inspection to identify additional TCP and UDP ports at layer 7, in addition to also identifying the actual application itself. It can also do what's called URL filtering by looking deep into the content of each HTTP request. There are two types of firewalls. One is called legacy firewall or a traditional firewall. We also call that a layer 4 firewall. And we also have the next generation firewall or NGFW. It's also known as application layer firewall or layer 7 firewall. Now, what's the difference between layer 4 firewall and layer 7 firewall? As the name gives it away, layer 4 firewall or traditional firewall can only filter up to layer 4. For example, if you look at 2ABC, these three elements here, source and destination IP, source and destination port, and storing the state information, that's your layer 4. But if you look at 2D and E, they're more advanced functions. That's the functionality of a next generation firewall. Now, this is not a comprehensive list that I have up here in bullet 2, right? There's a lot more to it, but I'm just giving you a very high level overview of what a firewall is. But we'll go deep into the legacy firewall and next generation firewall as we move forward here. Now let's quickly look at stateful firewall overview. So let's review this topology. We got an internet connection that's terminating into an internet edge router. That router has a firewall sitting behind it, and behind the firewall we got the switch, and that switch has a web server plugged into it. Now we got this legitimate user on the internet. His name is Bob. He's connecting to this web server and life is good because our firewall will do what's called a stateful inspection. And assuming Bob is only sending, let's say, between 10 to 100 connections per second, that's totally allowed because our firewall policy has these limits set and defined within the firewall policy. So that's considered a normal traffic flow. Once again, here we have the TCP connection limits or the total number of TCP connections per second predefined. And the firewall has the ability to keep track of every single flow. This allows the firewall to be able to monitor TCP connections per second. Now, let's take this concept to the next level. We still have Bob connected. He's happy. All of a sudden, we got this hacker. And now let's look at what's going on with our firewall. Our stateful firewall now has a red flag. It's a DOS attack traffic flow. What's going on now is hacker is sending 10,000 TCP connections per second. So if you guys recall, previously our limit was between 10 to 100. Now the firewall is seeing 10,000 connections per second coming its way from a particular machine, from one particular source going to one particular destination. Now that's a red flag. It's a policy violation. But if he didn't have a firewall, what would end up happening is our legitimate guy, Bob, will actually lose access to the web server because of the denial of service attack. The firewall will be so busy processing hackers' request that the legitimate users will never be able to connect to that web server. But thanks to the firewall, we can not only detect this malicious behavior, but actually protect against it. We can take an action and kill that traffic. Now let's look at another important concept when we talk about firewalls is security zones. So as you can see in this diagram here, we got internet connection coming into our edge router that's plugged into the firewall. Now, as you can see, the orange highlighted area is considered an outside zone. It's called zone outside. And then we got the firewall connected to the switch port that is connected to a machine that Bob happens to be using. Now, the green box at the bottom of our firewall is the zone inside. Okay. So what this is giving us the ability to do is we're literally defining different zones and we're assigning different trust levels to those ports in order to be able to do something with that traffic. And the way we use these zones is through firewall rules. So our rule 1 could say allow zone inside to initiate traffic on port 80 to zone outside. Okay, so you see this green port here on this firewall. That's rule number 1 that's configured on this firewall. And then rule 2, the default rule on a firewall is to deny all traffic. So in our case, rule 2 says all other traffic is disallowed, meaning we'll only allow zone inside to talk to zone outside if the traffic was initiated internally from the LAN going to the WAN over port 80. And this is considered a legitimate traffic because it's being initiated from the inside. Now, if the traffic comes in the reverse direction, if somebody out on the internet tries to initiate a TCP connection over port 80 into our LAN, let's say if somebody's trying to connect with Bob over that port, firewall will kill that traffic because we don't have that rule defined. Now let's take our security zones to the next level. So we still have our zone outside at the top of the screen, and we got our zone inside at the bottom of the screen, the green and the red zones. What we have now is the third zone to the right of the firewall, and that is the zone DMZ. So this is our demilitarized zone. Here we have a public-facing server, a web server, that we want internet users to connect with. Let's say we're Amazon.com or Google.com, or pick your favorite site. That's how they configure it, right? They have these different they actually have a DMZ zone where their web servers sit to serve their customers. And the reason they do that is so when you define your firewall rules, the first rule may say, allow zone inside to speak with zone outside over port 80, that's allowed. Rule 2 might say allow zone outside access to the DMZ zone over port 80. That's also a desired behavior and it's allowed. But what's not desired is all other traffic is denied. Meaning if somebody on the internet wants to communicate with Bob, that traffic will be denied. Unless Bob wants to talk to the outside world, that's allowed. But the outside zone cannot connect with Bob. However, the internet users can communicate with the web server all day long. No issues, but only on port 80. If somebody tries to change the port because they're trying to be clever and they're trying to break into the DMZ server, they can try all day long, but they're not going to succeed because our firewall will keep killing that session as soon as that traffic hits the firewall and it detects that the port is not 80, but let's say it's 1020 or 20,001. It will go ahead and drop that traffic. Now, how does an IPS work? So here's a quick topology overview. We got an internet connection terminated on an edge router, which has an IPS sitting behind it, and a switch, and we have a desktop plugged into that switch. The first thing that IPS does is it downloads a database of exploit signatures. It's very similar to antivirus on a computer. So if you got an antivirus on your computer, you know it goes and downloads updated signatures. So it learns about any type of viruses. Now, one key concept to keep in mind here, guys, before I move forward is NIDS versus HIDS. Now, what does NIDS stand for? NIDS stands for Network-Based Intrusion Detection System. And this was a previous generation of IPS. IPS initially started out as IDS, which is Intrusion Detection System, but later it became Intrusion Prevention System, or IPS. Because IDS is just a dog that barks, but IPS is actually a dog that not only barks, but can also bite. That's the difference. Okay, so that's why IPS ended up becoming mainstream. Now back to the difference between the two. So IPS is a network-based intrusion detection system, whereas antivirus on your computer is considered a host-based intrusion detection system, or HIDS. That's the big difference. The second thing that IPS does is exploit signatures define different header field values. So you know how we have packets, and those packets have headers at layer 3, layer 4. All these different layers have different headers, and within those headers, we have different fields. IPS looks at the exploit signatures and compares them against the different well-defined header fields and looks for anomalous behavior. It basically compares packets to the known exploit signatures at the end of the day. And packets that match those signatures are logged and discarded. Okay, so IPS says, this traffic is bad. Not only I'm going to deny that traffic, but I'm also going to log it. So it can be later on analyzed by a security expert to see what's really going on. And IPS can also send this traffic to another security appliance for further analysis. And finally, you may be asking yourself, what are exploit signatures and what do they exactly do? So here's the answer. Exploit signatures protect against the following types of attacks: denial of service attacks, distributor denial of service attacks. They protect against worms and viruses and zero-day attacks. So zero-day attack is an interesting concept if you're not familiar with zero-day attacks. When a brand new attack shows up in the wild and machines start getting infected, well, it's a zero-day attack because there is no protection against it, and it's a brand new attack, and nobody has ever seen it before. Hence the name zero-day. From the time that attack happens until a protection is made available, there is a lag that occurs, and that lag is typically a bad thing. So if you think about it, let me give you another perspective of thinking about this. Let's say this machine right here has an antivirus. Let's say it has Symantec antivirus running on this desktop. Could be any, but Symantec is good as any. Now, if you think about it, typically when a zero-day attack happens, ZDA, right, comes through the internet, makes it through our router, makes through our IPS switch, makes it to that machine. And that antivirus that's running here, unless it has the latest updates, it's none the wiser, and the machine may get infected, right? And then we'll have to wait a couple of hours or probably a couple of days before that update is made available. But as you can see, this is pretty scary because that malicious traffic was allowed through the entire network infrastructure for it to be able to make it to our machine. Now, what network-based intrusion prevention system does, which in this case is our IPS here, is it says, how about I kill that traffic right here before it even has the ability to infect machines on the inside of the local area network. So catch the traffic as early as possible. That's the purpose in life of an IPS. Instead of allowing that traffic to get to the machine, and if it gets infected, it might be too late. And you may be in really, really terrible shape if that happens. But with an IPS, we have the ability to proactively and in real time deal with that traffic. And typically, IPS is a lot more efficient at detecting variations in packet headers and application signatures than an antivirus on a machine. Because think of an antivirus as more of a reactive solution compared to an IPS, which is more of a proactive solution. Now, before I talk about next generation firewall, I want to talk about some of the challenges with a traditional firewall. So this is a network topology you looked at a couple of slides ago. Internet connection terminated into an edge router, and that edge router has a firewall sitting behind it and then a switch. And then we have the zone outside represented in orange, and we have the zone inside represented in green. Now, first thing that happens in a traditional firewall scenario is firewall inspects each IP-based application which is mapped to a well-known port, and it's a predetermined mapping. In other words, what we have in a traditional firewall scenario, an IP that is mapped to a port, and it's assigned a certain application to it. So for example, a web service. A web server is an application running on a server, and it has an IP address, but there's also a port. If it's providing services over HTTP on port 80 or HTTPS over port 443, it's all predetermined mapping. Now, hackers know that firewalls filter most well-known ports from sessions initiated from the outside zone to the inside zone. So hackers already know, they're smart enough to know that firewalls are really good at filtering well-known ports. Now, what they can do is hackers scan ports to find available ports not currently being blocked by the company's firewall. So in this example here, let's say the firewall that we have in front of us, there may be certain ports that are not blocked on this firewall. So now when hackers on the internet run a scan on this firewall, on the external interface of this firewall, they may uncover that certain ports are not blocked. Well, when they find that out, they get really excited because now they can get creative and launch an attack. And in this case, for example, they could use HTTP with a non-standard port. So HTTP is over port 80, but they may say port 2001, for example. And they may craft a packet that comes to our firewall with that port number, and our firewall may get confused and allow that traffic to go through. And this allows the bad guy to break into our network, and then they could potentially gain access to hosts inside of our LAN. And once that happens, that makes for a very bad day. What's the solution? Next generation firewall. What's the difference between a traditional firewall versus a next generation firewall? Well, before we talk about that, one thing for you to know is Cisco's latest security portfolio includes next generation firewall and next generation IPS in a product or solution called Firepower. You can buy it in a form of a physical appliance, or you can buy it in a form of virtual appliance in AWS or Azure or GCP. Now, one cool thing to notice here is Cisco's next generation firewall can also include next generation IPS. And it's a one box solution. So one thing I did not touch on when I was showing you different topologies is that many years ago, back in early and mid 2000s, you had separate firewall, and then when the initial IDS came out and IPS came out, that was another piece of hardware that you had to buy. So you had a firewall and then you had an IPS. They were both separate physical devices. Now, over the years, what Cisco has done is Cisco has merged and combined the next generation firewall and the next generation IPS functionality into a single box. And that's what I'm calling a one box solution. Now, the big benefit of that is inherently less hardware is better because that means you have a more green footprint. Plus, the biggest advantage is you don't have to use completely separate systems to monitor and manage. You can now use a single platform to be able to see what's going on in our environment and also set up policies using a single pane of glass, if you will. And there's less opportunity for things to miss because you define your policy in a centralized place. You can bring the firewall and the IPS policies closer together so they are providing a much better quality security. Now, traditional firewall, some of the features that you get, stateful firewall filtering that we talked about, right? It's the ability for a firewall to be able to have a state table and it keeps track of all the incoming and outgoing traffic flows, and it looks for anomalous behavior. Anything that deviates those flows, it can kill that traffic. It also provides network address translation or port address translation. So this is something I talked about early on in my course, where you have a single public IP from your provider, but you have multiple hosts on the LAN that may need access to the internet. So think of your home environment. You're using a version of NAT called PAT, Port Address Translation. Single public IP, multiple internal LAN IPs, but they're private IPs. That's the key. And finally, VPN termination. So firewall can also be a VPN concentrator, meaning you can either have users terminate VPN sessions into the firewall so they can connect to the different corporate resources, or you can have two different locations. Two of your branch locations could have a VPN tunnel between them, so the traffic over the internet is secure, completely 100% encrypted and secure. So that's what VPN functionality provides. So these are the features that the old school, the legacy firewalls provided. Now, what do we get with the next generation firewall? First, application visibility and control. This is the deep packet inspection engine that is built in to the next generation firewall that actually does deep analysis at layer 7 or the application layer, with the sole purpose of identifying the application rather than relying on port numbers. Because as you saw earlier, when you have statically defined port numbers, it's easy for the bad guys to get around that and break into your network. And a lot of new applications use dynamic port numbers, so they don't have like static port numbers anymore. So you absolutely need to have this functionality to be able to protect your network. Also, you get things like advanced malware protection, or AMP. AMP provides an anti-malware protection at the network level. It's very similar to what antivirus does for you at the host level. AMP does for you at the network level. There's also a version of AMP available for endpoints. It's called AMP for Endpoint. In other words, you can actually use AMP on your machines as an antivirus and anti-malware protection. Next generation firewall also provides URL filtering. So now this is a feature that monitors and filters URLs in each web request. So what happens is, when you type in www.cisco.com, when that request goes to the firewall, it looks at the URL and it says, where is this request going? It's going to cisco.com. So that's a domain. Well, is it a good domain? Is it a bad domain? Well, cisco.com is a reputable website. It's a legitimate website. So by looking at that request, it can determine whether or not it's a legitimate request and it's a good domain name, and then it allows that request to be passed through the firewall. This is what's called URL filtering. Now, the way it happens is Cisco has this technology called Cisco Talos. This is the threat intelligence research team within Cisco. These are world-class network researchers and scientists that are designing the next generation protection capabilities within the Cisco portfolio. And they have this reputation-based system set up where different domains and different email servers and these different systems globally get certain score assigned to them. And that score is based on their reputation. If their reputation is good, score is better. If reputation is bad, score is lower. And the next generation firewall can use this function and this feature to filter traffic. So if you're going to a known bad domain, your firewall may kill that traffic and it may not render that web page for you because it may potentially be a dangerous web page. Also, the next generation IPS. Like I said, a lot of the new next generation firewalls have that functionality built in. So that's another element you can keep in mind. Now, before I talk about the next generation IPS, I'm going to first talk through the challenges with the traditional IPS. So here's a quick topology overview. We got internet connected to an edge router that has an IPS connected to it, and IPS has a switch connected to it. IPS compares all packets against a signature database which lists all known exploits. As a result of this, what IPS does is it generates a lot of events and logs. And this is to the point that if you think of things from a security operations center perspective or SOC perspective, the security staff gets overwhelmed by just looking at the sheer number of events that are happening in the environment. And then to analyze and evaluate and then do something about it, it's a tall order. So ultimately, SOC engineers are expected to find a needle in the haystack, because if you got hundreds of thousands or millions of logs being generated, and now your engineers are trying to see if any of those logs actually correspond to an attack, I mean, that is insane, right? So that's what they're doing. They're looking for a proverbial needle in the haystack. Now, this is not a big deal in small environments, but when you look at large enterprise networks, this could take an absolute toll on the security engineers and may lead to security incidents, because if you're trying to find that needle in the haystack, who knows how long it might take you to find that needle? And while you're trying to find that needle, the bad guys may get into your network and take control of your environment. And it may be too late by the time you find out that there was an actual attack. So what's the solution to that? We need a next generation IPS. Now let's talk through the traditional IPS versus next generation IPS. Traditional IPS includes things like signature-based packet analysis, like we talked about before, right? So we have a signature database, and then as each packet comes in, we look at the header of that packet and we analyze it and make sure it doesn't match the database. If it does match the database, we're going to do something with that traffic. Most likely, we're going to deny that traffic. We're also going to log that traffic. So that's called event logging. And traditional IPS could also redirect those packets to another security appliance for further analysis. Now, here's a couple of features of the next generation IPS in contrast to the traditional IPS. We got, once again, application visibility and control. Very similar to the next generation firewall. Here, we're looking at things from, once again, application layer 7 perspective with the sole purpose of identifying the application. The next big thing, and this is the biggest element of the next generation IPS, is the contextual awareness. So you need to understand what's really going on. To generate logs that are relevant, we first need to gather data from the hosts. And each host has an operating system running on it. There's a particular software version or revision. We have patches that are applied, applications that are running on that operating system, any open ports, etc. This provides a 360-degree overview of what's really going on with each host in our environment. We can then use this data point for all of the endpoints in our network to de-emphasize checks for exploits that do not apply to those endpoints. So why do we do that? You may be thinking, okay, what does that even mean? What that means is, ultimately, next generation IPS only wants to focus on stuff that's relevant to your network and not. So for example, if you're only using Windows operating system in your environment, there's no point for your firewall to do inspections on Apple iOS and Mac OS and all that, right? It doesn't need to do that because you only have Windows operating system in your environment. So that helps next generation IPS cut back on all these events and all that it needs to generate and be more laser focused on what it needs to do. And it also helps your security staff because now they don't need to look at a million different logs because they're only looking at relevant stuff. The next big thing is reputation-based filtering. So like I talked about earlier, filtering based on Cisco Talos assigned reputation scores. So we talked through this. It's a reputation-based system that looks at known good domains, known bad domains, email servers, bad email servers. It's looking at all those things and it assigns certain scores, and those scores represent a reputation. And based on that reputation, the IPS can make certain calls. And finally, the next generation IPS provides what's called event impact level. Next generation IPS provided assessment based on impact level for the security operations center. So the whole idea is if there's an event happening, instead of the security engineer trying to figure out whether or not it may be an actual attack, the next generation IPS, because it has a lot of intelligence and contextual awareness, it can also tag certain events as a potential attack because of all that intelligence. And this way, the security staff can then jump into those events and focus 100% and rule out whether or not it's an actual security incident taking place. CCNA 200-301 course. Today I'm going to cover Section 6, Part 1. This is the network automation section of the CCNA exam blueprint. Today's video is all about SDN. Before I jump into this, keep in mind network automation is a super hot topic in the industry right now. So you're going to learn a ton and it will help you develop skills to be the next generation network engineer. Let's go. Here are the topics I plan on covering today. First, I'll provide an overview of SDN, or software-defined networking. Second, I will then provide overview of the two SDN solutions offered by Cisco. Cisco ACI, which is designed for automating data center networks, and Cisco SDA, which is designed for automating campus networks. And finally, I'll wrap it up with cloud architecture overview. Let's first discuss SDN, or software-defined network. But before we do though, I want to take a step back and articulate what a traditional network device looks like. A traditional network device has three different planes. It has a data plane, control plane, and management plane, all located on every single network device in our network. Now, what's the function of a data plane? Data plane, at the end of the day, is all about receiving traffic, processing traffic, and forwarding traffic. In some instances, we may also decide to drop traffic if we have an access control list in place, or if we have a firewall policy in place. But ultimately, the whole reason data plane exists is to facilitate traffic flow through our network. And this is where the forwarding information base comes in, for example. Then we have a control plane. Control plane is how network devices learn about each other. They get to know each other. And control plane is what allows the network devices to have end-to-end path. This is how the path is defined. Without control plane, network devices would be blind and they won't be able to forward traffic. So data plane is dependent on control plane. As a matter of fact, data plane is derived from the control plane. And finally, we have a management plane. So if you think about a brand new router, for example, out of the box, that device is not going to do anything. That router is just going to be a blank slate. In order for us to do something with that device, you're going to have to connect to it either via CLI or through a GUI or graphical user interface. Now, if it's a home router, most likely we'll just connect to a GUI and configure it. And once it's all configured, it will allow us to connect to the internet. But in an enterprise, typically we connect via a CLI. Now, to build on this concept, like I said earlier, every single network device on our network has all three planes located on that device. Once again, the whole reason data plane exists is to forward packets. To facilitate forwarding of packets, we either have IPv4 or IPv6 packets. From a control plane perspective, on our local area network or LAN, we may be using something like OSPF or ISIS as a routing protocol. But over the wide area network or WAN, we may be using BGP. This is how, once again, the end-to-end network path is built. From a management perspective, if you want to connect via CLI, we could be using a protocol like Telnet. Now, Telnet is an unsecure protocol, so do yourself a huge favor and do not ever use Telnet in your environment. It's a legacy protocol. It's still around, but you should avoid using Telnet if at all possible because it passes credentials, username, and password in clear text. Instead, you should use SSH. SSH is all encrypted end-to-end. That's another protocol we can use to remotely connect to the device via CLI. SNMP, or Simple Network Management Protocol, is used for visibility into the network. And Syslog is also used to understand what's happening with the device. As different events take place, neighbors come up, neighbors go down, interface comes up, interface goes down. Every single time a system log is generated. That's what a syslog is. And through that, we gain visibility. So these are the three different planes located on every single device to be able to allow each network device to operate. Now, if we were to take a step back and look at the SDN or software-defined networking, as you can see here, as I mentioned, we have three different planes located on our device: data plane, control plane, management plane. Now, if you look closely here, you'll see the control plane is missing. What happened to our control plane? Well, typically in an SDN solution, we have an SDN controller, and what we do is we centralize the control plane onto the controller. So this way, the controller then is responsible for programming the forwarding tables of our devices. Just to provide additional context around control plane centralization, keep in mind not all SDN controllers are created equal. It depends on the vendor or the OEM that you're using. Each vendor designs their SDN controller differently. So for example, if it's OpenFlow, which is open standards-based controller, the control plane is 100% located on the controller. There's no control plane intelligence on the network endpoints. But in the case of Cisco actually uses a distributed control plane model where they do not move the control plane to the SDN controller. Okay, so I wanted you to keep in mind from a CCNA perspective, I want you to think that control plane is always located on the SDN controller. But as you go CCNP, CCIE, and beyond, and also from a real-world perspective, keep in mind that different vendors implement SDN controllers differently. Now, SDN controller's job is to centralize and automate network provisioning. So that means creating the underlay and creating the overlay. So underlay being VLANs and BGP routing and all the different other components that you may need to be able to bring up the routers and switches and firewalls and load balancers. That's what network provisioning is. And the other job of the SDN controller is to centralize and automate the network management piece. So basically, once we have an SDN controller in place, we will no longer go and touch devices individually. We'll log into the SDN controller and let the controller manage the entire network fabric instead of us having to touch each device hop by hop like we did in the past. And finally, SDN controller centralizes and automates network visibility. Now, why is that important? Well, if you think about it, in a traditional network, each device, we may be using different third-party tools, or it could be Cisco tools to be able to monitor our network. And we have a hodgepodge of Syslog servers and SNMP servers, and you may be using NetFlow and NetFlow data collector, but that makes it a lot harder for us to troubleshoot because we have different tools to log into, and if something goes down, unless we receive an alert proactively, it just becomes a nightmare. When we have an SDN controller in place, that also gives us visibility into the entire fabric, 360 degree. So we have complete deep visibility into what's going on in our network. So what I'm trying to get at here is I'm trying to give you a sense of why SDN controller was designed to begin with and what the job of the SDN controller is at the end of the day. Now, from a terminology standpoint, there's a couple of terms you want to familiarize yourself with. When it comes to SDN controller, we have what's called a southbound interface, or SBI for short. That's the interface that's responsible for communicating with the network endpoints like the routers and switches and firewalls, the load balancers and all that. And all the devices, the endpoints get programmed by the SDN controller through the southbound interface. Now, how does the controller know what to push or what policy to push to the network endpoints? Well, I'm glad you asked, because that's where northbound interface comes in. Through the northbound interface, we can potentially log into a GUI. So for example, if it's a Cisco ACI solution, it has a nice GUI. You log into it and you go ahead and start defining different logical constructs and templates that allow us to create an underlay and overlay network, and it makes it real simple for us to be able to configure all the network devices. Now, this Cisco provided portal is an example of a native application on the SDN controller. It's an application natively written and designed by Cisco software developers to facilitate the deployment of ACI within our data center, for example. But we're not necessarily restricted to that. We could use third-party automation tools like Ansible, Chef, Puppet, or the automation tool of your choice, and you can go ahead and configure all of your network devices through these automation tools. You'll typically pick one automation tool, like Ansible, for example, and use that as a primary way of defining your playbooks to be able to configure your entire network fabric. Now, building on that terminology, we have southbound APIs versus northbound APIs. Now, before I get into the details of those APIs, well, let me first define what the term API stands for. It stands for Application Programming Interface. API is a method for one application to exchange data with another application. So let me explain. So the southbound API allows the SDN controller to program all the network endpoints that are located south of the SDN controller through OpenFlow, which is an open standards-based SDN solution, or it could be Cisco proprietary OpFlex SDN solution used by APIC. The southbound API could leverage CLI, things like Telnet or SSH. Like I said, Telnet is unsecure, so you should be looking into deploying SSH version 2 to be specific. Also, SNMP for network monitoring. And the southbound API could also be leveraging netconf, which is an IETF protocol, which means it's an open standard protocol used for installing, manipulating, and deleting the configuration of network devices. It's very popular in the industry right now, and you'll learn a lot more about netconf at a CCNP, CCIE level. But here, all you need to know is that it's a very popular mechanism used for network automation today. Now, when it comes to defining what the SDN controller needs to do, that's where the northbound API comes in. And northbound API typically leverages RESTful API. And REST stands for Representational State Transfer, or it could be using a Java API. It just depends on. The RESTful API is the most popular API because it uses HTTP verbs, and we'll talk about that in a moment. Now, speaking of REST API, let's zoom into the northbound API component, and let me give you a glimpse into how REST API works. So if you were to take an SDN controller and look into the northbound API, let's assume in this example, I designed an application called Nodge app. And the whole purpose in life of this application is to pick a router within our network. And on that router, we can go ahead and pull information about all the active and currently operational interfaces on that router and all the configuration associated with each of those interfaces. So what we would do is in this app, the first step would be I would send HTTP GET URI request to the SDN controller. Now, before I go any further, let me first explain the HTTP verbs I was telling you about. So here are the 4 HTTP verbs that are used by the REST API: post, get, put, and delete. HTTP post means to create a URI. And URI stands for Uniform Resource Identifier. It's a fancy term for an object. So basically, HTTP post means create an object. HTTP get means read an object. HTTP put means to update an object. And HTTP delete means to delete an object. Now, as you can see, back to my example here, step 1 is HTTP get URI. So I'm saying, go to router 1 in my data center and pull all the interfaces that are live and all the configuration associated with those interfaces. So this get is basically a read request for that object. SDN controller is then going to go talk to that network device that's attached to the southbound direction. Then once it reads and gets that information, it's going to come back to my application with the HTTP GET response in a JSON data format. Now, JSON stands for JavaScript Object Notation. It's a very popular type of human-readable format that is also very well adopted on a global scale today. And it basically extracts that interface configuration in such a way that it becomes human-readable. And ultimately, my application will then display the results of my initial request on a web page, and it could be in an XML format. And XML stands for Extensible Markup Language. It's a web-friendly language. So once again, the whole idea of the REST API is to facilitate the automation of network programmability. Ultimately, at the end of the day, what we're trying to do is we're abstracting all the complexity away. Instead of having to memorize every single CLI command in our routers and switches and firewalls, instead, we want to use a standards-based approach whereby using HTTP, we can define our request in a human-readable format, and the SDN controller then goes ahead and translates our intent from a human-readable format into a machine-readable format, like the CLI commands, for example, and then parses all that data and returns the data back to us in a human-readable format again, so we can read what we initially requested based on that request. Now, here I'm showing an example of reading, but you get the idea. It doesn't have to be just a reading function. I could create interfaces like a loopback interface, or I can delete a loopback interface, or I can update the interface with a new IP address or an ACL or whatever have you, but you get the idea. Now, another important element that I want to bring to your attention is, so SDN, as I alluded to earlier, has a centralized control plane. Now, what are the pros and cons of distributed control plane versus a centralized control plane? Well, I'm glad you asked, because that's exactly what I'm going to show you here side by side. So distributed control plane, that's a legacy approach. It's a hop-by-hop approach. Centralized control plane is a more modern approach. It's a controller-based approach. Distributed control plane, there's one instance of control plane per network endpoint, whereas in a centralized model, control plane is centralized on the controller. Now, distributed control plane has a big benefit when it comes to network resiliency. It's resilient to failure, whereas the centralized control plane could potentially become a single point of failure unless we have redundant controllers configured in our network. And another big issue could be the synchronization of the state of our network or the database of our network. So let's say if we have two controllers, and if controller 1 knows about all the network endpoints in our network and controller 2 only knows about half of those devices, we have a database sync issue. And it's going to cause issues when it comes to maintaining and managing the state of our network at any given point in time. Distributed control plane, however, has some convergence challenges though. So for example, if we have 10 routers in our environment, 9 may come up okay, but one older router may have issues converging because of maybe some iOS bugs or some challenges with the hardware itself. When it comes to centralized control plane, the convergence is much better because now the control plane is located on the controller. Now, distributed control plane works fine in small environments. Typically, centralized control plane works better in large environments. Now, distributed control plane is difficult to horizontally scale because as you need more resources for the control plane, as you add more devices, your control plane gets bigger and larger. You're going to need more memory, more CPU. At some point, you're going to run out of those resources on that device, which means you're going to have to add an entirely new device. Whereas the centralized control plane is designed with horizontal scalability in mind, and all you do is you simply deploy a new instance when you need more capacity. Now, let's take a huge step back and think about why SDN is taking off now. Because that could be a question, I'm sure, that you may be thinking of at the moment. Why did SDN take off now compared to 20 years ago or 15 years ago? Even about a decade ago or so, SDN was slowly gaining traction, but over the past 5 years, SDN has taken over the world by storm. Why is that the case? It's a great question. I believe there are 3 big reasons. First, high bandwidth availability. So if you think about it, I'll give you my own personal example. About a decade ago, I had a 50 meg internet circuit at home. Today, I have a 1 gig internet connection from my ISP. And it's pretty much for the same price. I don't think I'm paying a whole lot more than I did about a decade ago, but my bandwidth has increased 20-fold from 50 meg to 1 gig. Similarly, on the enterprise side of the house, both on the LAN and the WAN side, we have a lot of bandwidth-hungry applications. We want low latency. We want better quality of service. For all those things to happen, ultimately, we want to provide a great user experience. That means we need to have a lot of bandwidth available, both on the wide area networking side of the house and also on the LAN side of the house. So we have come a long way over the past many, many years, and especially over the past 5 years, we have come to the point where bandwidth is no longer an issue. It just comes down to how we design and architect our networks. Second of all, we're seeing an evolution of silicon chip and ASICs. So basically, if you think about like the compute capacity, we're seeing the silicon chips getting smaller and smaller in size and footprint, but their capabilities are leaps and bounds ahead compared to where we were about a decade ago. If you look at switches today, a 24-port switch, and if each port happens to be, let's say, 10 gig, that means we're going to need 240 gig worth of uplink capacity from that switch to be able to provide a non-blocking fabric. And that's no longer an issue. Thanks to the advancement in silicon chip and ASICs, the throughput limitations we had on the backplane of the switches is pretty much gone. We can now do what's called non-blocking forwarding, which means we can use the full throughput of all the ports, all the way from the downlinks that are plugged into the endpoints to the uplinks. And we no longer have choking points in our network. Back in the day, we did have choking points in the network. but those choking points are almost gone for the most part, at least in the data center realm. And finally, this is the big one, is the adoption of virtualization technology like virtual machines and vMotion and container workloads, and the use of Docker and Kubernetes to manage all the container workloads. Virtualization and automation go hand in hand. And the reason for that is, so if you think about 20 years ago, if you needed a server, you would have to buy a big honking server from Dell or HP, and then you would have to wait a couple of weeks for it to arrive, and then you would install a certain application on it, and that's the only application that server ran. And then virtualization came along, which allows you to have a single physical server, but using a hypervisor, you can run multiple applications. So what that means now is you can spin up hundreds of virtual machines or even thousands of virtual machines in a matter of minutes to facilitate the connectivity for those virtual machines to be able to communicate with each other. It would be insane to think about having to go to every single network device and configuring that network device individually. That would be completely out of control. So instead, what we want to do is, as these VMs come up, we want some sort of automated way of configuring all the relevant ports, the VLANs, our routing tables, everything that we need to do to be able to facilitate the use of that virtual machine so it can communicate with other virtual machines within the environment and also to the external world if need be. So I think these are the three big reasons why SDN has taken off like there's no tomorrow. So when it comes to SDN, how is it implemented in real world? In other words, what type of solutions exist so we can leverage software-defined networking in our environment? Well, first of all, data center is the number one space in the enterprise realm where most of the technological innovation has happened over the past decade or so, especially when it comes to virtualization and automation. And the way data center SDN solutions operate is they're designed for facilitating east-west traffic flow. So what do I mean by east-west traffic flow? So if you look at this particular topology here, we got a couple of core switches, and then we got these access switches that have the different network endpoints like servers plugged into them. And on the servers, you may have different VMs that are running. Within the data center, majority of the traffic flow happens to be between the virtual machine themselves. That's what's called east-west traffic flow, meaning the traffic stays within the data center, but the traffic needs to be able to communicate with other servers and virtual machines that are located within the same data center for different reasons. And I'm going to give you some of those details momentarily. Now, there are different data center SDN solutions that exist out there. One of the most popular ones that is open standards based is called OpenFlow. And what we have here is the control plane is fully centralized on the controller, and it's responsible for building the forwarding plane of all the network devices that are connected to that OpenFlow controller. Now, Cisco has its own flavor, of course. It's called ACI, or Application-Centric Infrastructure. And the controller, which is at the heart of ACI, is called APIC, or Application Policy Infrastructure Controller. It's very elegantly named, and Cisco rarely names things elegantly, but here I think they did a great job because the whole idea is application centricity. And I will explain to you what that means as we continue moving along. The next big SDN solution is the campus or branch SDN solution, and this is designed for north-south traffic flow. Now, let me explain what that means. So as you can see, in a typical campus network, you have a three-tier design. You got the access, you got the distribution, you got the core, as you're seeing here. So, for example, this phone right here, let's say it's a voice over IP phone. If I want to call somebody outside of my organization, traffic flow is going to go from the access, through the distribution, through the core, out to the internet. And that's what's being referred to as north-south traffic. And then when the traffic comes back, it's going to take the same path back. And this is the north-south traffic flow. As you can see, this is a very different type of traffic profile as opposed to the data center profile. Data center, a lot of traffic east-west within the data center. Within branch, north-south. Hope that clarifies why we have different type of SDN solutions out there. Now, the first solution that Cisco had a couple of years ago, it was called APIC-EM. So they took the ACI APIC and they added a keyword enterprise module or EM to make it more branch-centric. And it wasn't just a name difference, but they actually changed a lot of the functionalities within that controller to make it more campus network-centric based on that 3-tier north-south traffic flow. But that was legacy. It's now called Cisco SDA or Software Defined Access. And sometimes it's also referred to as IBN or Intent-Based Networking. And at the heart of SD access is DNS Center or DNAC. And DNS stands for Digital Network Architecture. It's a marketing term used by Cisco for the campus controller. So DNS Center is the controller. So what APIC does in ACI is what DNS Center does in SD access. And finally, for the wide area network, now once again, if you think about a WAN design, WAN is very different than data center and campus. The whole reason WAN exists is to allow the data centers and the branch locations to talk to each other and to connect with each other. It's the connective tissue that allows the branches and the campuses and data centers to all talk to each other. That's why wide area network exists. Once again, a very different type of traffic profile and a very different type of architecture. The big one here is the Cisco SD-WAN. It was formerly called Viptela. Viptela is a very popular SD-WAN company that Cisco acquired a couple of years ago for north of $600 million. And it brings tremendous SD-WAN capabilities into the Cisco portfolio. As of today, the Viptela solution has been 100% integrated into the Cisco portfolio. Most of the Cisco routers within their routing portfolio today are SD-WAN capable. In order to manage the wide area network solution, there are two different types of controllers you can use. You can either use the vManage controller, which was acquired through the acquisition of Viptela. So this was the original technology that Viptela had designed, which was basically a controller for managing Viptela WAN fabric. But what Cisco allows you to do is you can still use the vManage controller if you wanted to, or you can use the Cisco DNS Center controller, which also allows you to manage the WAN in addition to managing your LAN or your campus network. So it's really interesting that Cisco is kind of bringing it all together now to make it a lot simpler for users to manage their environment. And one last thought on this topic here is, keep in mind that SDN controller could be available in a virtual form factor as a virtual machine or a VM, or it could also be available as a physical appliance. Now, the most popular way of acquiring SDN controller is a physical appliance. For example, Cisco ACI and Cisco SD Access requires you to have a physical appliance. And the reason Cisco prefers you to have a physical appliance for managing your devices is because of the stringent requirements as far as the compute resources, the memory resources, the storage required for managing the entire network fabric. Physical appliance works better because Cisco kind of designed that appliance for that purpose. But as the world is increasingly becoming virtual, Cisco is seeing that trend and are slowly moving in that direction to allow customers to have a choice of just installing a VM on the hypervisor of their choice. Now, let's quickly shift our attention to the Cisco SDN controller for the data centers called ACI. ACI stands for Application-Centric Infrastructure. What it does is it gives us a 2-tier leaf spine architecture. It's also called QoS Fabric. It's named after its inventor and designer, QoS. And by the way, interesting tidbit, this leaf spine technology was designed back in, I believe, 1950s by QoS. It was primarily designed for telephony infrastructure within the service provider realm. If you recall the old school analog telephones, to facilitate the circuit availability, that's what the QoS fabric was designed. But interestingly enough, over the past few years, leaf spine architecture has taken over the world by storm. Now, before I get into the topology of leaf spine, a couple of things I want you to, from a terminology perspective, what I want you to keep in mind is, in some literature that you read, it could be called leaf spine architecture or leaf and spine architecture, or spine leaf architecture, or spine and leaf architecture, or just could be simply referred to as a two-tier network architecture or a QoS fabric. All of these terms could be used interchangeably, but what I want you to understand is it all means the same thing. So do not get confused as you switch from one literature to another literature. Now, in the two-tier leaf spine architecture, at the bottom of our network, we have leaf switches. So in this example, we have 4 leaf switches, and we also have spine switches. And in this instance, we have 3 spine switches. And as you can see here, the way these switches are interconnected with each other, none of the spines are directly connected with each other, and none of the leaves are directly connected with each other. Instead, all leaf switches connect with all spines, and all spines connect with all leaves within that environment. So it's very important for you to keep in mind from a physical connectivity standpoint. It's a key concept. Another thing to keep in mind is it's non-blocking fabric. So today's data centers require a tremendous amount of horsepower. So you're looking at 40 gig, 100 gig, up to 400 gig type of fabric within our data center that is 100% non-blocking, all the way from the down ports that are connected into the different servers and different endpoints that are plugged into the leaf switches, all the way through the spine. And this model is horizontally scalable, meaning if you want to add more leaf switches, we can simply do so until the spines run out of capacity. And then what we do is we just add another spine. And by adding another spine, it just gives us the ability to add that many more leaves. Typically, you would want to check with your vendor. In this case, you would want to check Cisco documentation to see how many leaf switches are supported per spine, depending on the spine switch you're buying. That will tell you how many leaves are supported per spine. It's an important design concept for you to keep in mind. Also, it's an ECMP design, or equal cost multipath design. What that means is if there's a VM attached to leaf 1 and it wants to talk to a VM on leaf 4, all 3 links that leaf 1 has and all 3 links leaf 4 has are 100% active. There is no active passive anymore. It's all 100% active, and we can send traffic in a load balanced way across all available links at any given point in time. And it's very, very powerful. And finally, an important element to keep in mind from the ACI design perspective is the predictable nature of this design. So in the 3-tier architecture, if you guys recall, we also had sometimes what was called collapsed core, meaning the core and distribution was collapsed into a single layer, which also kind of mimicked a 2-tier architecture, but it wasn't exactly 2-tier architecture. And plus, sometimes you would have a single link between the core. Sometimes you would have like an ether channel with multiple links bundled together to facilitate traffic between the core. What that did was that created a lot of one-off snowflake type designs. When it comes to automation, we don't want any snowflake design. When it comes to automation, what we want ultimately is a predictable design that is always the same across the board, because that's what facilitates network infrastructure automation. So in this example, let me show you something really cool. So let's say there's a VM on leaf 1 that wants to talk to a VM that's attached to leaf 4. What would happen is Leaf 1 would take this path and go down to leaf 4 using this path. It can also leverage other paths as well, but ultimately it doesn't matter which path it takes, it's going to be able to reach that virtual machine. So what that means is each virtual machine is 2 physical hops away. This is 1 hop right here, and this is the second hop right here, all the way from here to leaf 4, right? So 2 physical hops. Why 2 physical hops and 1 logical hop? As I explained, there are 2 physical links, but logically we could be using VXLAN overlay technology. So these VMs think as if they're directly connected with each other. In reality, they are 2 physical hops away, but logically they think they're just 1 hop away. So that's the whole idea of underlay overlay, which I will also discuss in a moment, but that's what you get with this design. Now when it comes to Cisco data center switch portfolio, you have the class of Nexus 9K switches. For leaf switches, you can buy the Nexus 9300. There's a huge variety of different options within the 9300 family that you can buy. And from the spine perspective, you have this Nexus 9500 available to you, and it comes in different form factors like the 9504, 9508, 9516. That gives you the ability to be able to have modular type chassis supporting the spine. I wanted to let you know what options are available to you when it comes to designing and architecting your network within the Cisco portfolio. Let's dig deep into the physical design aspect of ACI. So we already talked about the leaf and spine switches. Well, all the endpoints connect into leaf switches. Nothing connects directly into the spine. Now, there are some designs where certain elements may plug directly into the spine, but that's a more advanced level concept, CCNP, CCIE, and more real-world type concept. At a CCNA level, for you, keep in mind that nothing plugs into the spine. Everything plugs into the leaf when it comes to network endpoints. So that would be APIC controllers. And typically you would get a cluster of 3 APIC controllers to be able to have a quorum for high availability and redundancy. You also have bare metal servers that may be dual homed into the different leaf switches, for example. You could have different VM workloads that are running on different physical servers based on the hypervisor of your choice, ESXi, KVM, Hyper-V. You could have different type of container workloads that you may be managing through Docker or Kubernetes. You could have an external layer 3 out router, which basically connects you to a non-ACI fabric. So if you have a legacy data center that hasn't been fully migrated over to ACI, you could use the external L3 out router to be able to connect to that network. You could also have firewall, IPS, load balancers, all that layer 4 through 7 services also connected directly to the leaf. So as you can see, you get the idea here. Nothing plugs into the spine. The only thing that plugs into the spine are the leaf switches, the uplinks of the leaf switches. But all the endpoints plug directly into the leaves, including the APIC controller. Okay, so this is a gotcha. Some people may think, well, the APIC controller should connect to spine. No, it doesn't. APIC controller connects to the leaf. Even though everything is being done through the APIC controller, but it still connects to the leaf. That's by design. Now, let's talk through the underlay versus overlay. I'm going to keep it very simple. Everything you're looking at on your screen right now from a physical network standpoint, that's all called an underlay. Physical spine switches are underlay. Leaf switches are underlay. Bare metal servers are underlay. Routers are underlay. Firewalls are underlay. But then what becomes overlay is, for example, we may have a VXLAN tunnel between 2 VMs that are riding on top of this underlay physical infrastructure to allow them to communicate directly with each other. That happens to the VXLAN overlay that rides on top of the underlay that we built. Now, the cool thing about the overlay technology is it's regardless of how the underlay is designed, we can create different type of topologies to facilitate different type of communication. For example, using ACI, we could do vMotion between data centers, even though in between the leaf and spine switches, it's all layer 3 connectivity, but we could facilitate a layer 2 And for vMotion, we need layer 2, basically, which means we need to be on the same subnet. Using VXLAN, we can extend and we can create an end-to-end tunnel between the data centers to allow a vMotion to happen between two physically, geographically dispersed data centers, thanks to the VXLAN overlay. So these are some examples. Now, at a CCNA level, that's all you want to know. At a CCNP and beyond, we're going to go into a lot more detail into ACI. And there's a lot of different logical constructs that are part of the overlay, like tenant, bridge domain, EPGs. We'll discuss few today, but to understand at a lot deeper level, you have a lot more going on that we'll discuss at some point in the future, but I'll still give you some additional insight into ACI. Now let's look at the logical design of ACI. Like I said, there's a lot of logical constructs within ACI. And the big thing with ACI is it could be scary for people at first because it's a paradigm shift. You no longer define VLANs and subnets in a traditional way. It's a very different approach. It's an application-centric view of the world. Remember, networks exist for applications, not the other way around. So networks are basically plumbing that allow applications to ride on top of. From that perspective, Cisco completely reimagined how data centers could be automated. And that's what ACI does. And there's a term called IBN. I kind of touched on it earlier, intent-based networking. Once again, the idea is, as a human operator, we want to define the intent of what we want the network to do in a very abstracted way, in a human-readable format, and then the controller can then take our intent and convert it into technical realm, things like CLI commands and netconf configuration, to be able to go and program our network. In order to help you understand ACI logical constructs, think of a typical web application. A typical web application has a web tier. It's a 3-tier application architecture, not to be confused with a 3-tier network architecture. This is a 3-tier application architecture. So a typical web application has a web page that users connect to. That's called the web tier. Then there's an app tier. So basically anything dynamic. So for example, if I go to google.com, it presents me with the web interface. But if I go to Gmail, then all of a sudden there's dynamic elements attached to that email. And all those dynamic elements are presented to me through the app tier. And then the third one is the database tier. And this is where all the information is stored. This is, for example, where my email profile might be stored. This is where all of the email data is stored. So that's the way a typical web application is designed. Now, one additional thing to keep in mind is you have an external tier, which is basically a set of routers at the edge of our network that allow the outside users over the internet to connect to the web server. And in ACI, we have what's called a policy contract, which dictates how that traffic flow is going to look like. And the reason we have that policy contract in place is to only allow legitimate traffic and potentially segment off any attempt at hacking our network. If the external users want to connect directly to the app tier or the database tier, we're going to say exclusively as part of our external tier that we're not going to allow for that to happen. External tier can only talk to the web tier. And similarly, we can say in another policy contract that web tier can only talk to the app tier. And similarly, app tier can only talk to the database tier through another policy contract. Now, if you were to combine all of these policies and EPG at the bottom of the screen that you're seeing in front of every single tier is endpoint group. And what endpoint group or EPG is a collection of different endpoints that are part of the same group. So for example, if I have a bunch of VMs that are serving my web users that are all part of the same web page, collectively they would become part of the same EPG or endpoint group. Similarly, I will have different application VMs that are also facilitating the web functionality. They would similarly be in one endpoint group. And similarly, database. All the different instances of databases that I may have running in the background would also be part of the same EPG, and same thing goes for all the external routers that are performing the same function. Now, ultimately, what ends up happening is that those EPGs, or the endpoint groups, and the policies, the way those EPGs can talk to each other, this is what's defined through the policy. An application network profile is designed per application. So what you're seeing here is for a very specific web application, but you could imagine you may have dozens of different applications in our network, and for each application, you would define a different application network profile with unique policy contracts to define how the communication flow is going to look like. There's also an element of microsegmentation and security that's kind of built in. There are different approaches. We could go very deep and do things at a microsegmentation level, or we can keep things at a very high level. At CCNA, we're going to keep it at a high level. Now let's shift our attention to the Cisco SDN controller solution designed for the campus networks, SDA. SDA stands for Software Defined Access. It's Cisco's campus network automation solution. So remember, with SDN technology, the general idea is to automate the deployment of our networks. We're trying to decouple the hardware from software, so it becomes a lot easier for us to onboard devices or to deboard devices. At the heart of the SDA solution is the DNA Center Controller, or the Digital Network Architecture. This is the brain of the entire solution. It's an appliance that provides a centralized graphical interface to design your network, add and configure devices, monitor your network and devices, and troubleshoot your network. So it's an all-in-one, single pane of glass solution. SDA manages and automates campus infrastructure that includes both the wired and wireless. So if you have a desktop computer that's plugged into a switch via an Ethernet cable, that would be a wired device, as compared to a wireless laptop connected to your network. SDA brings it all together under a single pane of glass for management and automation purposes. And for those of us that are familiar with APIC-EM, SDA is the next generation APIC-EM. You may still have APIC-EM deployed in your environment today, but APIC-EM has now been phased out, and it has now become DNA Center. SDA is composed of three components: the overlay, the underlay, and the fabric. Now, at this point, because I just wrapped up talking about ACI, I'm sure the concept of overlay, underlay, and fabric is pretty clear in your head, but I will still go slightly deeper because the idea of how the underlay versus overlay operates is a little bit different per SDN solution. So when it comes to SDA, we have the underlay network. That's the network infrastructure. These are the physical devices within our network. That includes all the switches, routers, firewalls, wireless access points, wireless LAN controllers, all the end hosts like the servers that are connected to our network, or the end machines that are connected to our network. And we also have the underlay control plane concept. So the control plane here being the routing protocol. In case of SDA, it's ISIS, could also be BGP, depending on the network we're trying to connect to, and the routing protocol supported by it, but that's all part of the underlay. And what we have on top of the underlay is called the overlay network. And the overlay network has its own overlay control protocol, which in this case is VXLANs. And with overlay, the idea is we have virtual machines, we have virtual switches, we have virtual constructs that we build on top of the physical infrastructure that allow us to be very flexible. And with an overlay tunneling protocol like VXLAN, we have the ability to carry packets within our network, even though our infrastructure is all layer 3, we can still transport layer 2 packets over a layer 3 network. That's the beauty of VXLAN. And the whole idea here is the encapsulation and decapsulation of VXLAN. So the encap happens when a packet enters the network. So when the packet from this server to the left comes into this switch, the switch is going to perform an encapsulation procedure. It's going to take a packet that's coming off of either a VLAN or a trunk link that is carrying multiple VLANs and encapsulate it into VXLAN. Now, throughout the fabric, that packet is going to be a VXLAN packet. But when it's ready to exit, let's say the traffic is destined for this machine right here, when this switch is going to hand the packet off to this endpoint, what it's going to do is it's going to go ahead and remove or decapsulate the VXLAN header and look at the VLAN information and move the packet along. So as you can see, the end hosts are still speaking VLAN, but within the fabric, we have VXLAN that is transporting the packets for us. Now let's quickly look at what makes up the entire SDA solution. What are the key constructs that make up SDA? And on this slide, I'm going to explain the fabric roles and the associated terminology. So the first device in our network, which is the key to the entire solution, is the DNAC controller. This is a physical appliance that you have to acquire from Cisco. And typically in a practical production environment, you would want to have a cluster of 3 forming a quorum, so you have high availability and redundancy in your environment. And once again, this is the brain of the entire solution. This is what provides the GUI-based portal that you log into. And this is where you define all the constructs necessary to configure your entire network. DNAC controller also supports northbound APIs like REST API. So if you're using tools like Ansible, Chef, Puppet, or any other automation tool of your choice to be able to program your network, whether it's spinning up switches or wireless LAN controllers or APs, it can all be automated. That's what's cool about this entire solution. Instead of touching each device hop by hop, we use a centralized model for configuring the entire network. Now, the next component is ICE, or Identity Services Engine. Now, this is very important for the SDA solution to operate because users are authenticated by ICE and the security policy is configured in Cisco DNA. SDA helps ensure policy consistency by defining and enforcing policies preventing unauthorized access and user mobility. And another very important component of the SDA fabric is analytics engine called NTP. Stands for Network Data Platform. It's an analytical engine that collects information about networks via things like NetFlow and logging and SNMP. And it's just a centralized ingestion point for all of those monitoring/management protocols for deep visibility into the entire fabric. And it also has a little bit of artificial intelligence and machine learning built into it. Now, when I use these words, I don't use them. So what does AI and ML actually mean, besides being buzzwords? What it ultimately means is we're trying to make our networks so intelligent that they mimic a human brain. So how a network engineer would actually troubleshoot and monitor the environment, that type of intelligence is built into the analytics tool called NTP. Next up is control plane nodes. And the control plane nodes are responsible for mapping the endpoint ID to different devices. And control plane nodes use Lisp protocol, and Lisp stands for Location ID Separation Protocol. It's a really powerful protocol, and this is what allows mobility to happen within the fabric, where you can unplug a device from one part of the network, go to another part of the network, and it can just magically come up without the network administrator or operator having to reconfigure that port. But once again, this is a more advanced CCNP, CCIE level topic. I'll go into more detail when I launch the CCNP course. Fabric border nodes. Now, these nodes are at the edge of the network. And that's why they're called border nodes, because they're literally sitting at the border of our network, and they connect the fabric, the SDA fabric, with the non-fabric solution. So for example, let's say you have 1,000 sites within your network, and the very first site you decided to deploy SDA to is going to need to be able to talk to the legacy or the traditional network devices. This is where the border nodes come in. They have the ability to translate the fabric constructs into the old school constructs that you may have in the rest of your environment that hasn't been migrated fully to the SDA solution yet. Then we have the edge nodes. So these are the access switches. So if I were to give you, so the best analogy I can give you here is these are like your access layer switches. And this is where the wired endpoints plug into the network. This is where the devices are onboarded into the network. And we also have the fabric wireless controller. This is the wireless LAN controller. And this is where all the wireless endpoints are terminated and controlled and managed. And then we have these intermediate nodes that are part of the underlay. You can think of intermediate nodes as distribution layer. They do not participate in the overlay, but they primarily participate as an underlay, meaning they provide physical connectivity for the access layer switches to be able to connect up to the core or the fabric border nodes by being intermediaries, hence the name intermediate nodes. And once again, in a traditional layer 3 design, we have access distribution core. This is exactly what you can think of here in this design. And one final thought from a design perspective that I want to leave you with when it comes to SDA versus traditional access layer design is what SDA brings to the table for us compared to what we traditionally had in our networks. So today, if you haven't been migrated to SDA yet, what you have most likely is a user connected to an access switch, as you can see here, that is dual homed into distribution layer switches via redundant links at layer 2. And then the distribution layer switches might also be connected with each other via layer 2. And the rings on top of the redundant links are representing ether channels in this case. So we can kind of bond all the links together and take full advantage of the throughput of the combined ports. So once again, access layer switches, layer 2, distribution layer switches at the uplink level most likely will be layer 3. But down below to the access layer, they're all purely layer 2. In this design, of course, we'll have spanning tree. And most likely you'll be running rapid spanning tree because that's a default spanning tree protocol on all the switches, Cisco switches. And what spanning tree does is it goes through an election process. If you want to learn more about that, you can watch my video I did on layer 2. And I have a fully dedicated video on the spanning tree protocol. You'll learn all about it. And once a route is selected by the spanning tree, what ends up happening is it then goes through the process of blocking certain ports. So in this instance, as you can see, it's a shame we just lost half the capacity. We literally lost one leg that was going up to distribution 1. It's pretty much non-functional because that's what rapid spanning tree does for us. So rapid spanning tree is a good technology because it blocks redundant links, but it sucks from a perspective of taking full advantage of our investments, because now it's a shame that we can't take advantage of additional capacity in our backbone. Now, another layer on top of that would be HSRP running on distribution 1 and distribution 2 to provide gateway redundancy. Now, I also did an in-depth video on first hop redundancy protocols, and I went deep into HSRP. Feel free to watch that video. I'll also provide a link you can tap on. And here on our gateway machine at the bottom of the screen, it's going to have a gateway IP that it's going to pick up from a DHCP server, and this is where it sends all the traffic when it doesn't know who the host is on the network or outside the network. And HSRP provides that gateway level of redundancy. But once again, it's a shame that STP blocked that link for us, and we can't take advantage of it. However, if the other side going to distribution 2, if that link were to go down, or if distribution 2 were to go down, if that switch were to went down, then the other side is going to come up and we're going to be able to speak to the router that is running as the primary HSRP gateway, and life will be good at that point. But as you can see, there are some limitations with our traditional design. Now, let's look at the SDA access layer to the right of the screen. And ultimately, what we call this design is active-passive design, because that's what we're dealing with here. Now, let's contrast this to the SDA access layer design. So to the right of your screen, you're seeing an access layer switch that's plugged into distribution switches at the top, and these are all layer 3 links. Once again, they're all bonded using Ether channel. And the access layer is layer 3, distribution layer is layer 3. We have layer 3 everywhere. We have no spanning tree. And because we have layer 3 everywhere, it grants us to run a routing protocol like ISIS, or intermediate system to intermediate system, which Cisco uses in SDA, to be able to build the underlay of our network. And because we're running layer 3 everywhere, the gateway now becomes the access layer switch. So as you can see, it's low latency because the traffic is not having to go all the way up to distribution layer switches. And it's right at the source of where the access switch is. And as we move this, let's say this laptop, from this switch to another switch in the network, using the magic of Lisp, which I'm going to discuss in much more detail in my CCNP CCIE course, you'll get to see that what ends up happening is Lisp automatically allows mobility to occur. So this user can then go to another switch, connect their device, and be still connected to the entire fabric without having a human operator or a network administrator having to configure that port that they just plugged into. And this is what we call an active-active design, because we're doing some sort of load balancing using a hashing algorithm. And we may be doing either a flow-based load balancing, or we may be doing per packet-based load balancing, but typically it's flow-based. But the idea here is we're distributing the load of the traffic, and we're fully taking advantage of our investment using active-active design. Now let's shift our attention to cloud architecture overview. So before I get into cloud, I think it's important for us to take a giant step back and see where we came from and what eventually led to the cloud. There are different types of physical servers. I want to give you a preview of, let's say if we were to wind the clock back to 1980s or 1990s or even early 2000s for that matter, we would go ahead and buy, in this case, a tower server. Here we have a Dell PowerEdge T550 tower server. It's suited for small business. And it looks like a desktop computer. For those of us that actually have a desktop computer at home, it looks very familiar. So at the front of the computer, we got a couple of USB ports, we got the power button and all that jazz. On the back side, we got a power outlet, we got a VGA, or we got an HDMI cable that connects to the monitor. And then we got a couple of network Ethernet jacks that are basically network interface cards that allow us to connect to the network. So that's what we have in a tower server. Now in the middle of the screen, what you're looking at is a CPU, which is part of any server. You have all of these slots right here in the middle. These are all memory slots. And what you do is you insert memory chips. So these are all memory chips that are inserted in memory slots, and that provides memory to us. And all of these are storage devices or hard drives that provide storage to us. And one additional component is we may have graphic cards or GPUs, graphical processing units, within our server. And what has happened is over the years, software developers have realized that GPUs provide much better capability for running algorithms. They can process the algorithms, advanced algorithms, at a really, really rapid, fast pace as compared to the general purpose CPU that we may have inside of our computer. So to offload that functionality, we're now seeing GPUs as part of the server package for offloading those advanced mathematical algorithm functions. And that pretty much is what a tower server is in a nutshell. Now here's another type of server. As you can see, the difference is the previous server was vertical. This is horizontal. And this is a much slimmer version of that server that we were previously looking at. And I'll explain the purpose of this in a moment. But as you can see, front, very similar. We have a power button. We have a couple of USB ports. We have a mini LED display here, which actually shows us our IP address, which is very handy and neat. And at the bottom here, we're seeing how the backside looks like. So we got a couple of power outlets. We got network interface ports. We got the VGA. We got USBs and all that. It's no different than the tower server. The only difference is the form factor. It's a 1U form factor. And what 1U in this case means, it's a 1 rack unit. So typically in a data center, we would have a rack that is 42U. That's the height of a typical data center server rack. And what we do is we take these servers, these 1U pizza boxes, we also call them pizza boxes, and we slide them inside of that rack. And what that means, if it's a 42U rack, it means we can potentially insert and populate 42 of these servers in a single rack. Now that said, typically that's not how you do it. Typically you have different sections of the rack dedicated to different type of devices. So you may have servers at the bottom of the rack, but at the top of the rack, you are going to have a couple of switches. Typically, that's how a rack is designed. Now, here is an example of a Dell PowerEdge R650 rack server. It's typically designed for small to medium business. In the previous example, the tower server is more suited to very small business if you only have one location or maybe a couple of locations. This, when you need a large data center environment, you're going to need these rack servers. And the next level beyond the rack servers is what we call blade servers, okay? And what you're looking at on your screen is a Cisco UCS 5108 chassis. And right now it's a blank chassis on your screen. And what this chassis is giving us the ability to do is, as you can see, we have different slots. We have 8 different slots to be exact. And we have the ability to insert 8 half-width blades in the server chassis, or 4 full-width blades, or we can have a mix of both. Now let me show you another picture where the server is fully populated. And kind of taking a step back, blade server is a server enclosure with multiple modular circuit boards. And here in this architecture, these are B-series blade servers for UCS. By the way, UCS stands for Unified Computing System. And what we have here is, this right here is one server. This is half width. This is another half width. This right here is the third server. This right here is the fourth server. And then, as you can see, the bottom half, we have two servers down here. And these are full width blades because they're taking up the entire width. So we have 6 servers in this instance installed in a mixed environment. Now, what are these servers for? We may be running different type of applications. We might be doing Cisco Unified Communications Manager, CUCM. We may have UCCE. We may be running different type of databases, etc. You name it. Any type of server you can think of, you can go ahead and throw on these servers. And the cool thing about the blade servers is that they provide a very small hardware footprint because you can have a lot of horsepower all condensed into a very small footprint of this server. And by the way, on the back of this server, we're seeing the power outlets. And as you can see, the reason we have multiple power supplies here is for power high availability and redundancy, because we don't want one power supply going out and bringing down our environment. And typically these servers are running critical business functions. This could be like your website. This could be the key database that all of your employees are using. So this is serious stuff. And you absolutely need to make sure that you have power redundancy. So typically you would want to populate the all of the power supplies. And it all comes down to how many blade servers you're using. If you're using maybe just 2 or 3 of half-fit blades, you may get away with just having 2 power supplies for redundancy purposes. But if you're going to fully populate the chassis, then you better have all slots for power supplies 100% populated. We also have fans on the back here, as you can see. And then we also have these FIs. They're called fabric interconnects. And these are the network interface cards that we were talking about that allow the servers to be able to connect to the rest of the network. So we literally have an RJ45 coming out of the fabric interconnect, plugging into a physical switch that we may have, which could be a top-of-rack switch in this example. Now I'm going to zoom into the physical server architecture, like what's inside of a server. Well, I already gave you a clue. We got the CPU, we got the RAM, which is memory. We got the storage, which is the hard drives. We got the network, because ultimately that server needs to connect to the internet or the rest of the network, right? What we have on top of it is the operating system. Now you can think of the operating system as a manager that has multiple employees that it's managing. So the CPU, RAM, storage, network all become the employees that the operating system as a manager is managing. For what? Ultimately, we're going to be running an application on that server. I gave you the example, like a call manager, right? Which we now call CUCM. Could be the call center solution, the UCCE. Could be any type of database or the application of your choice. Could be any application. Could be a web server application, right? But ultimately, the idea here is we have the underlying hardware. Then we have a layer of software that is managed through operating system, which becomes the middleware, so to speak. And then that middleware manages all the physical resources that that application needs to be able to function. This is how traditionally we deployed servers. For each application, we bought a separate physical server. Now that changed in early 2000s when virtualization started to take hold. Thanks to VMware, there were other virtualization solutions on the market way before VMware, but VMware is what commercialized the virtualization technology for the masses. And since then, VMware has been the most successful virtualization company on planet Earth because of their ability to be able to take the physical server and do some magical things with it. And what do I mean by those magical things? I'm going to explain on the next slide. So now we take the same physical server that has CPU, RAM, storage, and network, but instead of an operating system, we install a hypervisor. So I gave an example of VMware. VMware's hypervisor is called ESXi. Microsoft has their own hypervisor. It's called Hyper-V. We also have KVM. So there are different type of hypervisors that are available on the market that you can leverage that are installed on top of the server. And then what that allows us to do is to provision virtual machines or VMs on top of that hypervisor, but each VM has a certain amount of CPU, RAM, storage type of resources allocated. So for example, in this case, it's app1. Let's say it's a web server. So it may need 8-core CPU. It may need 16 gigs of RAM. It may need 200 gig of storage. So what we'll do, the hypervisor will look at the request for this web server, and depending on the options we picked when we were configuring this, let's say we're using the VMware vCenter solution. So we're in the vCenter in a GUI, we are configuring a VM, and that VM has a certain amount of vCPUs. It has vStorage, it has VRAM, it has vNetwork, and all of those things are being provisioned by the hypervisor. And on the physical server itself, which is called a host, we may actually have a 24-core CPU server. And we may have 96 gigs of RAM. And we may have 1 terabyte of storage. And we may have redundant 10 gig network interface cards on the server. But each virtual machine is just going to take a small slice of these resources that are located on the host machine. And it's all done through the magic of hardware virtualization. So now we understand how a server is virtualized, but now the next question most likely in your head would be, how do we connect the virtual machines to the physical network? How does that happen? Great question. So remember, at the top, we got the virtual machines. Then right underneath that, we got the virtual hardware. And then what ends up happening is the network component of each virtual machine may have a single VNIC or a virtual network interface card, or it may have multiple VNICs. But ultimately, all these VNICs from different VMs terminate into a vSwitch or a virtual switch. This is a virtual network. It's not physical. It's all logical constructs. And then we have the physical world. We have a physical network. We have a physical switch. And what ends up happening is the server has physical NIC cards on it, right? So we would take those physical NIC cards, those two 10 gig ports that I was referring to on the previous slide, we would go ahead and plug them into the physical switch, into the 10 gig ports. So by having redundant links, we have high availability and redundancy. Most likely those are going to be trunk links, which means they're going to be carrying multiple VLANs, because most likely if you have multiple virtual machines, each virtual machine may be in a completely isolated VLAN. Some VMs may share certain VLANs if you have a reason for them to share VLANs. But in other instances, we may be completely isolated. That's totally okay, because we could make the routing happen at the physical switch level. Ultimately, this is how the physical NICs are mapped to the virtual environment through the vSwitch or the virtual switch. And the next thing I want to talk about is I want to slowly shift us into a more bigger picture concept. So how about the physical data center network architecture? Within a data center, what do we have? Well, we have rows and rows of racks. And within each rack, as represented in the picture here, we have servers underneath, typically at the bottom of the rack. And then what we have at the top of the rack is called TOR switch or top of rack. That's what TOR stands for, top of rack switch. So we have multiple top of rack switches for high availability purposes, of course, and for dual homing purposes. And then what ends up happening is those top of rack switches ultimately get aggregated and terminated into aggregation switches. And those aggregation switches would ultimately connect to the core of our network, which would connect us to the outside world. This is typically how a data center is configured physically. Now, how about a virtualized data center? So once again, a data center is racks of servers, switches, and storage area network or SAN, and you have rows and rows of those racks within a data center. And what you're seeing in this picture here is actually cabinets. These are more advanced than racks. Cabinets have a nice enclosure, they have a door in front, and they provide a form of physical security. And what we have here is a customer who could be a developer or an operator within our network, and they may need to run a certain application. So let's say they came up with an idea of a brand new application, which is going to revolutionize our business. Well, to run that application, they're going to need resources. They're going to need CPU, memory, RAM. They're going to need server, right? So what they're going to do is they're going to create a change request into some sort of a ticketing system. That's how their request typically shows up. So they're going to log into two most popular systems out there are ServiceNow or Remedy. So they're going to generate a ticket in one of those systems asking for whatever resources they need. So they may have a business justification. Hey, I designed this new app called Nudge app. It's going to be an awesome web app, and I need 8 core CPUs, I need 16 gigs of RAM, and I need 100 gig of storage. That's the request in the ticketing system. Now that request will generate an alert, and the data center engineers, and that data center engineering team most likely is going to be composed of server engineers, network engineers, storage engineers. They're going to get that request through the ticketing system. They're going to analyze that request, and then they're going to go ahead and log into a tool like VMware vCenter and go ahead and through the GUI configure things. Or they may also use an API using a tool like Ansible, Chef, Puppet for automation to be able to translate that ticketing system request into the resources that that team needs. And ultimately, you're going to add, move, or delete virtual machines. And once again, virtual machine has a CPU, memory, storage, and network piece attached to it. You're going to take all those components and get the resources provisioned, and then ultimately end user gets an email saying their ticket request has been closed and the resources that they have requested to have been successfully provisioned within the data center. Now, this virtualized data center workflow typically could take days up to weeks. It just depends on how well designed your system is and how well designed your teams are. What if you have critical team members that are out on vacation? Well, you may be in a world of hurt. Things will be really slow. It may take a month or so for that request to be processed. Now, in today's world, it's not acceptable. So what that led to is a private cloud architecture, which we also called IaaS or infrastructure as a service type mindset. Here, what we're doing is we're offering our infrastructure as a service to our end customers, which could be developers, application designers, software developers. And we also call that on-prem. You would typically, when you're reading different literature, you're going to see this terminology constantly come up, on-prem or on-premise. It's typically being referred to a private cloud or private data center type environment. So once again, we have a customer or a developer in this case, same request, but here, instead of going to a ticketing system, they may go to a web page and they may select, okay, I want to add this VM that basically has 8 core CPUs, 16 gigs of RAM, and 100 gig of storage. That may be available as a small VM option in the organization. And when they do that, through the magic of API or Application Programming Interface, and I actually did several videos on API, so feel free to browse through my playlists. But ultimately, through the magic of APIs, what's going to end up happening is that request is going to get translated into the virtualization software through GUI or some sort of an API, most likely through an API. And ultimately, what that means is the resources will get provisioned within the data center. Now, what's cool here, as you guys can notice, as compared to the previous workflow, we don't have the data center engineering team in the middle of the workflow. We literally removed that team. And I'm sure the minute I said we no longer need data center engineers involved in the workflow, that probably drained all the blood out of your face. Before you freak out too much, here's the cool thing. We still need data center engineers. Now it's called a cloud engineering team, but the idea is it's the same team, but their job function is that they're the ones who are making the cloud services catalog available to the programmers, right? So how is it that a developer can go to a web page and then select, small VM, medium VM, large VM, whatever they need to be able to do their job and, deploy apps and whatnot? How do they get that? Well, cloud engineers made that available because remember, this is on-prem. So our team made it available. And then another thing cloud engineers did was they actually configured the virtualization software for it to be able to understand that automated workflow, which is step number 2, through the API operation. So it's all like behind the scenes, there's no magic, right? Basically, the cloud engineering team is the Wizard of Oz in this design, if you will. So if you're a data center engineer, your job is not going anywhere. If anything, you're going to become more and more relevant because now you are part of a strategic IT operation. Instead of just being an expense center, you're now truly a business partner because you're providing a service to the customers, which are employees in this case. So what is a public cloud? A public cloud is somebody else's data center. That's the most simple definition I can give you. Managing servers is their headache. Managing power is their headache. Managing cooling is their headache. All the cabling infrastructure that you have to deal with within data center. It could be a lot just to manage the data center. Data center is a beast in itself. And you typically have experts that have lived their entire life in just managing and maintaining and feeding the beast called the data center. Okay? In the public cloud realm, that beast is managed by somebody else. It's no longer your headache. And this is a huge time saver, potentially money saver for you as a company. If IT is not your core business, then you shouldn't really be doing all the things we have been talking about up until this point. You should actually use a public cloud-like service through companies like AWS, Microsoft Azure, or GCP, Google Cloud Platform. These are the 3 big gorillas in the cloud arena, and you could be using any one of them, or maybe you may have a multi-cloud strategy or a hybrid cloud strategy. But ultimately, the idea is it's also an infrastructure as a service type idea, but here you're no longer doing any of those things. It's all completely outsourced to the third-party cloud provider. And once again, the idea here is you still have the enterprise customer, developer, operator, right? And most companies that end up going to the public cloud, they implement this methodology called DevOps. And if you were to separate the 2 words, Dev stands for development, Ops stands for operations. So the idea is we take the best practices from the software development team that we have, and we incorporate it into the IT operations. And we create a set of practices that allows us to become very agile in our business. So what I mean is typically network provisioning is a very slow process, right? That's the longest pole in the tent, if you will, when we're doing things. And we no longer want the network to be the bottleneck in our business. So using the DevOps type methodology, CI/CD type pipelines, which is continuous integration, continuous development, and continuous deployment type pipelines, we're able to accelerate how many services we can offer to our customers and be able to launch software at a really rapid pace. In this case, provision software and provision network at a really fast pace. So our customer goes to a web page, which in this case could be an AWS customer portal. They'll log into that and they'll select whatever it is that they want to provision, let's say a small VM. And then when they do, through the magic of API, There's a virtualization software that AWS runs. It's their secret sauce. And they go ahead and provision the resources within their data center, whatever that request might be. Once again, it's the same type of request. X number of CPUs, X number of RAM, X amount of storage, and certain type of network capabilities. All that is provision. Now, here, as you can see, the red box, the dotted line box that I'm showing here, it's completely outside of our management. We're not doing any of those things. Our people can just go ahead and get whatever they want through the Cloud Services Catalog. That is completely managed by AWS or Azure for that matter, or Google for that matter, depending on the cloud. So that's pretty much it. This is what a public cloud is at a very high level in a nutshell. Welcome to CCNA 200-301 course. Today is the final video of the CCNA series. I'm very excited about that. Section 6, Part 2. Today's session is a deep dive in network automation. Here are the topics I plan on covering today. First, REST API overview. Second, data serialization and JSON overview. Third, DevOps overview. Finally, I'll wrap it up with an overview of configuration management tools such as Ansible, Chef, and Puppet. Let's go. First, let me start off with a REST API overview. Now that said, in my previous video, I went really deep into this. So here, I'm just going to provide a very high level overview. So if we look at an SDN controller, which it becomes the central management point of our entire network, there's a couple of terms that you need to understand. First, what does an API stand for? Application Programming Interface. Now, an SDN controller has northbound APIs and southbound APIs. When it comes to southbound APIs, these are the APIs that speak to the south of the SDN controller. Network devices like routers, switches, firewalls, load balancers, you name it. Any network appliance that is managed by the SDN controller is a fair game here. And it uses protocols like OpenFlow, which is an open standard protocol, or OpFlex, which is Cisco proprietary. It uses SSH, SNMP. It could use netconf or a combination of all to provision the network, to monitor the network, to configure the network. Basically, everything we did in the past with CLI and a lot more can now be done using the SDN controller through GUI and using APIs. And from a northbound perspective, what we have is a northbound API. And typically, northbound APIs use RESTful or REST APIs and sometimes Java APIs. And the whole idea here, guys, is if I have a browser on my laptop, for example, I can connect to the SDN controller. And when I do, using my browser, I'm actually using a northbound API to speak HTTPS, for example, and have GUI access into the controller. This is a very rudimentary form of a northbound API. But if you want to take this to the next level, is we can use third-party automation tools like Ansible, Chef, Puppet. These three I'll cover later in this video today. But the idea is that I can use applications on the northbound to be able to program my network intelligently and in an automated fashion. Now, a couple of additional terms, because with APIs, it's very important to have a really good grasp of the terminology. For the rest of the information to sink in, you gotta understand the terminology. So there's this term called CRUD. It comes from the software development realm, and it stands for, the C in CRUD stands for create, R stands for read, U stands for update, and D stands for delete. And it's directly related to the HTTP verbs that we can use to be able to manipulate data that we would like to manipulate. And there's also a function that's attached to each. So let me explain. So the term create in CRUD equates to post in HTTP, which actually means create a URI. You can think of a URI as an object. So basically what we're saying when we post something to HTTP is we are basically creating an object. When we say HTTP GET, we say we're reading an object. When we say HTTP PUT, we're saying we're updating an object. And when we say HTTP delete, that means we're deleting an object. So that's what the term CRUD stands for. There are a lot more HTTP verbs than these four, but just to simplify things, I think these four are the most fundamental and crucial for you to understand before you get into more advanced level stuff. Now, some conceptual level understanding of HTTP verb and URI. So if you were to look into a packet that actually has HTTP verbs and URIs contained within it, when we zoom into it and we look at the headers of that packet, we're going to see the layer 3 header, the layer 4 header, and then the rest of the information. Now, when we zoom into the HTTP side of the house, what we'll see is we have HTTP request header and then we have HTTP other headers. Now, typically the verb, HTTP verbs we just looked at are contained within the HTTP request header. Also, the URI or the object is also contained within the HTTP request header. However, the API parameters, like, whatever we're trying to update or delete or any type of parameters that we pass through the API are contained and located within the HTTP other headers. Now, if you were to look at, for example, a request called HTTP GET URI. So what does GET mean in HTTP? So if you guys recall, the previous chart we were looking at, GET means to read. So here I'm saying HTTP, go ahead and read me an object. And what object is that? It's a URI 2. Now, what does that mean? So I actually have a REST server, which in this case could very well be the SDN controller. And it's got different URIs stored on it. So URI 1 will have a resource and variables attached to that resource. URI 2, resource variables. URI 3, resource variables, so on and so forth. Now in this request, I'm very specifically asking for URI 2, which in this instance could be, hey, I want to go ahead and get a read on all the live interfaces on this router. And with this request, that's exactly what I'm going to get back from the HTTP REST server, which in this case, like I said, could very well be the SDN controller. Now, kind of zooming into it a little bit more, typically when we're using an API to manipulate things, either we're going to be doing things through a GUI or we're going to have some sort of a configuration management tool that allows us to create scripts and run scripts against the northbound API. So what is a URI? So here I'm going to give you a more in-depth view of a URI. So if you look at a typical URI, it looks like a URL almost, like the URL you guys are familiar with, right? Which is a uniform resource locator. When you go to a website and you go to a certain page, the complete address is called a URL. And in this case, in URI, it's very similar to a URL. We have a protocol, which in this case is HTTPS over port 443. We have a server URL. So in this case, it's NOJ DNAC. DNAC stands for DNA controller, which I talked about in my previous video. And then finally, the part in green is the resource path of where that resource is located. Now, the entire structure that I'm showing you here is called a URI structure. This entire thing is a URI. And to take it a step further, what we have here is, once again, we got the protocol, we got the server URL, we got the resource path. But what we have in addition to that is a certain parameter. It could be a set of parameters too, or it could just be a one parameter that we are passing through the URI against the API in order for us to be able to either read something or write something. And our SDN controller is able to understand the request and get us the information we're looking for. Now let's shift our attention to data serialization, and I'm also going to provide a quick overview of JSON. So what is data serialization? Let me explain. So we have a data object. Typically that's complex data. And the idea of data serialization is we want to take that data object that we have stored on our computer, and we want to convert it into a stream of bytes. And why would we want to convert that object into a stream of bytes? Well, we want to allow that data to be stored and transferred and distributed, right? So this is where file, database, memory comes in. And then from those resources, we take that stream of bytes and we convert it back into an object on the destination end. This entire path from left to right is called data serialization. So let me give you an official definition of data serialization. It's a process of converting complex data into a byte stream for storage, transfer, and distribution purposes on physical devices. So if you think about it, guys, different computer systems and environments have their own proprietary data format. So if you look at Microsoft Windows, it has its own proprietary stuff. And if you look at Apple Macintosh, it has its own proprietary stuff. And if you look at Linux, it's got its own stuff. And how do we allow the data to be able to talk to each other and these different systems to be able to understand the different type of files and data objects? Well, that's where data serialization comes into play. And what it does is it turns the traditional proprietary data format on its head by storing and exchanging data into a standard format that is platform and language neutral and can be understood universally. So, in other words, the stream of bytes has to be standardized format, and that's what allows us to make this data portable. So as you go from Microsoft Windows to Linux to Mac, you have this consistent standardized data set that looks the same and functions the same. And a couple of additional terms that are related to data serialization. There's a term called deserialization, and it's the opposite of serialization. So here what we're doing is we're creating an object from a stream of bytes. And some additional terms as you read through different text, different books, you're going to come across could potentially be data serialization language. It's also known as data modeling language. And by the way, JSON belongs to a standardized format. So does XML. But today I'm going to focus in on the JSON format, which is a data serialization format. JSON stands for JavaScript Object Notation. It's one of the most popular data formats for dealing with web APIs because, first, it's an IETF standard defined in RFC 8259, which makes it widely adopted globally because it's an open standard. It's human readable, which makes it very easy to understand and learn. It requires less coding, which means you don't have to be an expert software developer to write JSON scripts. And JSON processes faster on machines. So whether you're using a $10,000 desktop machine versus a $500 cell phone, it's going to get processed very fast and very efficiently. REST or RESTful APIs mostly use JSON, and that's what makes JSON so popular as well. And to understand JSON, the big thing with understanding any data format is to understand the different data types that are supported by it. So if you guys have any software development background, you will understand what the different data types mean. And even if you don't, just hang in there with me. You'll get it as I go into the detail. So the first type is string, second number, Boolean, null, object, and array. These are the 6 data types that JSON supports. And before I get into the data types, let's quickly look at Ferrari Enzo. And one thing I want you guys to familiarize yourself with is there's this whole idea in JSON called key value pair. So here we're saying, who is the manufacturer or the maker of this car? Well, obviously it's Ferrari. So what I'm saying is this is the key and this is the value. Like I said, it's the key value pair idea. Well, what's the model? It's an Enzo. What year? 2004. Color, red. Price, forget about it. Because it is very ridiculously priced. As a matter of fact, quick tidbit, Ferrari only produced Enzo between 2001 and 2004. And there's only a handful of these globally, and they're only appreciating in value more than real estate. I think the last one sold in an auction was $3.6 or $3.8 million or some ridiculous number like that. But that's not the point. I digress. The point is that we have this key value pair idea in JSON. So maker would become a key. Ferrari would become a value. Model would become a key. Enzo will become a value. Year would become a key. 2004 would be a value. Color would become a key. Red will become a value. So on and so forth. You get the idea. And this is what the entire structure is based around when you learn JSON. Once you get this idea in your head, the rest is simple. But this is the big idea, key value pair. Now let's get into the data types. So the first type of JSON data type that I want to bring to your attention is string. String in JSON is a sequence of alphanumeric characters. So here's a sample code. Now, a couple of things I want to bring to your attention here. See, in this sample code, I have the curly brackets. This is the starting bracket. This is the ending bracket. And these are curly brackets. Then space, then we have double quotation marks, and we have a word maker. Then we have a colon, then we have a space, and by the way, we don't need to have this additional space here, but I did it for clarity. Then double quotes again, and the term Ferrari. Now, once again, what is the term maker? This is the key. And what's the value for that key? Is Ferrari, okay? So whenever you're reading a JSON code, you're always going to see that it starts off with a curly bracket. It ends with a curly bracket. And in between, you have key value pair. Here, we're looking at a string data type. Now, based on this understanding and logic, I'm going to continue building on it and explain other data types. The next data type is number. JSON uses JavaScript's double precision floating point format. What does that mean? Here's a sample code. Start of curly bracket, space. Once again, we don't need a space, but I'm adding a space to make it look neat. And by the way, spaces don't matter. White space, I should say, does not matter in JSON. So that's important for you to understand, because in some programming languages, adding space is a major sin. In JSON, that is not the case. So to read the sample code here, once again, we have starting curly bracket, ending curly bracket. In between, we have two bids, bid 1 and bid 2. The first bid, bid underscore 1, I have a colon and then space and number 100. Now notice there is no double quotes around number. We do not put quotes around numbers. Once again, this is key value. Key is the bid is the key, and 100 or bid underscore 1 is the key. 100 is the value. And then bid 2 or bid underscore 2 is once again a key, and 100.99 is the value. And also notice between bit 1 and bit 2, I've got a comma and then space. And then the next string, so to speak. And then the next key value pair. So you see, when to separate key value pairs, what we have to do is we have to have a comma in between different key value pairs. Now let's look at Boolean. Boolean is basically binary. What that means is you only have two possible values. It's either true or false. And Boolean is treated as string values. So here's a sample code. We're saying, is it Ferrari? Of course it is. So it's true. But if it said, is it BMW? We would have said false. You get the idea. The next one is null. Null is essentially an empty value. So what does the code look like? It's saying, is it Roma? We're saying it's null, meaning it's not Ferrari Roma. Roma is a completely different model of Ferrari. We're looking at Enzo. So it's a null. Some additional data types. Now, object, it's an unordered set of key value pairs separated by a colon, like I explained earlier, contained within curly brackets. The values must be unique strings separated by comma. So here's a sample code. An engineer, and that engineer has a name, Naj, company that this engineer works for, WWT, and the city this engineer lives in is San Jose. Now, a couple of things I want to bring to your attention. This is the start curly bracket. This is the ending curly bracket. What about this curly bracket? Well, notice we have another starting curly bracket and an ending curly bracket. Here, this is an object. Engineer is an object that has multiple attributes within it. So a name is an attribute, a company is an attribute, a city is an attribute, but that all of these are contained within the object called engineer. So what we're doing here is we're basically defining an object. As I said earlier, white space doesn't matter. So what you would do is you would typically take, instead of writing the entire code on a single line, what you can do as best practice is to add white space. And what that does for you is brings more clarity. So as you can see, the same code here, again, provides a lot more clarity to what we're trying to achieve here. So here, once again, the object is engineer, and contained within that object are different attributes, which are string values, essentially, because we just learned strings. And it's defining that object. Now, a couple of things I want to bring to your attention from the white space standpoint is, once again, we have double quotes around engineer, we got a colon, then we got space, and then the curly bracket. And as you can see, for each string, there's a comma in the end. That's another string, and there's a comma in the end. But check this out. The third one, there's no comma, because this is the final string that defines our object called engineer. So because this is final, we're ending it with a curly bracket, which started right here, and we're ending it right here. Okay? So this is very important to notice. For exam and also for real-world purposes, there is no comma at the end. So definitely keep that in mind. And by the way, to verify your code that you wrote, ideally what you should do is go and Google the term JSON validator. And what that will do for you is help you validate the code that you wrote. As a matter of fact, let me show you what I'm talking about. Let me look up JSON validator. And I'm just going to go ahead and click on the first option that's available to me. So let me go ahead and run a JSON validator against the code that I showed you a moment ago. And look what it did. First of all, it gave me a confirmation down here at the bottom that it's a valid JSON code, which is beautiful, right? So this is great. and also see what it did to my code. Even though I wrote the code in one line, it beautified my code by adding white space to my code to make it easier to understand. So once again, you see the object engineer, and that object has all these strings. And as I said, there's no comma in the end. To prove my point, I'm going to go ahead and add the comma and hit validate JSON code again. And check this out. It's saying there's an error on line 5. And we know what the error is because we added the extra comma on this line. In other words, this validator is pointing us in the right direction. It's telling us there's something wrong with this line. And by paying close attention to it, we can fix the problem. So if I were to remove the comma again, hit validate JSON, once again, it's telling me it's a valid JSON code. So I encourage you to get into the habit of using a JSON validator as you practice writing JSON code to ensure you're actually writing good code that is bug-free. Now, the final data type, and this one is a very important one, is an array. An array is an ordered set of key value pairs separated by a colon. However, the difference between an object and an array is contained within square brackets instead of curly brackets. And I'll show you some sample codes to hit this point home. The values must be JSON supported data types. And so what are the data types? Well, string, number, boolean, null, object, or array. Now, what's interesting is you might be going, isn't this an array? How could you have an array within an array? Well, that's a mind twister, I know, but that's the idea. An array is a very comprehensive data type that pretty much contains all the other data types, and it has the ability to have nested arrays and nested objects within it. So it allows for a very complex data type that has a lot of objects and arrays within it. So a sample code could be CIS students or computer information systems students. So here I'm showing student name Bob, age 28, employer is WWT, then comma, another student named Dan, age 31, employer Facebook. Now let me add some white space to this code to make it easier for you to understand, and let me bring a couple of things to your attention. So look, here we're starting at CIS students, and then we have a colon, and then check this out, we have a square bracket followed by a curly bracket. And then we have the first student, Bob, age 28, employer WWT. And then we have the ending curly bracket. Then we have a comma. And then we have a starting curly bracket for the second student. So student is Dan, age 31, employer Facebook. And then we have the ending curly bracket. And then we have the ending square bracket. And then we have the ending curly bracket to end the entire code. So as you can see, here we're showing computer information system students, let's say in a college or a university, and different attributes associated with each student in that course. Now let me show you another sample code. So here the student name is Bob, age 28, classes, Comp 101, Soft 101, Net 101, employed, false, employer, null. Let me add white space to it, and let me give you a quick walkthrough of this code. So here I'm saying I have a student name, Bob, age 28, classes that this student is taking, Comp 101, Soft 101, Net 101. This student is not employed, employment is false, and employer is null. Because they're not employed, so of course there's no employer to report. Now, one interesting thing about this example for you guys is, check this out. We have all the different data types covered here. We got the string data type, we got the number data type, we got an array here, we got the Boolean data type, and then we also got the null data type. Moving on. Now let's shift our attention to DevOps. So what is DevOps? Now I touched base on it in my last video as well, but here I'm gonna go slightly more in depth. Now, just to set proper expectations, DevOps is not really part of CCNA. This is more of an advanced concept. It's only highlighted at a very high level in the exam, but I think it's a very real world topic right now and very important for you to understand as a network engineer, because today's network engineering is all about DevOps and you must understand what that means. So what does it stand for? Well, it comes from two different terms. Software development, that's the dev piece of it, and network operations, that's the ops in the DevOps. So when we combine the two together, we get the term DevOps. Now, you might be scratching your head thinking software development and network operations are two completely opposite ends of the spectrum. So what are we trying to do here? Well, let me explain what has transpired over the past decade, especially over the past half a decade or so, that has accelerated the trend of adopting the DevOps movement. So first, let me take a step back and give you the official definition of DevOps. It's a discipline of applying software development agile methodology principles to networking. So for those of us that are familiar with agile type project management approach, agile methodology is basically we do projects in sprints and we do them at a very, very rapid pace. Sprints are basically the amount of time that each sprint might be made up of. So for example, you may have sprint 1 that is 2 weeks long. And then you have another sprint, sprint 2, that is another 2 weeks. So by defining different sprints, you're breaking the project into smaller chunks and smaller pieces, hence achieving the ability to have a lot of agility. This is where the name agile methodology comes from. Okay, so that's the first definition of DevOps. The second definition of DevOps, and I'm using another term here, which is also interchangeably used with DevOps, is called NET DevOps. And here the NET stands for network, of course. So NET DevOps is a practice that facilitates collaboration between the network design and network operations teams in order to automate the process of network design and changes. So what the second definition is saying is we have evolved. So remember how we used to be cavemen and then fast forward 21st century and we're now living in a metaverse. Similarly, we used to do things by hand. Now things are changing. Now we need to automate because there's a proliferation of technology, new IoT devices, new hacking attacks, and with new demands, we have to have a new type of methodology of doing things. So Net DevOps encourages network designers or architects to work very closely with network ops teams that are traditionally used to just managing and monitoring networks to create a automated workflow for network provisioning and for network changes. What that eventually leads to is what we call infrastructure as code. It's a buzzword, and you may also hear some other terms that are interchangeably used with infrastructure as code. Terms like programmable infrastructure and software-defined infrastructure. Now, the agile methodology in DevOps introduces what's called CI/CD pipeline, which is a catalyst for automation. So what does CI/CD stand for? Stands for continuous integration, continuous delivery. And sometimes the CD could also be called continuous deployment. Now, the continuous delivery is a more preliminary step. Continuous deployment is for organizations that are more mature on the DevOps spectrum. The whole idea is that we treat our entire network from start to finish as a pipeline. So now let me zoom into the DevOps framework. So here, once again, like I said, we're bringing the development team and the network operations team together. So what happens is, the first thing that happens is the development team comes up with a game plan. They think of or conceive of an application they want to design. So they go through the planning phase. Once they have determined what they want to do, there are dedicated engineers and teams that start writing that software code. And what I mean by build is that they either build the code from scratch or they integrate the code into the existing code that's already written. So for example, if you're adding a new module to an existing application, you would integrate code, but you may very well be starting from scratch. After all these steps, you would want to test them to ensure that the code is valid and bug-free. And then at that point, a handoff happens to the operations team. And this is where the release comes in. Then you release the code into the wild, but you do it in a very smart fashion. Typically, you go from test to a dev environment or quality assurance environment. From there, you deploy the code. And at that point, the code is now deployed into the production network. And then you operate the network at that point and you monitor. You see the changes that you introduced into the network, whether or not they had a positive or negative impact. And as you can see here, it's a continuous loop. It's a self-perpetuating continuous loop of changes. From monitoring, you go back to square one again. You look at what else needs to be done to continuously enhance the security of the network, to continuously introduce new features and functions into the network, to add more stability to the network. You go back to planning, you code, you build, you test, you release, you deploy, you operate, you monitor. So you get the idea. It's a continuous loop, and it's a never-ending infinite loop. Hence the reason for the infinity symbol here is that it's just a continuous cycle. And to give you another perspective, typically when you write the code, you test it. And what you would typically do is you would create a bunch of virtual machines or containers to set up a test environment. From test, you will go into your dev environment. It's also known as quality assurance environment. It just depends on the organization, the terminology used. But the idea that the big difference between test and development environment is that development environment mimics the production environment very closely. So test may not have anything production related at all, but dev is an exact replica of the production. But the difference is there's no production devices plugged into this. It's just a replica to ensure that if the code was to be released into the production environment, it's going to function as intended. And then once you're 100% confident that your code didn't cause any issues in the development or the quality assurance environment, is that you're going to have the ability to go ahead and launch that code into the production environment. And this is where CI/CD pipeline comes into the picture. As you can see, this whole entire thing is a pipeline. As we go from test to dev, from dev to prod, it's a pipeline. And each element within the pipeline, we can go ahead and automate. So we can write scripts to spin up VMs and containers to quickly set the test environment. We can do the same thing in the dev environment. And finally, the code gets released and deployed into the production environment. And that said, deployment is where we're going to focus next. This is where the automation tools or the network configuration tools come into play. Things like Ansible, Chef, Puppet, they live right here. Let's get into that next. But before I do though, I think it's important to let's take a step back and look at how we got here and what led to the whole DevOps mindset. And by the way, DevOps is not as easy as just sending a bunch of your team members to take a DevOps certification class, and after they get certified, all of a sudden, magically, your organization is now DevOps organization. It doesn't work this way. What it is it's a cultural change. It's a cultural shift in the way your organization operates and functions. The organizations today have a culture of fear. What that means is changes happen rarely in our network. Changes are big and complicated in our network today. Teams aren't well prepared and practiced to handle changes. Changes are seen as high risk. Problems occur as changes are introduced. Think all the weekends and late nights after business hours that engineers and teams have to spend for changes to be pushed. And changes are seen as failure. So if you are a traditional network engineer, if you are making a ton of changes to your network every year, you're going to get dinged on your annual review with your boss. And most likely you're going to get fired for making changes because changes are considered bad in the legacy or a traditional network engineering mindset. But that's a culture of fear, right? The leadership, the way they design the whole culture is to eliminate and reduce the number of changes. But that's not the fact of life today. If you look at your phone or your iPad or Android, one thing you'll see is almost on daily basis, there are app updates that are being released to make the apps better, faster, more stable, more secure. Similarly, organizations need to be on the cutting edge to have a competitive edge in the marketplace, and they need to adopt change. And this is where Net DevOps come into play. So with Net DevOps, the mindset is changes are part of life. Each change is small. Team is well practiced because that's all they do. They write code, scripts, things of that nature. You test the heck out of those changes in a test and dev environment, like I alluded to on the last slide. Change is typically uneventful because you already tested it and you verified it in your quality assurance phase. So you know there's going to be zero impact to the environment. And changes are actually rewarded. It's considered a success. So the more changes you make as a Net DevOps engineer, the more praise you're going to get from your leadership. You're going to probably get a bonus, a promotion. You're going to be rewarded for more changes. So you see the difference. The difference is a 180-degree shift in how the organizations operate. So now, as you can see, it's not just a change at a network engineering level, but it's a change at a leadership level in the organization to change the company from a culture of fear to a culture of change that embraces change and thrives in the 21st century. Now let's shift our attention to configuration management tools. I'm going to provide a quick overview. The first tool I want to look at is Ansible. Now, Ansible is an agentless network automation tool. It's an open source tool, so that automatically means it has a free version available, but it also has paid versions for enterprises. Now, you may ask yourself, why would I want to pay for this service as an enterprise? Well, trust me, you do. Because when you have a paid version, you have a bunch of engineers that are available to you in case you run into any issues. You can contact them via phone or they're just an email away. So you want to have access to those support resources if you run into issues. Now, Ansible Server can be installed on a Mac or Linux, and it uses a push model. And what that means is Ansible doesn't rely on any code or agent running on the network devices. The code actually runs on the Ansible server, and configs can only be pushed to the network devices via the Ansible server using SSH or netconf. So it's a one-way change that gets pushed to the devices from the server to the devices in that direction. Now, Ansible server contains some text files. Once you're done installing the Ansible server, there's a couple of text files that you need to be aware of. The first one is called playbooks. It's a master instruction file with step-by-step tasks. There's also another file called inventory file. It's a list of all the network devices in the network. Then there's templates. It's a baseline config with variables using Jinja 2 language. And finally, there's a variables file. It's a list of variables that Ansible will substitute into the templates using YAML. And YAML stands for YAML Ain't Markup Language, which I find hilarious. Somebody got really cute with the name here. And now here's a visual view of what I explained so far. So we have an Ansible server, could be a VM or a container or whatever have you. We have an inventory file, we have templates, we got variable, we got all these files that are subset of the playbook. And then what we do is we run that playbook via SSH or netconf, and we log into the router or switch, or in this case, it's a router. And by running that playbook, we're pushing a certain configuration to that device. Now let's shift our attention to Chef. That's another very popular network configuration tool. It's an agent-based network automation tool, and it uses a client-server model. It's open source, so once again, it has both paid and free versions, and I explained earlier why you would want to be on a paid version if you're doing this in a production environment. Chef can be installed on a Mac, Linux, or Windows. It uses a pull model, so this is the opposite of the Ansible. Here we're pulling information. So the idea here is each managed network device runs an agent called Chef node or a Chef client. So managed device is basically a client. Router, switch, firewall, you name it. An agent monitors and compares its configuration against the configs available on the Chef server and automatically synchronizes the configuration if it finds itself to be out of compliance. And here are a couple of text files that are contained after you're done installing the Chef server. You have a file called recipe. This is the master instruction file with step-by-step tasks. The next one is cookbook. It's a list of all similar recipes grouped together. Another one is called run list. It's an ordered list of recipes for a given network device. And finally, there's a text file called resource, the config objects whose state is managed by Chef. So let me quickly give you an overview of how it looks like visually. So you have a Chef server, which could be installed as a VM. You have a resource file, and then you have a recipe or run list, and the resource is a subset of that. And what a Chef node in this case would do, which is a client essentially, is it would actually pull details from the Chef server. And when it finds that it doesn't have the information that it's expected to have, it goes ahead and pulls that configuration. So the onus is actually on the network client to be able to pull its configuration, compared to Ansible, where the change was pushed from the server in the direction of the client. Here, the client is asking for information from the server. But the big difference here is that you need to have a client, a little piece of software. It's a very lightweight software running on your network endpoint. Now, one big thing to keep in mind is not all network endpoints are created equal, so they do not have the ability, some network endpoints, to actually have a client installed or an agent installed. So you have to be very careful when you're deciding on using the appropriate tool chain for doing network automation. Make sure you're picking the right solution for your environment. In other words, if you have a lot of old Cisco gear in your network that you're not planning on replacing anytime soon, then you should probably look at Ansible instead of Chef. Because most likely the network devices you have in your network today, if they're older switches or routers, they may not have the ability to install an agent on them. So you're going to have to rely on something like Ansible to be able to push configs. Something to keep in mind from a real-world perspective. And finally, we're going to look at Puppet. This is another very popular network automation tool. Once again, very similar to Chef. It's an agent-based tool, client-server model. It's open source like the rest. It has both free and paid versions available. Puppet Server, also known as Puppet Master, can be installed on a Linux or Windows. It also uses a pull model, very similar to Chef. Each managed network device runs an agent called Puppet Agent. An agent monitors and compares its configuration against the config available on the Puppet server, and when it finds itself out of compliance, it automatically synchronizes itself by pulling the config. Now, once you're done installing the Puppet master or the Puppet server, it contains the following text files. It has what's called a manifest. This is the master instruction file, and it contains what's called the desired end state of the network endpoint or Puppet agents. And then it has another text file called resource or class or module. Typically, these terms refer to manifest components, with module being the largest component. And then within module, we have different classes. And then within classes, we have resources. And finally, we have templates. It's a baseline config used to generate manifests by substituting variables into the template. Here is how Puppet works. We have a Puppet master, which is a Puppet server installed as a VM. We have templates and variables, which are basically a subset of the manifest. And then we have a Puppet agent. Puppet agent pulls details from the manifest to compare the config that it has against the desired state defined in the manifest. If it finds itself to be out of compliance, meaning it finds out that it's not complying to what the end state is defined in the manifest, it goes ahead and pulls the config. Once again, the onus is on the agent, not the server, to pull the configs. And finally, how do they compare and contrast? I'm glad you asked. This chart right here provides clarity on how they all operate. First, looking at the master file, right? So Ansible has playbook. Chef, it's called manifest. Puppet, it's called recipe or a run list. The protocol required on the network device, in Ansible, it's SSH and netconf. In the case of Chef and Puppet, we rely on HTTP, which basically means we're relying on the northbound APIs. Now, Ansible is agentless. We don't need to run a piece of code on the endpoints, whereas Chef and Puppet both require an agent to be ran. Now, that said, I want to let you know that at a CCNA level, this information applies, but at CCNP, CCIE, and beyond, and from a real-world perspective, both Chef and Puppet have standalone agentless solutions as well, but they are a lot more kludgy to implement and not very popular. Typically for an agentless, Ansible is the most popular solution out there. And finally, Ansible is a push model, meaning information gets pushed from the server down to the client. Whereas both Chef and Puppet, it's a pull model where the client or an agent running on the end point is responsible for pulling the config to ensure it's in compliance. And that wraps up the CCNA course. And always remember, in this class, the ultimate goal, the ultimate prize is to become CCNA certified. May the force be with you.